Shankara has come.
Good morning to all. Welcome back for the day 2 session on National Workshop on Electric Aircraft and Allied Technologies. So we will start with the first fifth technical session. To chair this fifth technical session, I kindly invite Sri M. Shankaran to come on to the dais and chair the session. So it's my privilege to introduce Sri M. Shankaran. He holds Masters in Physics and from Bharatiya Dasan University, Tirupati, and is presently Director, You Are Now Satellite Center, Bangalore. Sir, please. Sir.
Good morning. Very happy to be part of this National Workshop on Electric Aircraft and Allied Technologies. Today in this session we have 7 presentations related to battery cells, packaging and battery management. The main issue related to electric mobility is the safety of the battery, the gravimetric and volumetric energy densities of battery or even the fuel cell system, and of course the cost. And finally, the technology is required for fast charging, because the battery, when we are using, the chemistry decides what is the energy density in terms of volume and weight, but it also decides its ability to discharge and charge at higher or lower temperatures, and the rate in which it can accept and the charge and it can discharge. So this is a involved process. The electric vehicle technology for surface transport has taken up, of course, not so much in our country, but elsewhere it has been reasonable success, though always the safety and the range has been concern. Similarly, the effort to make the air travel also electric mobility based has been gaining momentum elsewhere for obvious reasons like environmental friendliness, lesser noise and vibration, and of course sustainability is the main bottom line for this electric mobility, even in air vehicles. There have been some demonstration vehicles that have been done elsewhere in the world by NASA as well as some private entities. And it is commendable that NAL has thought it fit to take it up for this as a subject of study and conducting this national workshop, 2-day national workshop. Let me compliment and congratulate the NAL team for organizing this workshop, and I'm sure that this workshop will act as a inspiration for the researchers and people who are working in this area of electric mobility, and of course the aviation technology, aeronautics related technologies, to identify and take up research in the key technological area. Now, let me invite the first speaker of this session, Dr. Siddharth Mukhopadhyay, Head of the Department in the Electrical Engineering in IIT Kharagpur. He holds a PhD in Integrated Vehicle Health Management, Aerospace Tracking and Guidance, Industrial Automation and Cyber Physical Systems. He is currently building an indigenous plug-in hybrid electric vehicle under the Uchchatar Avishkar Yojana program of Government of India jointly with Tata Motors Limited. The topic of his talk is control and energy management of electric vehicles. Dr. Mukhopadhyay.
Thank you. Namaskar. Good morning. I'm very happy to be here. I was about to miss the visit, but because these are fantastic opportunities for an academic like me to learn. These sort of coming and talking to the people there. The mic, I don't have a collar mic. Oh, okay, I have to stand here and have this class mode. So, yeah. All right. Yeah. Okay. So first of all, thanks for the opportunity. And I always like to make my acknowledgements at the beginning. So I'd like to acknowledge my sponsors, Tata Motors, the Government of India, and with whom I have done this work and learned. Of course, the colleagues and students of IIT Kharagpur, and particularly two of my very senior PhD students, Rupal and Susenji, various colleagues of the industries with whom I have worked. So let me start with the disclaimer that this talk is about, my experience is in electric vehicles. And so my experience is mainly EVs, but when we talked to Dr. Kota, I suggested that there's a big issue of energy management in EVs which arises, which all OEMs face. And we don't talk about it that much. And I believe that a lot of that will be applicable probably in more stringent context for an aircraft. So I opted to at least talk about energy management more. I mean, opted to talk for energy management rather than battery management, which we also do. So that's what I have written, that the talk was proposed in the belief that I'll try to explain to you the energy management problem in this amount of time. It's not difficult. I mean, it's very difficult to go very deep, but I hope to give you a feel about it and the criticality. And so I'll talk about it in the context of EVs, but I'm sure that we'll be able to explore many parallels to EAs. And in spite of there being parallels, I feel that there will be several, unique flavors and formulations for EAs, which I feel we need to work on. If we do not work on them, and I mean, whenever people talk about electric mobility, people, because we are kind of at the beginning, we talk a lot about about motors and batteries. But I always say that you must have a great musical instrument, but the instrument does not give you great music. You have to play it well. So energy management is related to the playing of that instrument. So that's what I am going to talk about. So we need to do a lot of work. Not many lectures talk about. So just to put a context, this is the vehicle that I'm talking about. We are trying to build it also. So it's the simplest of hybrid electric vehicles. It's a parallel hybrid electric vehicle, and there are two propulsion sources. One is the engine, and the other is the motor, which are connected on the same shaft. And then the motor is fed from the power electronics converter and the battery. And there is a gearbox, and there are some clutches. So this is the situation that we try to explore. So when you talk about energy management, you could talk about it in different scale. So you could talk when you are driving, you could talk about how to take great energy saving decisions, taking the 20-30 meters situation in view. So when I was coming from the airport, I was watching how the airport taxi driver is driving, and I was realizing how it is different. How that style is different from the driver whom I pay. So the airport taxi driver was very conscious about energy management, and if he sees that there is a block ahead, 30 meters ahead, he will never accelerate, never do any lane change, because he knows that if he accelerates and actually does a lane change, he'll have to go and stop again. So he's going to lose some energy. While my driver never does that, he tries to get me quickly. So this is local energy management. But finally, we are, and this is very true for an electric aircraft, that we are interested about energy management over a trip. So over a trip means when I am standing at any point, I do not know. There is immediately when I'm talking about a trip, a lot of future comes into play. What is going to be the traffic? Let us say 10 kilometers ahead, 5 kilometers ahead. How I'm going to take care of how am I going to use my battery optimally for this overall trip? That is trip level. And every driver, if you buy an electric vehicle, every day, multiple times, sir. Yes, sir. This is a new topic. Every. Okay. So I understand, sir. I'll try to. So every trip you will have to. So you can do a trip level energy management. The moment you try to do that, there is a lot of uncertainty. So I was thinking about an electric aircraft. When you are taking the aircraft on a let's say a trainer aircraft. Please correct me if I'm wrong. You know much more about aircraft. You are probably going to do various kinds of maneuvers under various kinds of circumstances. So each of them are actually going to cost energy, and the temperature, the altitude at which you are going to do it, at the velocity that you are going to do it, each of them are going to have energy impacts. So you have to plan them when you are actually going for a short, and some of that are actually going to be uncertain. So when you are doing a trip level, you have to look at all that. And then we'll not talk about it. I mean, for a car, actually, you have to do life cycle level energy management also, because the battery is extremely expensive. So when you try to do all that, one of the things that actually comes to mind, becomes clear that you cannot solve this energy management problem, particularly when you are talking about trip level, sitting in the car itself. If you want to solve that problem scientifically, you need information from other sources. And today, all OEMs are actually trying to provide those services to this customer, so that the customer gets the best value over trips and over a life cycle. So you need inputs from various sensors that you could put on the car that will improve your energy management, and you could also get various kinds of information from cloud and GPS and things like that about traffic, etc. So you must utilize all these informations to be able to manage the energy over the trip well. And as it turns out, so the overall control problem is actually, multi-loop, and it is somewhat like an pilot guidance loop kind of problem. So you have these initial loops, and then you have a supervisory loop, and then you have an adaptation loop, which is like a guidance loop. So you have this is a standard architecture. Advanced driver advisory system. So if you come to see what causes energy, you will find that finally energy is actually spent in the vehicle, and it comes from the torque speed operating point and the efficiency of the machine at that point. But these can be affected by various factors. So it can be affected by a driver. So there are aggressive drivers who will constantly accelerate, decelerate. So if you do unnecessary maneuvers, you will lose energy. It's affected by terrain, road conditions, affected by traffic. It's also affected by loop. So there are several factors which actually come into play. And this is what basically the same thing. So at the local level, it actually boils down to choosing the best. When you have different power sources, it actually boils down to choosing the operating points of the individual power sources, how much of torque you want to generate from the engine, and how much of torque you want to generate from the motor, and how you can do that instant to instant in the most optimal way. That is energy management locally. But we have to remember that you have to meet requirements. So the first requirement is that some of the torque of the engine and the motor must meet the torque demand. That has to be made, and that immediately opens up the question as to what is a good torque demand. So you can actually play with torque demand to save energy depending on what you want. So you can also, when you have multiple power sources, you can operate from moment to moment. You actually operate the vehicle in various modes. Yeah, I'm sorry, sir. Yes, this is better. Are you able to hear me now? Yeah, hello, can you hear me now? Tap what? Yes. Yeah, you can hear me perhaps. Yeah, thank you. Thank you very much. So we typically in the local level we try to create this thing. This is called the torque split ratio. How much torque to generate from the engine? How much to generate from the battery? So in your case, I mean, if you have a fuel cell and if you have a battery, then you could think of which I mean, you can. The problem can become actually three types. If you have an engine, if you have a fuel cell, if you have a battery, then you have three power sources. Then you like to divide the torque optimally, and then you can go through different modes, and the car actually continuously switches. You can have a motoring mode, you can have a hybrid motoring mode, where you have the engine and the motor operating. You have an engine only mode, or you can have a hybrid generating mode where the engine is actually driving the car and also charging the battery, and you can have a regeneration mode. So you continuously switch from mode to mode. Whenever you actually try to do anything optimally, you must have a degree of freedom. If you don't have a degree of freedom, you cannot do any kind of optimization. Then your solution becomes unique. So if you have an electric vehicle without a gearbox, actually your degree of freedom is zero. If you give a torque demand, it will be made in a certain way depending on the equipment characteristic, and that. But if you have a gearbox, which is true for a conventional vehicle, you can actually choose the operating point. If you have two parallel sources, then you have 2 degrees of freedom. So the idea is for optimization is to create these flexibilities and create degrees of freedom, so that under different situations you can actually optimize the energy, and this is done. So how do you do model-based optimal energy management? So the driver is constantly pressing these accelerator and brakes. So one of the trade secrets of these OEMs is the torque structure model, that based on the driver's input, how much of torque demand is actually placed on the energy management system. So the net torque demand is actually given to the energy management and this is like a control loop. So you have a reference input, you have a state feedback, and you have control input, and you have an output. Like this. And so big issue, scope of energy management which is here is based on these driver models, etc. How to generate a net torque demand? This is an open question, and you have to answer it. So this is how you do optimal energy management. And there are various optimization strategies. So this is a popular strategy which has been actually used in vehicles. It's an instantaneous strategy. So you are saying that I want to minimize fuel consumption, but then fuel consumption comes from two. I mean, there is consumption from the battery, and there is consumption from the engine. So the engine consumes real fuel. It also consumes energy. So you have to have an equivalent fuel corresponding to that battery. Therefore, you have the equivalent fuel consumption minimization strategy. And because the battery has a finite capacity, therefore you need to weight the battery discharge. So typically you will weigh it. So you will typically say that you can, especially this is a big difference, because when you are having a plug-in hybrid, then cost of battery energy is much lower than the cost of petrol. So when you have good amount of state of charge, you actually make this number very small. When you have low charge, as you are progressing into the journey, you are having less and less charge. So you are going to weigh this gas higher and higher. So that in the optimization, you actually draw less power from the battery and draw more power. So you can do these optimizations. This is that was an instantaneous one. You can also this is a very one of the most popular control strategies currently in the world, which is applied in various application areas, but it can be applied to very realistic situations. So you can also apply here. And here you are not optimizing over an instant, but you are optimizing total fuel over from physical to field. So you are also looking into the future. So you can do these optimizations. Now, the moment you are optimizing from you are standing here on the road at this time, wherever you are, and you are to optimize over a distance of time. You don't know what's going to happen in the future, right? So immediately the question of estimation and prediction comes in. So there are questions of future velocity forecast. When you are talking about a short distance prediction, let us say 30-40 meters, then you can do it with the in-vehicle sensors, or you can do it statistically if you have a low traffic density. And when you are doing a long range velocity forecast, then you are using things like GPS GIS data, or you are using cloud services where actually your position can be known because of this V2X connectivity. So all OEMs try to build these services. So there are a whole lot of factors that will come in when you trip energy modeling, and I think this will be important for an electric aircraft. I mean, given a facility, it will be very critical for a scene. I mean, even for any manufacturer, stopping of a car on the road is an absolute no-no. But for an aircraft, it's not simply acceptable. So one has to be very careful about how much energy is left, and then how to use it optimally for the rest of it. So I'll skip this. I just say that. So we saw that if we talk about electric vehicles, we saw that the degree of freedom is 0. If you talk about trip-level energy management, you can create degrees of freedom by saying that I can play with the document. So even in electric vehicles, without gearbox, it is possible. So this looks like math, but these problems are now you are actually able to solve this problem in real time. We have solved this using modest computing facilities, somewhat using some approximate models. And some of these things you have to remember that batteries get old and vehicles get old. So and for every trip, the characteristic of the vehicle can change. Load can be different, CG position can be different, atmosphere can be different. Every trip is actually a different trip. So you can for every trip you will have to optimize this thing. For example, the resistance of a lithium-ion battery is actually very dependent on its SOC. So the resistance value that you will use at the beginning of the journey and the resistance value that you will use at the middle of the journey are not going to be the same. So you have to constantly adapt your optimization. And so these are you have to generate various kinds of torque structure model. I'm skipping these that in the interest of. Now when you are doing trip level optimization, you will have to do segmentation, because you will have to solve the thing. You are solving a problem, you are solving this optimization problem almost every 10 to 20 milliseconds. Every 10 to 20 milliseconds, you are creating another torque. So if you start doing that for the whole trip, then it becomes an unsolvable problem. Right? I mean, just too long. So you solve a problem the whole trip, keeping average conditions. So you say that look at the Google map and say from here to the next 500 meters, I have a blue traffic condition. So my average speed is going to be like this. So I want to spend this much of battery there. So then I optimize for that segment. Next segment I am going to have a red condition. So my velocity is going to be much lower. So when I plan for the whole trip, I solve the problem in smaller segments. And then taking those values, I solve the in-segment problem in much more detail. So you actually try to reduce complexity by doing segmentation on the trip. And you also generate SOC reference. This is very important because you imagine it will be very important for the aircraft certainly because you have to do certain amount of you have to do certain amount of maneuver. So for example, for a car, if you know that at some point you have a 1 kilometer stretch where you have to go up. So your torque demand will become 3 times. So you have to manage your energy in such a manner that before you reach that point, you have actually built up enough SOC that you can cross that point. If you don't do that, if you actually use the battery in a greedy manner, then you will, when you will reach that point, you will not have enough SOC to actually traverse it. So you have to take care of it. So you have to generate SOC references which say that I want to do energy management in this segment in such a way that at this point I am going to have 90%. So I have to plan that ahead and then do energy management accordingly. Yeah, and there are various ways of doing. You can have a charge sustaining mode. Suppose you have an Ola vehicle. So that vehicle is actually going from trip to trip to trip. So at the end of every trip, it has to have a good battery condition such that it can take up the next trip. If you are going to the office, then you can actually discharge the battery and then charging for the next 4 hours. So you can choose a charge depleting mode or charge sustaining mode depending on your usage, and the energy implications are going to be quite different. So yeah, so this is what I was saying, that you have to also adapt your energy management. So the adaptations can be vehicle specific, and they can be powertrain specific, they can be driver specific, and all that. So you see that the optimization weights can also be changed. It depends on the drive side. So if you are driving from here to wherever, let's say the airport, at in the morning, you will do energy management using a different way than if you are doing it at 5. So I think these will have implications also for the electric aircraft. So you are going to have, whether, especially, I don't know what the aircraft is going to be used for. If you use it for, let's say, vaporizer and other things, depending on the conditions, your optimization parameters will change. This is for recognizing what kind of drivers are driving. You can classify the drivers and you can use. So exactly, this is what I was saying, that if you go to major cities in Europe, you'll find that city center you can only take your car if it has zero energy, zero emission. So if your car is emitting, so if you are a hybrid vehicle, then you have to, if you are crossing the city center in your car, you must run the car in the EV mode. So that you have zero emission. So when you are entering that point, you must have enough resources in the initially the SOC was coming down, but at some point when you realize that you are actually going to the zero emission zone, so you started charging the battery, and at this point, this is the zero emission zone, the emission comes to zero. You have to build up enough resources that you can cross. Similarly, the case for heavy. This is just the algorithm for doing that. So I'll not get into this, but we are actually trying to solve this problem for some industrial and a dual problem. The problem that I'm talking about is, given this much of battery, we'll use the battery optimally for going from here for going from A to B. The very related question is, given this much of battery, how far can I do? So the electric rate estimation is actually a very similar problem. So you can also solve that. This is the chip level energy. I mean, it's a fairly complex two-level optimization. Just to show you a background, you can actually plan your velocities taking many things into consideration. One of them could be traffic lights. So how can you drive so that you will escape traffic lights if you knew the traffic lights, you knew the traffic light conditions? And of course, you don't have traffic lights for an aircraft. So you can merge. Today's ADASs are mainly concerned with driving comfort and driver safety. So they are designed to work so that you have a safe distance with the car ahead. So that if somebody is trying to do a lane change, you don't collide and things like that. But you can have ADASs which actually merge energy and time optimization with that. So you can have mixed optimization strategies.
Possibly sensors where
So these are used, but yeah, exactly. Actually, sir, camera is much cheaper. Camera is much cheaper, but what's the data? What's mostly the data? There are lots of lighting. Now, even not even self-driving. I mean, self-driving is actually a very large spectrum. You can have various self-driving. Yeah. I just want to say that you see that if you use a normal traffic jam assist, is a feature of ADAS. These are all, they're all simulations, but using the current, industry standard models, I would say. If you do a energy optimal eco TGS, then you can spend about, this is a simulation, minus 9.38%. So your energy you can actually save. But your travel time will now increase because you are giving slower operating points. And if you do a energy optimal thing, then you can, in this case, they had, you can get further time optimization. So you can actually merge ADAS and energy management to get an energy management aware drive advisory. So these are, so I've almost come to, so finally your energy management strategy will look somewhat like this. It will happen in 2 or 3 levels, and then finally all these SOC mean, distance mean, SOC reference, fuel reference, etc. These will come, and then here you will do the operating point choice for the vehicle. So that's it. This is my last slide. So the problem is, even for vehicles, it's partially solved at present. And a more complete solution will require technology like 5G wireless, GSM, cloud computing, all these things. Because especially, even battery models can be, depending on what models you are running, you can run very, very, very complex electrochemistry models in battery in the cloud. You can run your individual battery in the cloud. And their optimal strategies will need parametric tuning. So it is now recognized that it is very critical for XEVs, and I think it is going to be even probably more critical for electric aircraft. And but we need to work on that. We have not worked on it. Yeah, thank you.
Yes. That's what I'm going to ask. I see all the battery model. Battery model. We are facing a lot of problems in our unit. But see, standard given, and then as per modeling, not working. You are not simulated in your.
Yes, sir. You can. So there are various ways. So there are 2 kinds of things happen. One is that your battery capacity will be maximum charge the battery can hold will be. The other is that the internal resistance will rise. So these are 2 different, broad relations in which this happens. So you can track them. You can track them using various kinds of things. So people do very advanced electrochemistry battery monitoring. They actually do dendrite formation estimation, etc. You can use simpler models. If you use very complex models, you have to go to that one. If you use simpler models, you can do EREA output.
That should be included in your.
It should be, yes, of course.
In an electric vehicle, it's managing the energy, critical parameter.
Yes. So you have taken, there is potential, just put something from equipment. You have taken potential out of that.
personally understand, I understand the optimization of technical. Okay, and this is good for production work, and practically derive very simple and most of here, you cannot expect that while running or while flying, I'll pick up connectivity and get the results. But that's something not happening in the next 20 years.
So it will happen in the next 5 years. It is already being built by that. What it takes to do crowd computing side? Take the cell phone thing. Take the cell phone thing.
It doesn't make sense. Be able to write simple, very simple algorithm from this study, which can be easily implemented by microcontroller. If you are not able to do that, it's all
You can make it multiple ways. You can do it the way you say or pattern. And today microcontrollers are actually amazing. They can do much more than simple rules. They can also solve optimal problems. You are asking that tell me here now if I place I'll be in that junction. While crossing that junction, how much energy will I save? Decide that. How do you know that? So there are cars already passing the junction now. Those cars are sending information how much energy they have spent. So the cloud computer actually machine learning. We are given that.
So all that simplified. You are that someone is going to decide.
Yes, nothing you cannot do in the cloud. It's being a
That signal seeing is that by very simple. Like we do it every day. If I see a bad signal, I put accelerate. But it won't accelerate. And that part of understanding can be put in a very simplified books. But again, not very, it's not asking you to do it.
Thank you, sir. But they're already done. They're already done. But I'm telling you that with today's hardware, you can do much more than that, which will also do your
Not needed. You please do that. Simple rules, you will not be able to get even 2% extra advantage. Please do that. Try to see how much extra advantage you get.
Automobile is having lot of regenerative braking. Okay. It is not there in here. So they won't break at all. Only that and brake. Okay. So it is, but the issues are different there. Okay. So that and all, that's why our technology and modeling, they are not able to take direction. They need another model.
You want to take directly, even in automobile.
Simpler for aircraft than it is much simpler for the aircraft. Not the whole sector.
Sir, valid in
Yes.
here.
There are 2 points. One of them is related to your algorithm, one is speculative. So, most random traffic on the road, aircraft is much because the road is planned, even the piloting is largely similar. So, some of these unknown factors go in the aircraft.
There's window, there's wind and there's weather.
Yes. So, weather from radar nowadays you can get. So other things though, like clear air turbulence. One, spoke about saying every 10 milliseconds or so, because the aircraft is going to cover much greater distance in that time. So in case of such sudden, say clear air turbulence, can the system respond? And what will be a response time? I know I've not given you enough data for an answer, but I'm.
No. The question is very valid, sir. The things are happening at several levels, at several time and space scales. So if you are talking about a sudden event, it has to be handled at the lower time scale level immediately. But that doesn't mean that you cannot plan for your dreams, where you know that you are going to encounter something.
Yes, this is a blip on the plan. The second part is a little more speculative. Somewhere in your algorithm, I'm sure is buried also the region. So in an aircraft,
Are there any ideas for region? Because, again, that's a big part of.
Special type of the color, which is called a integrated system, which is already developed. There's the in such a way that
Right. It should be possible, but I don't know how to calculate the time to that.
So somebody has a good point. Way of asking Professor is, it's not just a question of managing battery, managing the, it is a total system management. And that's what it tries to do. Not the, you cannot redirect directly, but certainly it gives you a direction how we have to do the whole except that. I thought that is the point.
Yes.
Everything in your loops you are saying for SOC as a state. SOC as a state. The SOC you are referring to what?
State of charge.
State of charge is referring to you have charge and
State of charge of the battery.
yeah, state of charge is battery.
State of charge is typically estimated using a dynamic model with voltage and current as measured.
Of the battery.
Something like an extended carbon meter.
Yeah, of the battery voltage.
Yes.
But that battery voltage belongs to the stator voltage SOC of the capacitor.
No, that is why you have the model. So you are doing a state estimation. So you are monitoring voltages of each cells and monitoring the current, and you are feeding it to a state estimate.
But that coordinates to the capacity. What is the ampere hour capacity linked to the battery?
Yes. This is very standard. Correct.
I think we have one part beyond the time dedicated to speaker.
Thank you, sir. Namaskar.
Okay, what I taken it from
Not idea.
that's it is not just only about battery management, it is the life cycle as well as the system level management, and also managing the consumption at the different points of time. That is what is the key takeaway from this talk. Thank you, Professor. We will now move on to the next talk, which is Deputy Director, PCM VSSC. Dr. Coulomb holds his PhD in battery chemistry from IISc Bangalore. He is actively involved in design, development, qualification, and production of energy storage systems, insulation and thermal protection systems, propellants, ceramics, special polymides, and space applications. For space applications, he was honored with the gold medal for the year 2005 by the Astronautical Society and INSAT 4CR Team Award, ISRO 2007. Dr. Ilangovan.
Very good morning to one and all. Thank you, Sir, for your kind introduction. For the Sir, Director NAL, and our Space Guru, Dr. Suresh, Dr. Welsham, and all other distinguished delegates. So let me come to the battery cells for electric aircraft. I'm from VSSC Trivandrum. Let me start with the one tribute my beloved teacher, Professor Satyanarayana, who is from IISc Bangalore, maybe about 30 years back. So without whose guidance and knowledge sharing, I will not be talking much about the batteries. So let me go to the topic. Here overview we will be seeing because several of them are talked, and what specific I will be talking I will get into. So these aspects where we started, how the energy consumption was there, and where we are, the crisis, and how we are now given the chance for solving this crisis. We will see. Yes, now today we are talking about the major energy consumption factors like transport industry, residential, and other gadgets are there. There is a growing demand, but so even if the coal type of or oil type of things are there, we are now constrained to use due to carbon emission. So today our this one will be limited, so the population is increasing and energy consumption goes up. So we will be limiting to our mobility, especially to aircraft. And this is not, though all the people have addressed that the sun god is giving us energy, but we have to store it. The storage medium is the one which we are targeting today, and all the renewable energies are intermittent in nature, seasonal. So we have to have an efficient conversion and storage so that we are able to safeguard ourselves from the global warming, all those aspects. So we know the carbon emission is continuously increasing, at least the slope is coming down presently, and we have government support. And because of, if you are able to stop the petrol or diesel or oil based or carbon emission, if you are able to reduce, definitely this much advantages are there. Pollution aspects can be reduced. So with this introduction, let me straight away go to the energy storage systems. There are variety of energy storage systems, starting from mechanical flywheel, compressed air kind of things. But when it comes to mobility, it is the energy storage systems based on electrical energy, especially battery, fuel cell type of energy storage systems. So now that we, for energy storage purpose, we don't have a very unique solution. But for mobility, if we have to consider, it is the battery based, especially the electric energy based. So that is the topic today, and the aircraft. So why it means, as I was pointing out, the mechanical, like if I have to carry a compressed air or a big energy storage, or even for a mobile, I cannot be carrying a hydrogen cylinder or a flywheel, such things. When it comes to our mobility aspect, it is the form where the chemicals can generate the electrical energy. So now the storage mediums, now what we are talking today, because a lot of algorithms were told, and whatever the EMA or the system structures, materials, all those things are coming. But energy storage, definitely it has to convert this energy when it is storing very efficiently, number one. Number two, it has to deliver in what rate we want. Because today, or the last 2 days, we have been talking about the C rate. Because if a cell can deliver about 100 AH means, we will be requiring the power at the rate of 3C rate or 4C rate. Because of that, there is a limitation with respect to energy, quantity of energy delivered, as well as the cycle life, whether we will be able to meet. So the cost that we are investing to store the energy, we are only portion of the energy will be maybe about 70% or 80%. Otherwise, we'll have to increase the mass in such a way that the cost goes up, mass goes up, life comes down. So how we will be able to make this energy into a power also is today's my topic of address. So now if you look at it, this is the well-known dragon plot, starting from the power is on the left side top, energy on the right side top, the right side, sorry. But when you see the power and energy are always inversely related, that is the problem today we are talking about. If I am able to have the capacitor on the right end or the fuel cell in the top, it is the problem we solve. So now today we are harping on this aspect, because of that only we are here. So let me get into the aspect. Let me start with straight away lithium ion system, which is the highest energy system. Now it is known thanks to the investigators who have brought up last 20-30 years. The energy density has come up to maybe 125 watt-hour per kilogram, or now we are touching 150. Also 200 is being reported, but there is a good scope that we may be touching 300 or 400 with whatever is there. But still, with the energy being coming up, whether we will be in a position to target the power delivery is the main point. So if you know the chemical reactions, I will just touch upon about 30 seconds. There are two chemicals, carbon and the LiMO2 oxide material, which are layered material, wherein if you see the bottom, left bottom curve, there are some layered materials into which lithium ion, direct lithium metal is not there. Lithium ion is inserted. So during charge and discharge, the opposite electrodes will be receiving the lithium ion or delivering the lithium ion. So the energy level of lithium plus, that is lithium ion, is only the difference when it is charged and discharged. So that's why we call it as a rocking chair. So lithium energy is up when it is charged, lithium energy is down when it is discharged. So these are the main aspects. Within the solid, lithium has to diffuse. Within the liquid, lithium has to diffuse. So this is energy portion, how much voltage it is delivering, how much ampere hour it is able to for the given mass. But power is something, if 1 Ah or 50 Ah, if I want, if the battery is able to exhibit about 50 Ah, at an incident, suppose if I draw it at 500 ampere, within 0.1 hour, whether I will be able to deliver is the question today. It is not. So why, what are the causes? how we will be able to overcome that. So, okay, leave upon charge and discharge, the curve difference is there, heat will be there, management of the thermal energy is also will be coming into picture. So these aspects are, some of them are inevitable. So coming to our the technology aspect, because there are other speakers who are dealing with, I changed my, revised my presentation also, because the development aspects I have not gone in. So process wise, where we are with respect to making the cells within the country, so that we have the the technology available with us. If so, cell production and the supply of raw materials, and coming to the manufacturability aspects, because now the cells for our aircraft and for satellites or electric vehicles, if you see, multiple numbers are required, means we don't have an industry. So what are the crippling points? Definitely we don't have the raw materials which are made in India. We are importing still. So process engineering is available. So we'll have to address such things that some other area they will be addressing, but still this is a point to be noted for us to progress in the country. So these are all the few of the chemicals which are responsible, which are actually converted into kind of slurry. The slurry is coated onto aluminum foil or copper foil, depending upon the anode or cathode. So we have mastered. Okay. So for a captive production like our ISRO, we have mastered maybe about 30-40 cells per month. We can make it. We have captive production. But we have developed the technology. We see all these aspects with respect to thickness, because starting the chemicals and making the slurry is chemical engineering. Then making the electrodes is completely mechanical engineering. Testing is full of electrical engineering, and our electronics comes into picture. So these aspects for a captive production for our requirements we have mastered. Technology is available for a small level requirements. So this aspect we could also qualify for our space applications to stacking, winding. All these aspects are available. Hardware generation, and what should be the seal, ceramic metal seal, completely sealed condition. We have come out and we have the technology with us. Some few parties also have taken up, but they have translated in a cost-effective manner for our electric vehicles. So this is with respect to the facilities, the constraints. There are so many constraints are there, starting from very thin electrodes, polymer separator, which is of the order of about 20 microns, mixture of electrolytes, all of them are sensitive to air. And these are all the complications. And these facilities, when we are putting up, yes, operational issues are to be taken into account. So these aspects are there. And these are the challenges which I was putting forth, like the raw material production availability now continuously is still on import only. So at this juncture, what we are planning to do for making implants in the country is one of the aspects. For a long run, it is prepared, sir. And the process engineering, yes, we have a good handle. Manufacturing areas, so like the industries, to make our own equipments for mass production and or import, but we should be able to find the market and then make it in a cheap rate is one of the aspects. This packaging, I think we have a very good control or hold over it. Other electronics as well as translation of the electric energy to a mechanical aspects also we have a good. But with respect to cell, we still have not yet fully matured, I may put it. Yes, engineering aspects and manufacturing, if we have to do what we are planning to do. So is it sufficient if I have the baseline technology alone? Is the point which I want to target, because energy person I will meet, what I will do for the power. So this is success story which we have started from 4 or 5, 50, 100 cells are available. But the problem, I will state the problem now that if you see the left side supercapacitor and the right side, if you see nearly around if about 200 watt per kilogram is there, means, but the energy level has to touch supercapacitor level. So this is the gap which we are finding. What we will be doing for meeting this gap is only my talk. So this is what is the issue. Now 2C rate, 3C rate, even for long run about for the kind of things 4C rate are the issues which we will have to meet for our aircraft requirements. Especially for us, the takeoff and the landing, these are the two aspects which put us on break, because the batteries are, the present day batteries are having clutches with respect to meeting the high rate. So you can see the bottom also, the requirements and what is achieved in the battery area, because the mass will go up otherwise. If we have to operate on a mass basis, these requirements are to be met with. So now when I compare, like in the previous Ravan plot, the gap between the internal combustion engine and the electrical energy seems to be the energy as well as the power. This is the gap which we have to fill it out. So whether advancing, like increasing the energy density alone will solve the issue means I am not able to say yes, because increasing the energy density does not increase the power density. That is what is the issue. Mass I can reduce for the same 100 AH, but the same 100 AH, if I have to increase to 400 ampere for a few seconds or 1 minute or 2 minutes, I will be able to do, but with the cost of loss of energy, heating, cycle life reduce. So these are all the issues which I want to, with the materials or size will come down, but size will come down, but the power will not go up. So what is that I have to do? So now, with the advancement in the energy, we will be able to touch here, but still there is a gap with respect to power. So this I am repeating so that it is getting registered. Now, another issues. Real, if you look at it, if I go through the voltage time curve or voltage versus capacity curve in any battery, rate of discharge, if I look at it, you start with about 0.20, that is C by 5 rate, to nearly about 30 ampere. If I am increasing, that is about 10 C rate. You can see the top curve and the bottom curve, the area that is almost half the energy will I will be getting. So that means there is a reduction in the energy I have to compromise. If you go to temperature also, again the same issue will come. Come to rate of charge, again the number of cycles will be reduced. So all the normal conditions of operations pull down the energy delivery from the battery. So now even the voltage level, if I overcharge or if I am operating at a higher level of voltage to increase the energy, again it will pull down the compromise on the performance of the battery. Whether this is dealable, main thing when we go through our fundamental of battery chemistry, the voltage is whatever operation voltage is pulled down from the open circuit voltage by the resistance. The resistance is originated from electrolyte, cathode, anode, as well as the polarization. That is what is the left curve which we are actually seeing. So this is the one I square R. So R, and I increase the power, it gets increased by the square root, and the resistance is also there inside the cell, and T generates the heat. This heat, whether we will be able to take care. What are the implications of the heat when I look at it? That is what is very responsible. Not only thermal management will completely solve the issue. Thermal management is the interface, whatever is heat coming, that is generated, makes hot spots which reduces the life of the cell. So through the hot spots, in due course of time, dendrites are growing, leading to short circuit path. So any high rate, in addition to heat generation, also pulls down the life of the cell through the dendrite, which is responsible for the failure of the cell or capacity fading of it. So the resistance in the short slowly decreases. So whatever is supposed to be there keeps reducing it. So the capacity fading takes place, as well as sometimes the safety conditions also will be reached. So these are the issues when we do the high power delivery in a normal. So this is what I was explaining. So when an electron has to come out from the material to the terminal, it has to undergo this many steps: charge transfer, diffusion, ionic resistance comes into picture, then the conducting diluent which is coming. So from the atom which is giving out the electron, it has to come to reach the terminal, means it has to go through series of paths. This is the problem. So it becomes, for me, this reduced kinetics is inherent with all our battery chemistry. So now reducing the weight does not increase the kinetics. So this is the major problem. Even in the bottom curve, if you look at it, temperature also is issue. At a particular temperature only, we will be able to do. Else we'll have to increase the mass. Either we can reduce the thickness or increase the quantity. So these are all the compromises which we have to make. Anyway, failure modes, all of us know. I don't want to deal so much. So this is what our future. So this is a real issue which we were talking about. If you see the blue curve where the battery current will be reaching the peak, if I bring in a capacitor where the battery current will be reduced, if you see the blue and the green where the battery current is there in presence of an ultra capacitor, it is reduced to the order of about 50-60%. So now if I bring in a capacitor wherein the power can be stored or the energy can be stored partially from siphon from the battery and it can deliver at a faster rate. So battery is not facing the high rate of discharge and capacitor is able to do that. So now whether it is feasible, yes, capacitor is well known. You know, we have, because of time, but I think it is only 15 minutes, I think. I will complete in 5 minutes. So this is the logic. Capacitor is something like a rabbit. It cannot run fast for longer duration because energy is not there. Ampere second. Battery is one thing which will go long but slow. Ampere hour is there. So now if I combine these two, ampere second, because none of our applications are involving a continuous discharge. It is always a transient requirement. So this transient requirement for short duration, high power in seconds can be met by the capacity portion. And the energy of the battery can continuously recuperating the capacitor. This is what is the idea that we brought. So we started connecting it. So we made the capacitor also. We demonstrated for all our applications of pyroignition in our launch vehicle. So all the ideal curves we could get. So even the cycle life you could get of the order of about lakhs, nearly 7 into 10 power 5 lakhs supercapacitor group, because there are no kind of it is only interfacial charge. There are no materials which are directly involved in making oxidation reduction kind of thing. So cycle life is small. The resistance is not there. So when resistance is not there, I square RT also is reduced very much. So that is what it is that. So now this was the one which came to our mind, like why we should not combine these two internally. You know, externally if I do, voltage differences are there. Battery voltage is different, separate, the capacitor voltage is different. Why we should not internally combine them to call it as a supercapacitor? That is what hybridization in the energy system itself. So if you see battery energy high, kinetics low, and supercapacitor power high, energy low. If I combine these two, I will be able to make both the energy and power high. It is like combining the rapid and the short. Yes, this is how. See, if you see the top blue curve, it is at C/10 bottom 7.5 where we were seeing it. Suppose if I combine these two, if I draw a continuous current of about 0.75 and 7.5 pulse, you can see the curve with how it is lifted up. I am able to utilize the energy. At the same time, transient powers are met by the supercapacitor. So now, anyway, this is explanatory. So this we tested. I think this was our like eye-opening. Our Viju Prasad and team, they were asking for a small capacitor and a small energy. So they offered a actuator. So we could do, if you see, 80% of the transient power is shared by the capacitor, 20% only goes for the battery. So even with the reduced small size 1.58, our C25 actuator we could demonstrate. Thanks to Viju for giving us the chance to demonstrate this one. So with that one only, sir, we went ahead. So we could, even with a small 50Ah cell, we could run a battery car in our campus. So now this again speaks about the how the peak power is reduced by the capacitor. And if you see the right side curve, power is well maintained. Blue one is battery alone, green one with the capacitor. So this is the one which we combine the concept of battery and supercapacitor. So now either capacitor or battery could not serve the purpose. So we combined a new concept with respect to capacitive electrode as well as the battery material. So that energy is not coming down drastically, maybe about compromise about 20% will be there, otherwise we will be losing because of the low depth of discharge. The peak power will not be there. So that we can use it here for adding the capacitor portion. At the same time, even at the fag end, we will be able to get the peak power. That is what is the point. So if you see, look at it, the current nearly even for about nearly 0.7 Ah cell, continuously we could discharge up to 3 volts. We are very 95% of the charge could be fully utilized, continuous pulse. So this was our the impetus which we could overcome. So when we went ahead for a 3Ah supercapacitor, so now I coined the word supercapacitor and battery into supercapacitor, wherein we have the energy, also the peak power, because of the capacitor being inbuilt in the battery itself. So there is no difference because the cathode is there. So then, sir, the 3A also we have gone through all the tests. This is yet another pyrocurrent. This one for SSL will be proved of the order of 50 ampere current we are able to deliver. And even after the first cycle, after 50 cycles we could do. And still, if you see the difference is about only 2 volts. So major capacity portion we could deliver it. So this is again the another PS for our actuator we could demonstrate with the simple 3Ah supercapacitor and all other test requirements, overcharge, over discharge, no safety hazard. All these things could be demonstrated with this one without any safety hazard. But definitely all other issues with respect to management with the whatever battery invokes will be also applicable here. Power portion alone we have come up very high. So nearly about all our 1 minute I will complete. For our small rockets, we would continuously do for nearly about last 2 years. We are only using the supercapacitor, and this is in nutshell. Supercapacitor charge the peak, and battery provides the sustained power. So now that I can confidently say that if I combine these two, capacitor meets the power of the ICE, and energy portion is lifted because of the capacitor. Fine, sir. So this is the story in our management parlance combining the Starbucks and our this one. So now that with that condition, we demonstrated an SR car also in ARA with the simple 25 Ah cell and the capacitor. So battery requirement was reduced, power requirement was improved. This I wanted to say the concern with respect to manufacturability, which we do not have. So definitely indigenization will be the key so that we are able to meet the requirements. So summary is nothing but whatever I was saying, sir, and increasing the power to 500 watt-hour per kilogram, what we were talking about 600 watt-hour per kilogram level, even with the reduced energy density and supercapacitor portion being there as a supercapacitor with the new materials, it will further improve. And this is what I want to say here. And I thank the organizers and especially Gautam sir for bringing me to here to propose this kind of opportunities for the high power without compromise on the energy from the batteries. Thank you, sir.
Thank you. Questions, sir?
Very well with respect to combining and say realization of that.
Thank you.
We see whatever we have done, we have to see because we have got once upon a time. But are we able to keep track with what's happening as we do? See, we are still stuck at 100, 150 whatever per kilogram. Whereas the world has already moved to 400 whatever per kilo. Now, what can be done? I'm really not telling that, okay, not as a BSSC, not as a country, what needs to be done to really catching up with the rest of the world? Otherwise, we will be always lagging. And particularly for the requirement like our HANSA or RTA in terms of aircraft, it's going to the battery capacity. Column of energy, management, transit, all that is, we can always do that. The real problem I think is what countries should do, keep track or keep developing. There should be development, there should be production. Both are gaps in my view. What can?
Sir, again, I did not go back to that. So I was mentioning about in institute industry anticipative approach. What line I
It's a very
get?
general word. I mean, we have been talking about this for
Sir,
years.
we are now bogged down by the raw materials. Otherwise, whatever 400 is coming, is all of them are having a institute to give them the raw materials.
It's not you only. I'm not, see, get my point. See, today, if you go west, the Nurses Foundation, the Nurses Foundation spends billions of dollars per year only for the development of the energy, batteries, supercapacitors, and all the related things of in the fuel cell. Are we having sufficient research manpower? Some of the institutions conventionally do their like Karakuri lab and all that. They have not produced anything in their life. What can be done in terms of institutional mechanism? Give a thought. We would like to really hear somewhere from you so that we can really make a difference in Expo 5 years.
Yes,
Just give a thought to it.
Sure.
I'll be like to listen to it.
we will discuss, and as you have given us the assignment for our solid state, no? You
Drawing back idea.
Yeah, drawing back. So we have come up, sir, and we will be meeting that promise.
No, I'm not talking only large vehicles, is for road. I'm talking in the country.
Country.
So just give a thought.
Country we will discuss, sir. You know very well. So we will discuss, and I will put my points about improving and meeting this big gap.
Because you have dealt a lot with the industry also, so your views will be very useful.
Who has taken over the production now? So the Gadkari and all that. Who has taken over the production?
So the production of the product companies have taken on technology. And then one Untitled Batteries, either 6 companies have taken over.
And they seeded?
They were 2-3 come out with prototypes. And then we are there. Sir, Amara?
No, come out with their
Amara also has come out with the small cell, and Tata Chemicals also. So they have to translate our space technology. So science will be said, sir.
And they made some modification in terms of cost production.
Yes. So it will be like one house, sir. Where the cell is steel. These things need not be there. Mass space and otherwise also like the material what we are using for space.
You have an idea how does it compare in cost? Vis-a-vis our cost.
Okay, so that I am not. I will come back.
Thank you.
This pouch technology,
Sir,
I thought it is more beneficial for packaging. Because normally we use about 25% from cell to packaging. But if you use pouch, it is coming down to only 12%. But I'm not saying that for Coulomb. Is there an issue or there was no requirement?
so for space, there is an issue because the fact whatever we are doing, maybe after a few years, 5 years, we can start. Because notice only keep sealing the airplane. But when it comes to like 20 years of life or our communication, like we are making completely welded, where aluminum comes, the ceramic metal steel comes, etc. So that's why we are not
So it will sell back when I talked to friends in university. There are something like 28%. But recently seen, it has come down to 12%. I thought this is something we can sell people and the packing people to do that.
yes, maybe our
That's why I'm making this very.
So we are very conservative in terms of.
No, but I think
Not only that, in spacecraft, the thermal management is mainly through radiation. So that puts a big overhead on how to conduct the heat from the source to the place where it can be radiated out. That is the reason the mass will go up in space batteries, whereas which is not the requirement in on ground where convective cooling is there. We can so the mass requirement for terrestrial use, the cell to battery ratio, the mass will not be so high as space batteries. Okay, any other questions? One more question. Okay. Okay.
Thank you, sir.
Dr. Ilangovan, who is an expert in the energy systems, has talked about the lithium-ion cell manufacturing challenges, the issue of the energy versus power delivery, and optimization of the utilization in terms of both energy and power, so that the requirement of the application can be met. And he also brought out this capacitor plus battery together for taking care of transient increasing the battery capacity. Let us thank the speaker. The next talk is on battery packaging, characterization and management systems by Shri S. Ananda from the URO Satellite Center. Shri Ananda is presently heading the battery division in the power system group of URSC. He has designed balancing electronics and batteries for various spacecraft. He has been project manager, deputy project director for several GEO, LEO and interplanetary missions. He has published over 13 conference and journal papers. Mr. Ananda.
Namaste to all. Thanks to the chair and the organizers and the veteran in front of the dais. I'll be trying to cover the battery and BMS aspects and try to touch upon electrical aircraft as well. Correct. Some of the aspects which I will be touching are listed here. Going forward, we know lithium-ion battery is a group of cells which can be combined in various ways. Series parallel configuration is one. Then parallel series configuration is a possibility, and hybrid of these two is another possibility. And we know lithium-ion batteries are energy dense, but to have some of the safety-related issues. So battery management system is an very essential aspect, which provides both the safety with respect to overcharge and overdischarge, and also charge equalization. So BMS is essential is what is understanding. Coming to the cell selection, Dr. Coulomb presented various options of the cells. As far as the electric aircraft is considered, obviously we have to go for the rechargeable cell or the secondary cell. And then looking at Hansa MG, the profile, it looks like energy dense cell is sufficient to meet the requirements. There are various flavors or chemistries of lithium ion. Which one to choose? There are trade-offs. Namely, safety versus energy density could be one, and then degradation could be another. Degradation, when we say, we'll be talking about the storage degradation or calendar level degradation and cycling degradation or charge and discharge degradation that happens. Those aspects will have to be considered. Then obviously cost is a factor. We also will have to keep in mind the cell we select has good performance at different temperatures. If you look at standards like 0311 for aircraft batteries, we see that -40 to +70 is the temperature range. Whereas the spacecraft battery that we work on between 0 to 30. So temperature performance is an important aspect when we transition from spacecraft design to the aircraft battery design. And also, external will discuss the rate capability. The charge current and discharge current capabilities are important. And touch upon with respect to energy, whether it is affecting anything with respect to battery sizing. Decommissioning and life cycle are tightly coupled. Life cycling studies are a must, either by the manufacturer or at our end, the user end. We need to carry out to make sure and ascertain that the reliability cell number of cycles is possible. There might be other restrictions like ITER in some cases, and also availability will also be a driving factor. Going further, the next step will be battery sizing. When we say battery sizing, we need to decide electrically what battery meets the various aspects of load output. Voltage requirement for one, then there are discharge requirements, which will be load and duration of the inputs in that. There can be charging requirements. There are cases, yesterday was discussed, whereas if it is only 1 minute or 2 minutes are sufficient to fill the tank, but battery we are seeing that it takes overnight. There are cases permanent charging kind of cells are available, but the reliability is yet to be proven. So charging requirements is also a requirement. Then requirement, high and then low temperatures will have effect on the rate capability, namely the charge and discharge current that can be supported by the cell overconnected. And also the equipment capacity can come down with respect to temperature. So give you an example. If we get at about 100% of capacity at ambient at minus 0 degrees or minus 10, we will get about only 70% of the capacity that it can deliver at ambient. But then what about high temperature? Kinetics can be high, but then at about 60 degrees, we may get only 90% of the capacity because of the other aspects, the thermal management aspects. So the impact of various aspects, namely voltage requirements, will decide cells in series, and your discharge requirements directly feed into what are the number of cells in parallel. So it also will give you a capacity. The other requirements, namely charging and temperature, will have impact on cell type and additional capacity requirement also might come up. So here we look at the case of Hansa FG as one of the case studies, and we have some of the cells that we could get upon with some of the data that is available online. As we got some data sheet, yesterday also Amprius cell was proposed by Dr. Pankaj, where he was talking about 360 to 370 watt per kg at the cell level. Apart from that, we have also looked at an aircraft set that we are developing for other applications, the LCA and then Hansa, not the electrical version, the regular version that is being developed by Dr. Edangor and team at BSSC. And there, after all the deliberations, we have decided lithium ferrophosphate with graphite chemistry is more safer than the standard NCA, nickel cobalt aluminum oxide chemistry that we are using in spacecraft, or even LCO, lithium oxide chemistry that is being used in space. The decision there has been to move towards LFP and graphite. In the next subsequent slide, I will discuss about the trade-off and the thermal aspect, but continuing further in this slide, I just wanted to make the case study with three different cells. Though they are not one-to-one with respect to energy density, just to give the perspective of how it impacts various aspects of series cells, parallel cells, and then mass. That's what I was trying to highlight in this. And also, we have in our table one of the quad cells of 3.5H, which is nickel cobalt manganese oxide with graphite anode cell. So these three examples we do. Then the rated watt per kg of cell is mentioned here. The maximum cell voltage is also different for these cells. So then we have resulted in the number of cells in series being different for all three cases. For 50 volts maximum for the which we are talking about. So further, we get considering 80% DOD. This is also one of the points which I may have to understand better. Generally, when we look at live versus the DOD, there is a kind of inverse proportionality. To put some numbers, if we are looking at 100% DOD cycle, any data set will mention about 300 cycles that can be supported for 100% DOD. If we look at say 60% DOD, we might be able to get about 3,000 cycles. If we go to 20% DOD, 30,000 cycles will be feasible. That is what is our experience with various cells we have used. This 80% DOD comes from the aircraft standards, namely 2311 and something like that. But then the batteries are secondary or standby sources. They are not being continuously used, and probably they might be used only once in its lifetime in one particular case, or just for engine starting unless there is a failure. Continuous usage fully on the battery. So this 80%, whether it is feasible, is a study which we will have to take up. For this particular table, I have gone ahead with 80% DOD to get the numbers. So total number of cells with 80% DOD in picture and number of cells in series being decided now are about 4,000 of that order for 3.5H cells, whereas for 10H cell, which is actually safer but low energy dense, about 1,755 cells would be required. The cell weight alone, if we consider, cell weight alone I am talking about, no structural mass and other things, we have 206 kgs resulting from the cell weight of Amprius, the example cell of 360 watt-hour per kg. Then LFP cell is giving us 495 kgs of cell weight itself. And the other one is 216 kgs for NCM with graphite. BMS we are still working on, so I am not included for the battery weight here. And as sir was mentioning, Dr. Kota, we have taken about 1.35, which we have been able to realize for the spacecraft battery in this particular table, which we are trying to improve upon. For the present, the numbers actually translates to about 230 watt per kg for the Amprius cell that seems to be the best in right now available in the commercial space. For the safer cell, it is only 97 watt per kg. For the other cell of NCM, it is 222 watt per kg. The other aspect which I would want to throw a light upon is safety versus weight. It looks like thermal runaway or the thermal management is an important aspect which we will have to test and prove for the cell that we are choosing. And in the literature, some papers are available which actually says that more the energy density, there are more chance of thermal runaway. It looks like we can't have the cake and eat it too, at least at the present state of the art scenario. Example is available not for LCO with nanosilicon, which is the ampere cell, but for a different LCO NMC with graphite cell is available, and also NMC and LFP, which I had given in the previous table. It looks like LCO will have a start of thermal runaway at a lower temperature of 150 degrees itself, but then it will reach much higher temperature of 700 degrees C. About the pouch cell, I am not fully aware whether there are SS based pouches. Aluminium will be ruled out, aluminum pouch will be ruled out when we say that 700 degrees is a possibility of thermal runaway. Because aluminum we have about 670 degrees is the melting point of the aluminum. So safety aspect is one of the things. If certainly we have to use amperes, though the case material I have to find out it, we may have to do some jacketing of SS for the cell. That may not be optimum because the mass it will take it to the higher value. Or we may have to have the modules. Actually, in the previous table, I showed some of the possible module configurations. The modules could be housed in SS, but then there will be mass penalty. But the safety will enormously improve because SS is a safer material with respect to thermal runaway. These are the studies which we have to do for this particular case of electrical aircraft. And then other things what we have to plan actually to optimize. We have some of the things available. I'll just throw upon. These are actually studies in progress which we have to do for the electrical aircraft. We have to test all the cells which we consider. Then we have to do the arrangement of the cells for the specific location. That is to get the optimum capacity out of the battery that we are making. Presently, linear sorting is widely used in the industry. Cell sorting machines are available where the cell parameters are taken. One parameter, the prime parameter, probably capacity is taken, and then in ascending order it will be put. Cell arrangement will be reached. We have also come upon, we have only developed in-house a genetic algorithm based improved cell sorting, which also is published, which is able to give more number of cells that can be put into battery out of the tested cells. So that way we are going to get advantage with respect to cost. That's what I want to highlight here. Just in an example, what is shown for about 1,000 cells that we tested, 94 strings only could be made when we went for linear sorting. When we used genetic algorithm, we were able to meet, rather, we were able to get 96 strings, meeting all the specifications. In fact, for majority of the parameters, we had a closer match with genetic algorithm. Coming to packaging, three different aspects dominate. Of course, optimization of cell to battery ratio is tantamount. The electrical aspects will have bus bars, wires, connectors, and insulation. We saw that the battery is going to be quite good, big, and then there are a lot of modules. Once the modules are in picture, the connectors and then the number of connectors will go up. So we will have to think of different ways to connect, maybe by bus bars and then some kind of fastening, not compromising the safety. Then a fuse wire kind of linkages could be possible. These are the things which we are working on, but we have to finalize it. But then those are the aspects which will contribute to the mass. Mechanical aspects are very well known to all of us. Of course, the cells and accessories has to be housed, where housing has to meet stiffness, post-static load requirement, and vibration requirements. Thermal parts have to be catered to when we do thermal modeling, and thermal aspects have to be addressed. So finally, it is optimizing of the cell to battery ratio. Material also, Dr. Kota was also suggesting, sir has suggested to look at the composites. We have used the composites for very small cells of INS class of batteries. Presently, we have not actually looked at a bigger battery to use the composite materials mainly because of thermal management. We'll be studying and trying to improve upon the cell to battery ratio. And battery pack making, there are many processes like we have to have cell tabs, and tabs have to be welded, cells to be bonded, and then there are requirements to connect the electrical accessories. For the pouch cell, the processes are being studied. It is new to us. We are working on those aspects. And okay, these are some of the publications on fabrication and then thermal aspects from our URC. Of course, testing as of now, we are thinking that test as you use is the main philosophy. Electrical testing, we want to actually do life cycling test, though some data is available, like 400 cycles are possible at 100% DOD for the ampere cell that is available from the data sheet. But then not stopping at that to decide on the DODs and then degradation numbers, we have to go ahead with accelerated, semi-accelerated, and real-time testing once we get hold of the cells. That is to establish the quality of the cell. But for the battery and the cell itself, to characterize and then make it into battery, we have to look at capacity testing, self-discharge characterization, insulation resistance, and bonding resistance measurement. Insulation and bonding resistance measurements are very important for the battery aspect. Mechanical tests also will have to be done, and thermal checks we will have to do. Failure tests, even the space standards which are from JSC, as well as NASA also talk about failure tests being repeated at the user side to get the confidence. Due to relevance for the air traps elaborates a lot of failure tests that we are already actually started for Gaganyaan, and then we are at some stage for the cell where we have confidence to use for our Gaganyaan battery. For the battery cell that we choose for aircraft also, we have to take it through all these tests. Modeling the performance is very important. State of charge, state of health, and remaining useful life are important aspects. In literature, a lot of model-free approaches and equivalent circuit models are available. But UNSC has mastered genetic algorithm-based generic estimation model. Actually, there was a question during the previous talk about how to make a simplified model. I feel there is a solution available. This genetic algorithm-driven genetic estimation model, what we have done is, we have taken the lookup tables as the baseline, and then we have provided the multipliers for the capacity and resistors. In genetic algorithm, it is an offline model, it is calculating those parameters. What I think is the basic lookup table we can take up, but then monthly ones or 6 months ones, depending on our experience, we can update the multiplication factors for the resistance as well as the capacity realizable. With that, there might be a practical way to approach the model on board. The real-time model is a possibility, is what I think. We'll work on that. BMS in satellite, as all of us are available, we have a distributed battery management system where the controller actually is sitting in the controller is actually doing much more management than just the battery alone. So a combined centralized BMS we are working on for the actual other LC and Saras related aircraft batteries, which will have to take it forward further to make sure it fits into electrical aircraft as well. As we have understood with the studies with the other teams, we know that current temperature voltages have been monitored and heaters are required for raising the temperature. Here I'll just tell one or two sentences. It looks like the ampere cell can work from -20, but the standard says -40. Elsewhere also, these kind of challenges have been there. -30-degree operating cell is available, but -40 it can operate not delivering the performance. In such scenarios, we can use the heaters at a low rate. The performance may not be the best, but then it can self-heat. Once it reaches a temperature which is comfortable, then more benefit with respect to performance is possible. Such papers exist, and we have also worked on the numbers that will be required for heaters. For the other case, namely LCA, we'll work on this and then we'll come out with a strategy how to heat so that at low current we are able to come to the required temperature and get the better performance. All other aspects are generic. Standards, sir was also mentioning yesterday that for electric aircraft there are no standards existing. We have been dealing with the NASA standard for lithium-ion batteries for space, and crew safety related we are following JSC standards. Of course, there are safety standards from Underwriters Laboratory 1642, which we have already testing some of the cells on those standards. Of course, the aircraft standards are different, which are also available. So we have to work also with respect to standard related aspects before we finalize and certify the battery for use in spacecraft battery. With this, I conclude. It looks like battery mass is at upwards 280 kg for ANSA NG. Cell sorting and selection we are equipped with, and we have to attempt once the cells are available. Battery packaging for pouch cells and safety aspects we will have to address. Modeling and analysis, what algorithm we have with cell characterization we will be able to use is the present first cut understanding. BMS, we have to work out with the team for getting better inputs, and then we'll try to finalize a standard, and we need to define. With this, I'll come to the end of my talk. Thanks for.
Thank you, Dr. Ananda. We spoke about the battery assembly trade-offs, including the manufacturing, testing, the battery management system, and standards. More practical aspects of these things were brought out. The main thing what we find is that it is a safety versus the performance. That is what is the key driver in where humans are involved, and that's what he has also brought out. There are any one or two questions we can.
What will be the reduction it will come if you dilute them properly and not
Just started working on 2.7. Actually, the densities we are looking at 2.7 versus 1.8 look to be the composite to aluminum ratio, where the composite can have thermal conductivity, where there is a filler material.
we can do that before we can introduce that. Like if you have a good connect.
That we will
I have to do that. That's not the way to build an assembly very quick because the investment is very low, very heavy. But thinking of drive finishing my problem. Right? Good lessons. So, as a engineer, you should make sure that you never and test the reality. To assume that you cannot change that law. And you make sure that you never get into the other way. So don't worry about it, don't invest. I somehow feel that way. Second thing is standards. See, if you find aircraft investors good luck. If you do not have, I think we must be able to write equivalent within power group or within our university. You should be able to write a sooner and give it to, let's say, again, this you get approved by whatever document. You should have your conviction in writing our own standard. They are not available. They are available, where you copy them.
Sir, I'll add a point here. Actually, we are testing one cell at UL laboratory recently. We are doing highlight. We have seen that the cell itself seems to be sturdy for thermal runaway. Though we introduced the external heat, thermal runaway can happen by external heating due to finance. We introduced external heat, and there the cell did not disintegrate as we expected. But we are working on it. We are working on module level, which we will be testing. So there are encouraging results also available.
Design to make sure that you never get into this type of problem.
Sir, sir, you wanted to ask a question.
New specification, because I think stands for ultralight specification.
Ultralight is something.
This refers to microlight aircraft, which are, for example, the crystal ultralight. Those batteries are made by new specification.
Even actually has the implications for transport of the EMN battery. For ultralight, is correct. In this case, the UL laboratory basically deals with standards, namely for battery as well as safety tests. Ultralight laboratory.
Their battery has clear for fuel. Ultralight or it is whatever it is not a it is not as per the each of them. It is pure involvement and we have to add a discussion for man aircraft it has to be safe and if we have to go for other things some civil environmental they have to do that
I think good thing. Cell to cell management. That's what that. If these are well done, that's the challenge.
The main problem, sir, the main problem is the abuse condition. When an accident happens, when a damage happens, battery should not catch fire. That is where this problem comes. Where when a vehicle meets with an accident, it should not result in a fire. That either you take care of by the chemistry, which is the LFP, or you take care of by very robust packaging, which is the steel. Both are inefficient in terms of mass. This is between the hard and a hard place and rock. That's all we have.
It is overall. If it is overall, it can't take up.
That is why, as you sir rightly said, FAR should only LF. Manage the passenger air. That's not the.
If the NCM or NCA or LCO, even though they give 200 or close to 200 whatever per kg, to make it pass the regulatory tests, you have to add so much mass at the battery level, it is going to become equal to LFP. That is what is the assessment as of today.
That's where you have also air. You can also put liquid. Possible. You can't do it in a set time. So you have there are ways, but
We can find ways whereby we can still meet the requirement and make it light. I think that is the challenge.
I think it's a very interesting and thought-provoking area of work. I think we are losing time on this. We'll stop at this point, break for tea, and maybe join back after 15 minutes. Thank you.
Sir, I have an announcement for NAL participants. Please collect your lunch coupons from there. We reassemble after 10 minutes.
Along can go for first day.
We'll run one. Yes, so please. Freeze ಮಾಡಿ ಇದನ್ನ ಫ್ರೀಸ್ ಮಾಡಿ ಡಿಸ್ಪ್ಲೇ ಬೇಡ ಸ್ಕ್ರೀನ್ ಫ್ರೀಸ್ ಮಾಡಿ ಸ್ಕ್ರೀನ್ ಫ್ರೀಸ್ ಮಾಡಿ ಆಫ್ ಮಾಡಿದ್ದಾರೆ that is also by it did not take more technical ಸರಿ ಇಲ್ಲೇ ಆಪರೇಟ್ ಟೈಪ್ ಮಾಡಿಸ್ತೀನಿ this one on the screen.
Good. Hello. Hello.
Specific character. Yeah. ಅದು ನೆಕ್ಸ್ಟ್ ಮಾಡ್ಕೊಳ್ತಾರೆ ಈ ಲಿಂಕ್ಸ್ ಮಾಡಿ
removing that video 9 MB file. That you would have saved that video. लेकिन वो इफेक्ट वगैरह सब है उसमें, वो एनिमेशन इफेक्ट्स वो सब है, टाइमर भी है, लेकिन पीपीटी नहीं मींस एनिमेशन what is now doing, that's what that thing appearing. Yes, that is doing it with the clip. There it is automatic. They teams and online.
Hello, sir. Hello. Good morning. Am I audible?
Online is there.
Hello.
Yes, sir, you are audible.
Okay, perfect. And for sharing, should I share the screen or you will present it?
Sir, we will share.
Okay. So Pankaj, I sent an email.
One sec, Pankaj will tell.
Sir, we will share the screen. You just do the talking and you say next. Okay.
Okay, fine.
Okay. Only point light man. Off But ಇಲ್ಲೇ ಇರ್ತಾರೆ ಇಲ್ಲೇ stand here.
here.
Color mic ಬೇಡ ಆಫ್ ಮಾಡಿ
ಇಲ್ಲಿ ಮ್ಯೂಟ್ ಮಾಡಿರ್ತೀರಾ?
ಹೌದಾ otherwise echo will one hour protect. Amar. ಇಲ್ಲ ಐತೆ ನನ್ನ ಹತ್ರ ಇತ್ತು ಕೊಟ್ಟೆ ಅದೇ ಅವ್ರವ್ರಿಗೆ ಹೇಳ್ತೀನಿ ಅಂತ ಹೇಳಿದ್ದಾರೆ ನೀವು ಬೇಕಾದ್ರೆ ಇನ್ನೊಂದು ಎರಡು ಕೊಡೋದ್ರಿಂದ ಕೊಟ್ಬಿಡಿ ಅವ್ರವ್ರಿಗೆ ಹೇಳ್ತೀನಿ ಅಂತ ಇಲ್ಲ ಇನ್ನೊಂದೆರಡು ನಿಮ್ ಕಲೀಗ್ಸ್ ಕೊಡಕ್ಕೆ ಅಂತ Sir, kind attention, sir. Sir, kind attention. We'll resume the session. So I kindly request Chairman sir to.
Welcome back. Mic is on, doesn't seem to be on.
It is answered. Yes, sir.
Okay, welcome back. We'll continue with the session. The next presentation is also on the battery packaging and management systems. The presenter is Dr. C.M. Ananda, Chief Scientist and Head of Aerospace Electronics and Systems Division of NAL. His research interest includes integrated modular avionics, architecture and systems, certification of complex electronics hardware, and DO-254 process, microelectronics payload for MAVs, safety and flight critical hardware and software, embedded and VLSI technologies. He was awarded with the NAL Technology Shield Award. He has several SCI publications to his credit. Dr. C.M. Ananda.
Thank you, sir. Thanks for introduction. Respected executives, ladies and gentlemen. So there's a small correction in the title. So mine is not packaging, it's an application of lithium technology, civil aircraft. But say engineering rocket to design the factory. So I'll talk about more on applicability of the regulation standards for civil aircraft. And as a test case, we have gone ahead integration of lithium battery in our own aircraft, two-seater Hansa. And we have gone through the complete life cycle of regulations, DGCA and things like that. I'd like to bring up that aspect. Also, I talk about the BMS requirements as applicable to civil aircraft requirements, especially for passengers. So, if we look at the requirements per se, before we get into the details, the top line requirements are the FAR regulations. Today, FAR regulation does not talk about specifically on the use of lithium batteries in aircraft. But however, there is an integrated or implicit guidelines with respect to 23, 25, and operational requirements and so on. It doesn't give specific to that, but subsequently will come. So if we just take a quick look at it, end of the day, apart from the 23 or 25 dot para numbers, which talks about in general, they talk about the 30311, if you see on the slide here, for rechargeable lithium batteries as a guideline, lead to the further act. And also, most important, as elsewhere in the world also, there is a special conditions paper, technical paper or CSIR-NAL, because issue paper is required to be generated for adopting the lithium battery and its compliances towards it. There are advisory circulars towards that, and I brief about. So most important towards that, there are MOPS requirements and the testing requirements associated with the FAR as a separate. Then coming to the others, the special test cases, we already talked about in the past, yesterday and today, a lot of discussion happened on the standards. Apart from the DO 160, which is applicable in civil for environmental coverage, the DO 311 specially released for the testing of lithium cell and the battery as a whole for use of such batteries in civil aircraft. So very, very special requirement has come in. Apart from that, the other standards of packaging, transportability have been looked at. I just quickly get you through. DO 311 and DO 160 more or less comes together, but the tests are quite unique. DO 311 talks about cell and its details, which we'll see. DO 160 is very generically a package as a system or an LR. But FAA's advisory is to have DO 311 as a primary means of compliance for lithium battery in aircraft. Also, also, if you look at there are UN standards for altitude simulation, thermal test, also it is part of it, it is there that, and added with IEC safety standards 61 all put together makes a means of compliance with respect to battery. But if you little get into more details on DO test, and I would like to compare, bring in 160 together. So 160 and DO if you look at it, DO talks about more on the cell, its capability, protection features, and the battery as a whole, the thermal runner containment, etc. There are 20 well-defined tests which has to be complied as a requirement, and that doesn't mean that DO160 is not applicable. As a whole system, it has to qualify to D160 also. But if we look at, is this enough for a battery, lithium battery to be put on aircraft? Certainly not. It requires an operational requirements also and the implementation as far as the system is concerned. What are those? So the lithium battery pack or a battery consists of not only cell and this, but a very critical battery management system. Battery management system is quite intelligent and an embedded control system which has definitely either a hardware, either software or a complex hardware as means of implementing the algorithm for battery management. So if we get into the if we try to implement it using a software, a microcontroller and a software, the D178 attracts, and there are ways of implementing using the hardware programmable device. So D254 comes into effect. So it's a choice of using the controller, and by practice we have been discussing in the committee forum also with UNSA also in ISRO where we are looking at the batteries for civil aircraft and military. The use of microcontroller would be the right choice because the process point of view is much simpler and the effort is much less in terms of game. And also the expertise available as plays a very important role. And also if you look at the process, I mean just for completeness I'm bringing it, I'm sure all of us are aware of this. The complete process of DO in terms of hardware, complex electronics, software are built into a well-defined process called hardware and software process. I will just try to get in this, which you are aware. So the DO254 process and DO178 process comes parallel in handling. Either we use the complex electronics or a simplex electronics, but still we need to follow at an abstract level. And when it comes to a system as a battery as a system, hardware and software to be contained to this DO process input. When we talk about the DCA requirement, particularly the civil aircraft, this process is what is being requested and demanded. And each stage of this has defined or well defined, and the DO process is there is no ambiguity in the documentation which is required to qualify and certify this. It's all in place. And to tell the audience here that the complete DO process has been well established at NL for various flight programs up to the design assurance level, both in terms of hardware, software, and the computer. So more important thing is that, yes, I'd like to mention that the NL has been one of the first organizations to implement the complete process of automated DO254 implementation, apart from DO7, which we had from last more than 2 decades. We have designed and developed the complete what we call the accurate IP, following the complete process of DO254. The idea was not to get an IP developed at NL certified. The idea was to establish the DO254 process in the country without going for any optimization, any waivers from Similac. So that's one thing that very, very critical, and we have the full-fledged process in place, documentation formats. In fact, I have to tell that the typical process checklists and the review formats has been sold by FAA in the hundreds and thousands of dollars. So in fact, we asked last time it came up to 1 million. So in the process of establishing this, we along with Similac derived the checklist format, derived the review process, and derived the complete artifact at every stage of this process, and the NL is full-fledged as an. So this we have in place, and to talk about how this can be applied to BMS, certainly the complete know-how NL has in this. Apart from this, as I said, there are a lot of advisories. FAA has many concepts of advisory circulars. This 20-184 is one of them, which provides a good means of understanding towards this, and 20-04 also in general. But all put together, the 20-184 talks about the in general, the process, acceptance, how requirements, safety assessment. Even though ARP standard talks about it, this is in specific more towards this battery requirement. And if you see 3.1 to 3.3, it talks about more of aircraft battery, maintenance, replacement, and so on. Apart from this, if you look at the complete, at the end of the day, I'd like to mention, even though we have set of guidance, guidelines, in some cases standards, but again, we all know that the electric aircraft today, there are no standards, very specific. But definitely, I think with the combination of all of them and the expertise that India has in many agencies, particularly we have a lot of technology, we can, as proposed earlier, I think it's very, very important that we should collate all of them, generate our own standards. So we are not well on that. Aircraft, civil aircraft technology, LFP is more critical, and we talked about it. I'll now get into the typical battery management, because this is the course. We have today, I think I had mentioned, we have battery management system modules available for right from 500 rupees up to lakhs of rupees. But one can ask, what is the difference? Certainly, yes, every cell that we use in commercial use, that comes with its own battery management, a small chip. But what is the difference? We'll talk about. When we talk about aircraft requirements, certainly the battery, there is an electronics controller which is required to do minimum mandate functions to fulfill the requirements of the aircraft, typically in terms of cell monitoring of voltage, the temperatures, and of course the package, current, and voltage. But apart from this, there is its own additional sensors also integrate. But most important is using this data, estimation of some of the health parameters, and the fault diagnostics is much more, and fault isolation is built into that. And we have more important, like today in aircraft, what are we going to do with the battery? If you talk about the traditional NACAD or any other battery today, there is no much communication of the health of the battery to the cockpit or to various subsystems who manages the power. Today, I just know that the temperature of battery, and typically I'm talking about the gear load battery. I'm sure that's a technology we have, but on aircraft. So we require a lot of information from the battery to various applications. Not for main electrical system, but of course for many other management we require. So there is a special requirement we protect for aircraft application. The status, annunciation, caution, and warning are mandatorily required to be provided to cockpit as awareness to pilot, awareness to interface system, especially when it comes to lithium battery. And certainly it should have charge, discharge, and the required control mechanism. Hot locking is one of the critical ones, and various interface. Now, there has been a lot of debate on what is the standard interface the BMS should provide or is required in aircraft. As of today, there is no such standard. But typically, what industry follows, if you look at those who are already flying with lithium batteries, they are primarily on the ARINC 429 or ARINC 825, which is the CAN interface. These are the two popular interfaces today. Battery management system worldwide people are flying. But of course, there is no restriction of not using any other standard. We can adopt it. And that way, so 429, 825 all the standardized interfaces today. Certainly, if I use a microcontroller, a software programmable device, DO also it will be adopted. But I think there has been a lot of debate on what should be the design assurance levels of this software in the market. Many cases, yes, because it is a critical. the way I use the battery in aircraft and the way I define the scope of the battery in terms of emergency, what is the application and so on, the DAN levels can definitely go up to level 8, the highest is here. But if I have the analysis, the analysis that you can see for different applications, comes lower, we can lower it. But always, when it is critical application, it is design assurance level. So as I mentioned that there are designs today, combination of hardware and complex electronics, typically a hardware is programmable device, either PLD or FPGA, and it is advisable not to have combination of it, even though this is a very simple controller which can be realized using the very low end or a mid-range microcontroller. Then this is associated with redundancy. In some cases, yes, I need to have the hardware level redundancy to ensure that I get the required value rates and associated with its own vending mechanism and a package. So typically at a very high level, this is the composition. But how do I use this on aircraft? If you look at it, see, as a whole, this is the package that I have, and when I get a qualified or certifiable box as a battery, that has to be integrated with my electrical system. First and foremost, the aircraft electrical system primarily is integrated by default in the battery system. And as I described, most important to my cockpit for both for pilot information and also for various regulatory system management and synoptic requirements, the diagnostics and prognostic requirements, definitely this is mandatory. And today, every battery that we integrate an aircraft has more than at least 10 to 15 parameters, minimum mandate, which are required to be logged to be managed. Of course, there are many more. Just in brief, that I'd like to cover on what is the activity. As I said earlier, we are not in the cell or the battery development, but we are user of that. I'd like to mention what we are. So typically, if you look at any of the aircraft requirements, the battery requirement comes in with endurance, emergency use, what should be there, typically is 30, sorry, 30 is that 60 minutes for safe landing and requirement. So the battery sizing depends on that, and I have to give sufficient derating and so on. So looking at that, and just give a brief, that there are 3 aircraft that I'm going to compare. One 2-seater on the leftmost, and we have 19-seater current program. And I'd like to bring on the hats also by the platform. Typically, if you look at the answer requirements, the Coulomb requirement is very minimal capacity. But if you look at the existing, what has been earlier and what is it? All of us know that there is a big saving in the power, range, and definitely the interfaces are much simpler and it is more interactive with the cockpit. So this battery has been integrated with the center system. So our battery, lithium battery comes with as a pack itself, battery pack, but in many cases it comes with a enclosure, metal enclosure for hazardous condition protection. So typically it comes with that and a welding mechanism. Some cases it is simple, many cases it is complex also, but these are the minimum requirements. So if you look at what are the challenges that we have faced integrating onto answer, first and foremost, when we started looking at lithium battery for an aircraft, that is the time we had worldwide panic on use of lithium battery. So a lot of questions asked why and how do we clear, and even including the design as well as search agencies. So first and foremost, we had to convince those levels. Then we went into the requirement standards as well. As of today, there are no standards much specified, particularly for 2-seater aircraft, it is generally or CSIR recall. There are no specific mentions. That is one of the challenges. Again, is that if you go to search and say to what compliance I should cover. So then we looked at the design requirements, then we formed our own standards. We call it as special conditions. So we worked with DGCA, and DGCA took a special interest in creating one issue paper for us, and for us it's not specific for NL, for use of lithium battery in this category of aircraft. So that is one of the very good activity done while integrating. So now today, India has placed a reference of integrating lithium battery on this category of aircraft. We did that, and further we went into the implementation part of it. We did lot of ground tests. As I told, there was a panic of using even. I remember the first connecting and starting an engine was a major event in ANSWER. So we did that with the certification agencies in the loop, and it was quite successful. Subsequently, we integrated our aircraft. We did lot of ground tests, EGRs, and performance evaluation in terms of charge, discharge requirements, endurance, and so on. And subsequently, we could get this battery, and finally we could get the state clearances without any major problem. Certainly, I think there has been a big event in that. And we got a special certification review item created for use across the country. And as part of it, the special conditions also looked at what are other standards in the world, in the industry they follow, DO 311 or any of the MOPS requirements. Everything they brought out and said there are 8 or 10 special conditions derived and told that NL should meet or comply with, which we successfully integrated all of them, complied through the means of DO 311 documentation available. So our own implementation on aircraft and various tests that we did on aircraft and ground and your bench level tests, lot of evaluations were done. So these are some of the tests which were done, and ultimately that yes. Now we went ahead with the design of it. First design was done, approved by DGCA. We did the bench level test, doing very minimal and mandatory requirements and safety. And so then we went into the engine testing, where the first time the engine was tried with the lithium battery. Then with that success, we went into the aircraft integration, flight, and data. So we found that the voltage requirement was much lower. All of us know that the lithium battery has good advantage in terms of holding the capacity, and with that we complied to all the requirements of certain authorities. Each one of them by various scales, and get the certification. I'll not get into much detail, but SIR Mark II, we are right now in the design phase. Here also we did a lot of study across the system, and we found that definitely this thing now we are more confident of getting the final release. So now we will look at the indigenization activity. Certainly, of course, at the very beginning, but part of the HACK program, we and of course ANSWER also. We started looking into the various BMSs available in the industry and what are the problems and what should be our drive to meet the requirements for aircraft. Today, BMS available in the industry is not directly integratable to aircraft. So I'll just bring quickly. So today, if you look at the left-hand side, these are the critical or rather the very minimal which BMS systems that we have, non-certified or many of them are in the industry grade, very minimal. But if you look at what is required for an aircraft, so this is the chart. These are the limitations today where we have critically that the balancing issues, active or passive balancing. Then in terms of the even the balancing is done with the solid state devices. The temperature monitoring of such other devices is also one of the requirements. And most important is today's technologies on diagnostics and prognostics. There are requirements to put in. Being the controller is there, we can have a lot of algorithms put in the for diagnostic purposes. Most important, of course, the last requirement is the distributed PMS with the master slave configuration is today's concept of things, because no single pack can provide the required things, so we have to have this kind of configuration. So, in a way, what is that we are not in a very short duration, and what we should do? We have done a requirement capture of based on looking at the industry, looking at what is available, what is required for aircraft, looking at all these both operational safety and regulatory requirements. Then we have arrived at the piece of integrate on the hot cell. I think we have got we got some hot cell, which of course not that high, whatever, but of course to ensure that the BMS is integrated with our device. And of course, we are going. The number 4 is with the ISRO in any case, but we are working with ISRO on the requirements of battery for civil aircraft and things like that. And the last So I'd say that based on our study in last 1 year, 1.5 years, so we have got sufficient information to read our own standards for battery. Because not NL cannot become battery, but battery requirements. We will and EA requirements as a whole, and compiling all of them together and what we require for a single aircraft application. Definitely, there are many documentation available. So we are beginning, we are now going. With this, I close the presentation. Thank you.
Thank you, Dr. Ananda.
Yes, sir.
Take that. Them check. You are spoken, and now you are. I was, what is the kind of ratio between the cell to packaging? You are.
Sir, our study also said that 12 to 15%. 12 to 15%.
And but are we using metal enclosure or composite enclosure or what?
Yeah, it is right now the metal enclosure. Yeah.
That means if I use composite to collect it is further filled up. Yes. That is the point. That is what.
We are not in that. We are not in. As I mentioned, we are not in that. Yeah. So that's why we have.
You will give BX.
Yes.
So I'm asking the packaging, what is it?
Yes.
Our studies show that, but definitely we are not into that domain.
I want to another to be together. Give some
Together. Our studies on the BMS related activities and so there.
SSC, URSC, and our project.
something like 12% is what they have to achieve. We have to come together as a group. With all the standards, you have this interfaces are established.
Yes.
And score for the standard. At top level, we have to decide the limits. You would be running some person.
Correct.
Individual person. Whatever.
Yeah.
So, battery, again, you decide that fact within one under a package or two package. Ideally, it would be better than you have two separate packages. And both are supported by separate microcontrollers. So I have two packages. I can have a different microcontroller for each.
Correct.
And that microcontroller be connected to the avionics bus. So you have to look at the overall there from the units.
Correct.
You cannot look at only from the electric line. Not battery current system per se. You know, it is part of the overall equilibrium system. That's what we are looking at. Once you look at that, then all the other lenses is possible.
Yes. Yes.
Well, I don't understand whether you are not going. Well, one is not there. The problem, whatever you
Sir, in our case, it is a simple thing, dual. We don't go beyond that. And I said in the last J, the right side, what you're talking is this distributed. It's not a single. I will have multiple BMS, but they are connected together, synchronized, and as a whole.
See, the moment you talk of synchronization, you are talking about complexity and synchronized system way to that. What you do is, just give one example. I don't think that only derived with good battery packs. You have dual redundant management system here itself. What by default, in this place, you have a K1 only that you let then you other one takes over. And then this is connected to the bus. Similarly, other one. You want redundancy for one management system, they will do all management. So you think every system and not the singularity on that. Synchronizing actually doesn't result any advantage in this case.
Yes.
Because time synchronizing is not the moving for you. You are not running a GPS problem.
Correct.
So in this case, it is passive management. 2 milliseconds doesn't make difference anyway. So you have to synchronize per point. So what do you do that? Just think it over. Think the overall system.
Sure. Sir, today, what we have worked for aircraft, although I said that the BMS should have this interface, it's not specific to BMS. We also looked at what the requirement in my cockpit other system, how it is interfaced and what is the requirement?
Bus.
Hmm.
This display will be only bus.
Correct.
Display is not worried about this.
Yeah.
Display is what you will see a display. You will always have Windows, but one more power system, one more internet, one more, and then you can do that. But everything is connected to the bus.
Correct.
So you don't have to look for display versus this. No, they are independent.
Yes, sir. Correct. You are right. Yeah. Yes.
So you don't have to worry about that at all. Display will be put in a independent system.
Correct.
So you have the bus.
That's it.
You have real bus. Buses are going there. And they have a selection. So think it's total system. And they have to explain.
Dr. Mukhopadhyay, you wanted to.
But you are on the right side. Okay. So I'm missing couple of functionalities. For example, what we do to take care of sensor bias. So there can be voltage sensor, current sensor bias.
Yes.
That can lead to error in SOP estimation, which can lead to, we will be going to the energy management, and it will either reduce the capacity of the battery or lead to charge discharge.
Okay.
So my first question is, I'm missing some functionality.
Right.
So what's the first question?
Yeah. To answer that, I didn't put details, but of course you can see the identified one. That is a complete input interface sensor. So what you said is part of that block. I not explicitly mentioned, but it is the complete sensor management is the first block. Only then the complete system will get interface with the number.
Bias correction.
So that's part of our signal condition.
So you can do on-board balancing.
What we require, and that's where we are right now. Yeah.
So your active balancing circuits
Yes.
can actually go beyond balance. They can provide, if you have a particular cell which is a string at which dies, then the balancing circuit can actually collect for that cell. I mean, the capacity will fall, but your spin voltage will be maintained. So these things are possible.
Yeah.
Another thing is that, are you doing any reverse? See, put temperature sensors on the surface of the cell. But you need to know the temperature inside the cell. So do you have any cell thermal profile estimate?
I think probably that the Coulomb can answer that. We are not into the cell.
So because you need to know what is the temperature at the separator.
Right.
Because the separator that you are going to have a short and you are going to have a thermal. So that estimation would be useful.
Okay. Dr. Ananda spoke about the standards and guidelines for the lithium-ion battery usage in civil aircraft, and also touched upon the BMS requirements. Let us thank the speaker. And now we move on to the online segment of this session. The next presentation.
So good morning. I am Dr. itself.
The next presentation is by Dr. R.K. Singh from IIT BHU, Varanasi. The development of battery management system is the title. Dr. R.K. Singh, Rajiv Kumar Singh is Associate Professor in the Department of Electrical Engineering, IIT BHU. Dr. Singh has got his PhD in Electrical Engineering from the Indian Institute of Technology, Kanpur. His research interests include renewable power conversion for hybrid microgrid, power conversion for electric vehicles, hybrid electric vehicles, optimal charging, discharging of energy storage system, etc. He has published more than 50 SCI research papers, have 2 patents and 2 book chapters to his credit. Dr. Singh.
So good morning. I am Dr. R.K. Singh, Associate Professor in the Department of Electrical Engineering, IIT BHU. The topic of my talk is development of battery management system. So if we look around, so basically batteries have become an integrated part of many of the modern world applications such as electric vehicles, space applications, consumer electronics, etc. Wherever we need uninterruptible power supply or a backup supply, batteries are the prominent basically part of the entire system. And with the time, it has been observed that there have been the evolution in the various types of batteries for different applications, like lead acid battery. Lead acid battery is popular for many of the applications. Nickel cadmium battery is equally, being used for different other applications. Nickel metal hydrate and lithium batteries. And one of the most prominent application area in nowadays in the modern world, basically where batteries are being used very extensively, is electric vehicle application. And in order to compete with the gasoline engine based vehicles, and electric vehicles should actually have some performance parameters, such as it should give good dynamic performance, it should give safe operation and economic and environmental friendly operation. And in order to ensure all these performance parameters, the battery should have high specific energy that is required for high mileage and also reduced mass and volume of the vehicle. It should have high specific power to improve the vehicle dynamic performance and excellent acceleration. It should have high lifetime to reduce the maintenance and vehicle cost, excellent high and low temperature performance. It should have adequate charge and discharge rate. Of course, cost is a very important part for any technology development. So it should have, genuine cost, and it should give environmental friendly operation. And in this figure, we can see that how, battery basically powers in electric vehicles, battery powers the propulsion operation. And not only that, it powers the different other devices into the cabin as well. Now, as far as the evolution of the battery is there, the lead acid batteries basically they have energy density of 30 kilowatt hour per kg and life cycle of 300 cycles. The advantages of this battery are basically they have stable performance and good reliability with low cost. But the challenges are there is a lead emission during production, process, and recycling, which may be hazardous. And energy density of the gasoline is around 10,000 watt hour per kg, which is almost 300 times higher than the lead acid. So lead acid requires basically more space for the same driving function. So that is one of the issues with this. Nickel cadmium has energy density of 50 watt hour per kg and life cycle of 500 cycles. And advantages of this are it has basically high energy density and life cycle in comparison with the lead acid battery. But the challenges are the toxicity of the cadmium metal is huge, and it creates a serious environmental effect, right? And moreover, it has a strong memory effect. That means a temporary decrement in the battery capacity is there if there is an incomplete charging discharging. Nickel metal hydrate has energy density of 60 to 80 watt hour per kg and has the life cycle of 500 to 2000 cycles. It has got the advantage that it is less polluting, overall performance is better than the lead acid and nickel cadmium. It has good characteristic at low temperature. But the challenges are, again, it also has got a strong memory effect, right? Memory effect is not completely eliminated, which is one of the major issues with this. And serious heating is there. The thermal management of this battery is another big issue, right? And at the same time, it has a poor charging performance at high current, right? Now coming on to the lithium ion battery. So it has very good energy density, 60 to 120 watt hour per kg, has the life cycle of 1000 to 2000 cycles, right? Better than others. And advantages are that it has no memory effect. So the capacity does not basically degrade if you are not charging it fully or discharging it fully, right? It has high power density at less discharge, has the mass of pack reduces basically by 40 to 50%, and the that's how volume for many of the modern world applications such as consumer electronics or electronics. But there are certain challenges with the battery pack system, right? And they are low cycle life, slow charging, poor temperature, low temperature discharging capacities, and it is very difficult to predict their degradation state. And moreover, there is inconsistency between the cells due to different manufacturing and operating as the technology with which we can actually overcome the challenges associated with these battery packs. And the objective of the battery management system is that it protects the battery cells from abuse and damage. It gives the extended life. It determines the state of the health. It balances the cell. It performs the logbook operation. It communicates with the display devices. And in this architecture of the battery management system, we can see that it basically takes the information of the entire battery pack, current, cell voltage, and temperature, and then inside to it, the algorithm actually is executed in such a way so that it gives the SOC, SOH information, the life cycle, the impending fault, as well as the fault that has already happened into the system. So all these performances are performed by the battery management system within itself, and it can also communicate with the CAN through the CAN protocol with the display devices. So there are different topologies for BMS. That is distributed topology, modular topology, and centralized topology. So in the distributed topology, what happened, there used to be one master controller basically that takes care of all the operation of all the cells. One controller is basically responsible for performing all the tasks of SOH, SOC, cell balancing, everything, right? In the modular topology, what happens in a group of cells, basically they have their dedicated slave controller, right? And there used to be a modularity. Further, they can add on to that, and all the slave controllers basically are controlled with the master controller. In a centralized controller, what happens, there used to be one centralized master controller that takes care of all the cell the functionalities related to all the cells, like state entire thing is taken care of by the centralized controller itself. In the operation of the battery management system, so what happens, basically this figure, this shows that, okay, the battery management system basically takes information of the cell voltages, current, temperature, and all. And in case of unwanted or unsafe event, what happens, there used to be a master disconnect. So it first disconnect the BMS from the source or a load, and execute itself execute within itself to ensure that unsafe event, or take care of those unsafe operation. So here, for an example, three cell system system is shown. So essentially what happens in case of any unsafe operation, first it disconnects from the source or a load. Then internal algorithm execute it accordingly to take care of the cell balancing, to take care of this other unwanted or unsafe events. State of the charge basically is one of the function that battery management system performs, and state of the charge represents the amount of energy that is left in the battery with respect to the total amount of energy in the battery when it was fully charged, right? So supposing your battery remaining capacity is 50 Ah for a total of 100 Ah capacity. So one simple formula of calculating this SOC is that you divide 50 by 100. So that's how you are getting 50% of SOC. But this SOC calculation basically is not accurate in terms of giving the energy however energy is left into the battery, because if you look at this profile, so 50% comes at this level, right? So at this level, the area of A1 is not equal to area of A2. So that is not predicting the exact amount of energy that is left in the battery if you are actually calculating the state of the charge with this method. So in order to take care of this, a Coulomb counting method for state of the charge calculation basically is evolved. And in this method, what happens, a discharging and charging current is measured and integrated over a period of time to calculate the total amount of remaining energy left into the battery. So that kind of predicts the exact amount of energy left into the battery. And if you look at this dotted line, so at 42% level, the area of A1 and A2 will be same, and that is how you can say that yes, at this percentage, the battery has 50% of energy left into it. So this predicts basically an exact state of the charge information. State of the health is another very important this function that is performed by the battery management system. And what happens, it is required basically to prevent failure and accidents, and to get prolonged and useful lifetime from the battery. And SOH is defined by the ratio of total capacity of the battery part today, and when with respect to the total capacity at the beginning of the life, right? And what happens with the number of cycles, with the increased number of cycles, the total capacity keeps reducing, and internal resistance of the battery, that is equivalent series resistance of the battery, keeps increasing. And this becomes very important parameter to basically, predict the state of the health of the battery, to model the state of the health of the battery. So higher the ESR means more thermal runout, and more thermal runout basically meaning is battery will have the lesser life. So this internal impedance characteristic, this profile becomes important to predict or model the state of the health of battery. BMS also performs basically and gives the provision with which we can operate the battery under safe operating area. So it prevents from the over temperature fault, right? So because it is required to protect the battery from thermal runaway. It also ensures overcharge protection that is required, for a battery cells, because battery cells cannot hold overcharge for a long time, which results into fire or explosion or melting of a cells. Similarly, over discharge protection is required at the same time, because electrochemistry of the lithium ion cell is no longer safe, and overall capacity of the cell is reduced, right? Under temperature protection at the same time is required, because electrochemistry in the cell is not able to move the ions on anode and cathode, right? And that's how battery will not charge and discharge properly, right? So BMS actually takes care of the envelope of the safe operation area. The cell balancing is another very important task to be performed by the battery management system, and commonly used cell balancing techniques are passive cell balancing, active cell balancing, and lossless cell balancing. So in the passive cell balancing, what happens, supposing this is the actual situation, and after some time, let's say cell 1, 2, 3 has they have the status, cell 1 has this status, cell 2 is having the status of this much, and cell 3 is this. So in this, what happens, a dummy load like resistor is used to discharge this excess voltage in order to equalize it within the cell itself, right? And this cell balancing controller actually turns on and off these MOSFETs accordingly, so that whenever there is a cell that is that has voltage gone up beyond certain level, then the dummy resistor will be connected through and this MOSFET will be turned on accordingly, and that kind of operation will reduce the voltage. And this process will continue till the time proper balancing across all the cell is achieved. In case of active cell balancing, what happens? Cell balancer generally transfers energy from one cell to other cell, and similarly discharge energy from one cell to other cell, right? So energy is transferred from high voltage, high SOC to a cell having low SOC, and that's how active cell balancing circuits are basically, they does not involve any dummy resistor into it, and they are typically based on capacitor, inductor, or transformer, or any other power electronic circuit, right? So some of the examples of this active cell balancing is shown here, in which in this case, what happens, if let's say cell voltage of B1 is high in comparison with B2, then this B1 basically charges this capacitor, and this capacitor further discharge itself to charge this B2. So in this way, B1 is supplying power to B2 through this capacitor, and in this case more number of capacitors are being used. Another way of transferring the power from one cell to other is through inductance or transformer. So in this circuit, what happens, let's say if B1 is having more voltage in comparison with other cells in the system, then this switch will be turned on and the power will be transferred through this transformer to other cells till the time the voltage is balanced across all the cells. And there is another technique, that is, lossless balancing, cell balancing. So in this lossless balancing basically is recently developed, that reduces the losses into the system. And in this, what happens during the charging process, the cell that is having high voltage is removed from the process, right? So supposing this cell basically is having high voltage, then the transistor will be turned on, right? And this entire network will be bypassed through this, right? So if the cell voltage is more, that will be kind of cut off from the and network, right? And the same technique is followed during the discharging as well. So in conclusion, what I can say that for effective and safe operation, BMS technology is very important for charging, discharging of modern batteries. It ensures thermal management, it models the state of the charge, predicts the state of the health of the battery, it helps in operating under safe operating area, and it improves the efficiency and life of a battery pack. So thank you very much.
Talk, Dr. Steen spoke about the BMS functionality and various ways the BMS function for lithium-ion batteries are implemented. Any questions to Dr. Singh? There is one.
Thank you, Dr. Singh, for the comprehensive presentation on the BMS development process. I want to know in indigenous BMS, what kind of products are available. And we do use something which are passive balancing BMS without communicating deficit. Have you come across getting available products which can communicate?
So your voice is cracking. Your voice is cracking. Can you come again? Sorry. Am I audible?
Sir, please come here.
My question is about indigenous availability of advanced BMS. Can you throw some light on it?
Yes, so as far as everything is being imported from outside, and the companies, they are assembling the components and making the BMS. So our effort is to develop, as you said, that indigenous development is very important for us, and battery management system is very important part for as far as entire operation of the battery is concerned. So yes, I mean our whole effort is to indigenize this development, and we are working very hard. And Tata Motors basically is our industrial partner, and we are trying to build up a battery management system for 320 volt 26 kilowatt hour battery, and the whole process will be indigenous only. We are actually trying to develop at least everything within our lab itself with the help of Tata Motors. But yes, as far as the components are concerned, I mean, see these chips and ICs and other things. So we don't have any industry or other organization who is manufacturing as of now. So in order to develop the BMS also, we need to purchase all these components from outside.
Fine, thank you. More questions to thank the speaker. Thank you. Next talk is on the lithium-ion battery degradation studies by Dr. Abir Ghosh, again from IIT.
Hello, one and all. I am Dr. Abir Ghosh.
Dr. Abir Ghosh is currently an assistant professor at the Department of Chemical Engineering and Technology, IIT BHU. He has completed his PhD from IIT Kanpur and worked as a postdoctoral research associate at the Electrochemical Science and Engineering Group at the Imperial College of London. His areas of expertise are complex fluids, thin films, microfluidics, electrokinetics, lithium-ion batteries, and supercapacitors. He has 14 publications in internationally reputed journals. Dr. Ghosh.
From Indian Institute of Technology, BHU, Varanasi. I truly appreciate this opportunity to be a part of this foundational meeting of Swadeshi e-Biman community. In my talk today, I will be focusing on understanding the degradation of lithium-ion batteries. Particularly, I will be focusing on the degradation of nickel-rich positive electrodes and how this understanding can help us to improve the operation of lithium-ion batteries. Before going to the fact that the lithium-ion batteries still remain a very good because of several degradation mechanisms that are going on inside the lithium-ion on the or other harmful gas evolution from the positive electrode side, and several degradation mechanisms that are going on in the electrolyte as well. All of these degradation mechanism reduces the lifetime of the lithium-ion batteries in batteries. In the next slide, what we are going to do is comprehensively distinguish the degradation separately on the negative electrode, positive electrode. So this primary degradation mechanism in the negative electrode, such as positive particle fracture of the negation mechanism of the positive electrode, such as eventually 2 milliamp hour per gram, which is a theoretical capacity, and we can extract almost around 350 milliamp hour per gram as a reversible capacity for graphite electrode. However, there has been choices of positive electrode that have been tried, and the recent commercial positive electrode that has been used in lithium-ion batteries is Nmc 811 electrodes, and they have a theoretical capacity of around 275 milliamp hour per gram. However, their reversible capacity reduces to 100 milliamp hour per gram. So that is a huge drop in a specific capacity. And that is because Nmc electrode goes through a phase transition at the higher degrees of delithiation. That means when during charging, the lithium ion goes out of the electrode and the lithium ion concentration is low in the positive electrode, Nmc 811 goes through a phase transition. Now, the structure of the Nmc electrodes they are basically layered metal oxide structures, as you can see from this figure. And as mentioned in the previous slide, at higher degrees of delithiation, that means when the lithium ion concentrations is low in the positive electrode, these layered metal oxide structures converts into a spinel and rock salt structures which are not layered. And these spinel and rock salt structures are thermodynamically much stable whenever the lithium ion concentration is low. And these structures, as you can see from these figures, that these structures are not layered. So they create a passivation layer which doesn't give a lithium ion pathway, and the intercalation, like the diffusion in or out of the lithium through the electrodes, becomes difficult within this Nmc electrode. And as you can see, when these layered structures are converting into a spinel and rock salt structures, there is a reduction in the oxygen ratio. And this reduction comes in form of a nascent oxygen. And they are very reactive. So either they give you oxygen or they react with the electrolyte to give you other harmful gases like carbon dioxide and carbon monoxide. And experimentally, this has already been proven that this oxygen release happen at the higher potential of cycling of lithium-ion batteries of around 4 volt, and that actually reduces the capacity fade and the impedance rise. So the impedance rise is happening because lithium ion pathways are getting blocked and the lithium ion cannot diffuse in or out of the electrode. Now, a multi-scale approach was required to understand the positive electrode degradation that we have described in the previous slide. And the same was implemented. like how the nickel and the sodium ion exchange or the molecular rearrangement of the nickel and the sodium ion leads to the structural degradation of Nmc 811 electrodes, and how that structural decomposition is affecting the continuum properties like the diffusivities of lithium through the newly created phases of Nmc 811, and how they are affecting the shell level degradation. Also, they are affecting the electrochemical performance and the temperature of the battery or the operating conditions of the batteries, those who are affecting the degradation and also the performance of the lithium ion batteries that we have figured out through a continuum scale model. And let's see that model can predict the capacity fade that a cell in a cell level going on or not. As mentioned in the previous slide, we have developed a continuum scale model to understand the structural decomposition of positive electrode and how that is affecting the capacity fade of lithium ion batteries via a continuum scale model. So here what we have considered the whole positive electrode as one effective positive electrode particle, and we have developed a shrinking core model where the core is, you can consider it as a layered transition metal oxide or good cathode. However, the shell is basically the bad cathode, or what you can say is the phase transition material through which the lithium ion diffusions become very slow. And this phase, like the shell, is increasing because of the chemical reaction that is happening at the core shell interface. Now, I am not going into the details of the developed model. However, what we can see here is that how the model is able to capture the capacity fade because of the phase transition of the Nmc electrodes. Let's suppose here I am showing 4 cases. Let's consider the case A, where the electrode that is without any degradation, that means a fresh electrode, and we are saying that is beginning of life. And if we do like how much capacity it is giving, the black line is the one you can look into the inset. So this is how, like 3.2 is the capacity that the Nmc 811 electrode is giving if there is no degradation present. However, look at the case D, where there is this this phase transition is happening and the spinel and the rock salt layer, or you can say the bad cathode part, is increasing with respect to time as the reaction is happening. And you can see, if you look into the inset, how the capacity is decreasing. This is from, compare the curve A and D. So the model that we have developed is basically able to capture the capacity fade that is happening because of the phase transition of Nmc electrode. Now, going further into the details of the capacity fade, like if the shell thickness or the, you can say the transition metal that is creating a passivation layer, if that thickness is low, then what happens? The degradation mechanism is reaction dominated. As you can see that with the this D0 is basically the diffusion of the lithium through the passivation layer, and this is the reaction rate. And you can see that it is changing with respect to the reaction rate. As the reaction rate is changing, your capacity fade is changing. However, there is no change with respect to the diffusion of the lithium ions if the passivation layer thickness is very high. So that means we can distinguish between this degradation mechanism is as like it is either diffusion dominated when the oxygen diffusion is slow and the shell is thick. However, it is reaction dominated when the oxygen diffusion is fast and the passivation layer is thin. And the transition between these two limiting cases is a complex interplay between the reaction rates and the oxygen diffusion rate. Now I will summarize by saying that we have developed a thermally coupled physics-informed continuum scale model to explore the structural changes of positive electrode on the performance of lithium-ion batteries. And our model is able to predict the capacity fade due to the loss of active material and loss of lithium inventory, as well as the slow diffusion of the lithium ions give us the power fade that is happening because of the generation of the passivation layer. And these kind of models are a necessary step to create a unified model with all the degradation mechanism included to predict the actual capacity that will that we can get after a few cycles and when this degradation mechanism are happening. And similar kind of degradation models or continuum scale degradation models are required for the electrolyte degradation as well, because those kind of models are rare in the literature. And the major advantages of these models are they can be easily extendable to other battery chemistry as well, like next generation battery chemistries or solid state batteries, sodium or aluminum batteries, in specific to the sodium and aluminum battery chemistries, because that will be helpful for our nation's energy growth as well, because of the abundance of sodium and aluminum that we have. Uh, Also, for this newer battery chemistries, what is required? An unified approach. Like we require machine learning to predict the proper combination of electrode and the electrolyte, even the composition of the electrodes and the electrolytes of new materials. And DFT will come into the pictures, or density functional theory, as soon as also we require multi-scale modeling and cell level experiments to predict and design the actual electrode and electrolytes for next generation battery chemistries. With that, I want to convey my regards and thanks to all the academician colleagues and friends with whom I have worked at Imperial College London and Faraday Institute UK, from where I have started this journey of lithium-ion batteries, and with all the group members with whom continuously I am working at IIT BHU Varanasi. And last but not the least, with all of you to giving your time and listening to me. Now I will be very much happy to answer your questions. Thank you.
Dr. Ghosh spoke about modeling of the lithium-ion cell degradation, especially the positive electrode modeling and its degradation. There are any questions?
Thank you.
Hello. Hello, sir.
Thank you. You have done the electrodes. Now you need to include electrolyte. Then we get the total picture of the degradation of the full cell.
Yes.
Am I right
Yes.
in my understanding?
Sir, if I am understanding you correctly,
hello?
yeah, if I am understanding you correctly, yeah, that is only a specific kind of like one or two degradation mechanism that we have modeled. Now the next step will be like whatever degradation models those are available for the negative electrode, we need to include that as well with the positive electrode degradation that we have developed, and together with the electrolyte degradation. So then only it will be kind of, already our team is working on a Python based model. Like this will be kind of one of the commercial packages that nowadays CFDs people use. So we can include the proper degradation module that we require. Like maybe on some other batteries you have negative electrode degradation is much higher. In some other batteries you have positive electrode degradation which is higher. So including that, you can include just the degradation mechanism that you require, and that can be then used with the specific parameters of the batteries to predict the capacity fade and the lifetime and the power fade of that model. Yes.
Okay, thank you.
Thank you, sir.
Any other questions? Okay, we'll thank the speaker for his talk.
Thank you.
We come to the last presentation of this session. This is by Dr. Prakash. His topic is the battery development. Dr. A.S. Prakash is a senior principal scientist in the Central Electrochemical Research Institute, Chennai Center. He received a PhD in the chemistry from Bangalore University. He has got rich research experience in lithium-ion battery research and development. He has authored more than 50 research papers and have 6 patents to his credit. Dr. Prakash.
Yeah. Good afternoon to everyone. Am I audible?
Yes, please go ahead.
Yeah. Good afternoon. I am Dr. A.S. Prakash from CSIR Central Electrochemical Research Institute, Chennai Center. I would be presenting our activities towards indigenous lithium battery development for EVs, energy storage, and avionics. As you all, next slide. Yeah. You all are very familiar with lithium batteries. Lithium batteries are established commercial products. However, R&D is still required to improve their performance to meet hybrid electric vehicle and electric vehicle requirements. And enhancement in terms of safety, energy density, and cost are very much required. And batteries for India's specific needs. Indian geographical terrain and weather conditions, and even the Indian consumer usage pattern can be totally different. And in India, temperature can vary from 45 degrees to -10 degrees centigrade. The batteries made in Europe or America or for other part of the world may not fulfill all the performance requirement for India specific applications. And hence, there is a requirement for developing batteries for India specific needs. If you look at the lithium batteries, these are various cell configurations available. They are available in cylindrical format. We call it the 18650 cell. It means 18 mm dia, 650 mm height, or 21700 cells, or 2650 cells, and so on. Similarly, prismatic of various dimensions and pouch cells are available. And these are the down one is the button cells, which you could use it in, which you could see it in watches and so on for small applications. And for EVs and cylindrical and prismatic cells are preferred for automotive application due to large surface area of electrodes, and therefore it is less weight, therefore the higher energy density. In CSIR-SICRI, we have capability and expertise available for cylindrical, prismatic, as well as pouch cells. And these lithium batteries have a diverse application. From a lithium battery of a few microampere hours are used for electronic convenience like RFID, sensors, wearable devices, and so on. And lithium batteries of capacity of few ampere hours are used for consumer electronics like your mobile phones and laptops and so on. And several batteries put together to have several tens or hundreds of kilowatts can be used for EVs like e-scooter, e-car, bikes, and so on. Similarly, batteries of capacity several hundreds of kilowatt to hundreds of megawatt can be used for energy storage applications like for grid storage or for harvesting renewable energies like solar and wind farms and so on. So these are the various applications lithium batteries found in. Next slide, please. Next slide. In SICRI, we have, these are the various lithium battery technologies available in CSIR-SICRI. We have technology for active material production, large scale active material production, cathode material production. So the process can be used for lithium manganese oxide and all variants of NMC cathode materials, NMC 111 to 811 cathode materials. The process can be used for large scale production in a cost effective way. On the cell technologies, we have three chemistries starting from NMC graphite, lithium iron phosphate graphite, NMC LTO, LCO graphite, and so on. On the IP portfolios, these are the 3 important patents we have on lithium batteries and a process for the preparation of cathode material for lithium batteries. So this is a process patent for large scale production of cathode materials in a cost effective way. And the second one is a process for producing cathode active material composition for lithium batteries. We have come up with a unique compositions of cathode materials which have a better enhancement in terms of performance and capacity, capacity stability, and so on. And the third one is on the thermal stable cathode active material compositions. We have few unique compositions of NMC 532 based cathode compositions which exhibit a better thermal stability, and therefore safety of the battery can be much higher and so on. And we have expertise as of now on the coin cells, cylindrical nitride cells, and prismatic cells. And in about 1 year, we will be also be coming up with 26650 and 21700 cylindrical cells. Next slide, please. Yeah, this is one of the IPs we have. So as I said, we have the process, this is the process patent we have, and this process can be used for large scale production of cathode active NMC based cathode active materials, and the process can be used for all variants of NMC, and the materials derived from this process can be on par with the global benchmark materials which you obtain from standard suppliers like Unicode, BSF, and so on. And we have scaled up this process, and we have put up a pilot plant for producing 25 to 30 kgs of NMC cathode material per day. Next slide, please. So this process is very simple. Next slide. Next slide, please. This process is very simple, and this is about 25 to 30 kgs. Previous slide. 25 to 30 kgs of cathode material can be prepared, and we can take the reactants in a stainless steel container, and this is being introduced in a conveyor belt furnace where it goes to the high temperature zone, and an exothermic redox reaction happens, and the reaction is completed within about 10 minutes, and you get about this is a kind of batch process. In a batch, we are producing 1 kg per day. We can make 15 to 20 kg of cathode materials from this process, and then it has to be reheated to a required designated temperature to make it electrochemically active and so on. This process can be cost effective. Next slide, please. The other IP we have is on thermal stable NMC cathode compositions. As I said, we have come up with a unique compositions wherein thermal stability can be better, and this composition can mitigate the thermal runaway. As we all know that the cyclic degradation and catastrophic failure leading to safety issues are a serious problems and complex phenomenon originating from various reactions during the charge discharge process. If you look at the lithium and battery, the heat generation is more on the positive electrode sides. So we have this kind of positive thermally stable cathode active materials. Suppose if the in normal condition when your BMS is working fine, your electronic controllers are working fine, and heat exchangers are taking away the heat produced in a battery pack, then all fine, the battery works good and it is safer. However, thermal runaway can be initiated by abuse of a battery pack or by accidental crush or internal short circuit or electrolyte leakage or overcharging and so on. This will generate a lot of heat inside the battery and it lead to a explosion and safety issues. So we have these electrode materials which can have a better thermal stability, which I show. Next slide, please. Next slide. Yeah. So this is on more on the fundamental mechanism of what happens with this, what happens in the structure with this structurally modified cathode material. So in layered cathode materials, you have MO6 octahedras, edge and phase shade octahedras, which are wherein we have a substitution of several metal ions, wherein the oxygen D bands are on par, are too far in comparison to oxygen 2p bands. By combination of more electropositive transition metals and non-transition metals are used to reduce the degree of metal oxygen covalency and thereby to minimize the thermal runaway issues and so on. So this is the next slide. Yeah. This is the characteristic of thermal runaway studies on the structurally modified NMC cathode composition. I give here two graphs. The one is on commercial conventional NMC 532 cathode. You can see the electrodes at 75% state of charge were removed, and in terms of electrolyte, we have conducted a DSC studies. You can see the batteries around 250. From the previous speaker was talking about the thermal runaway from 150 to 300 degrees. So on an MC532, we have observed a exothermic heat around 260 degrees centigrade. You can see at the same identical conditions, these structurally modified electrodes completely suppress this thermal runaway problem. Even at 100% SOC, thermal runaway is shifted to almost like 60 to 75 degrees centigrade higher temperature. Further, these electrode materials also they demonstrate better in terms of cycling performance and degradation approaches. Next slide, please. Next slide. Yeah. So once we make all these materials, we scale up, and then it goes into a lot of engineering process for when you have to convert that into a battery. So battery manufacturing involves several engineering operations. It involves about 15 to 18 unit operation. This is the schematic of lithium battery manufacturing process. We start with the slurry process. These powder material are converted into slurry. We mix with the polymer binder and the solvent, and we convert into a viscous slurry, kind of paint like viscous slurry. And those cathode material is coated onto aluminum current collector, and anode material is coated onto copper current collector. Then it goes to a calendaring process where this is the process where the densification of the electrode happens. The higher the dense electrode, the more the energy density you get. So you need to process this electrode to better densification, and then it goes into a splitting process. It depends on the exact what is the configurations of the format of the cell. You need to cut into a specified dimensions and so on, and then tab welding and vacuum drying and so on, and then the assembling process. This is a complete process. In Thickly, we have created the next slide, please. We have created the state-of-the-art facility for lithium battery manufacturing. Next slide. Next slide, please. Yeah, these are the state-of-the-art automated facility for lithium battery manufacturing. Using this facility, we could make about 1,000 cells per day. And this is the cathode slurry mixer, and this is for the anode coating line. Next slide. Next slide. So all this equipment has to be in the dehumidified atmosphere, and for battery manufacturing, you need something like less than 1% of humidity level. And this is a cathode coating line. So using these facilities, we are able to make 1,000 cells per day. And this is a complete this is a splitting machine. And here is all completely automated machineries. So from one process to another process is a kind of roll-to-roll processes. And we have created this automated facility. Next slide. These are splitting process. Next slide. And these assembly equipments which are housed in dry room atmosphere. And so as I said, we maintain something like 1% RH for making all these batteries. Yeah. And so using this facility, we are able to make 1,000 cells per day. And now we are coming up with still higher capacity. We have a project from CSIR Innovation Center for Next Generation Energy Storage Solution. The project is about 100 crore, wherein the objective of this project was to enable the indigenous lithium battery technology to the scale of 100 megawatt per year under Make in India as well as Made in India policies to ensure self-reliant India. And this project is implemented in 2 phases. In the phase 1, is already operational. Phase 1 facility is already operational. We are making 1,000 cells per day. And here in the phase 1 facility, we are producing 8650 type cylindrical cells. And present status is installation is completed, and the trial production are going on. And the phase 2 is about 100 megawatt lithium battery production facility. And per day we'll be making something like 15,000 cells of 5 ampere hour 21700 type Nmc based cylindrical cells. The status is we have designed the equipments, and we have already gone through the tender process, and machineries tender process is completed, and the PO will be released soon. And the plant layout is finalized, and the building construction etc. will be taking place in about a few months. And in about 1 year, we will have 100 megawatt manufacturing facility. And the idea is we are at the tier level 6 presently, to go to the tier level 8 or higher, so that the commercially it can be made viable and so on. Next slide, please. Yeah. So this is the performance benchmarking of our cells in comparison with the global benchmark. So as I see here, these our cells are with the NMC 532 cell chemistry, and these are 18650 cell. Currently, we are making 2.3 to 2.5 ampere hour 18650 cell, and our commitment is to make 2.5. Although we make 2.5, we have kind of consistency. We are able to go with the 2.3 ampere hour. So presently, we are at 2.3 level, and global standard for similar chemistry is 2.5. And SICRI's performance benchmark is our cells are able to perform at C/2 1C and 2C rate, whereas at 5C rate there is a significant capacity drop. So whereas the global standard for power cells are up to 5C rate, this is something we still need to improve and so on. This is the specification of our cells. The cells are up 2.3 ampere hour, 3.6 volt, and this is the charging protocol CCCV at 3/10 rate. Voltage range is 4.2 to 2.8 volt. The cells are about 43 grams, and the cells can work from 10 to 55 degrees centigrade. And cells have energy density of 526 watt hour per liter, and gravimetric energy density of 192 watt hour per kg. And in the bottom table, I had given the comparison for similar cells of similar chemistry manufactured by Samsung. Samsung 26 FM cells are with the 532 power cells. The weights were about 45. In our cells are about 43 grams. Voltage wise, ours we are comparable 3.6 volt. We are able to go up to 2.3 ampere hour, where the commercial cells are 2.5 ampere hour. And in terms of gravimetric energy density, we are very close to commercial cell level. So Samsung cells are 205. We are at 192 watt hour per kg. 192 watt hour per kg. And volumetric, we are almost close. 526 our cells, and commercial is 560. We are almost close to commercial benchmarks manufactured from best like Samsung or LNG. Can you go to the next slide, please? Yeah, and we have evaluated these cells and validated for various applications. These are some of the recent demonstration, and these cells have been used for consumer electronics like torches and powering the power banks and solar lantern, and even several cells we put together to make 1 kilowatt pack, and these cells have been used for EVs. And this was our former science minister, Dr. Harshvardhanji, took a ride with the EV scooter, which was fitted with our indigenous lithium batteries. And these are our DGCSR who took a ride on the two-wheeler EV, which have used our cells. This is the e-bike and solar application. These our cells have been validated for all these applications. Can you go to the next slide? Next slide, please. Yeah, before I close, these are some of the views on lithium battery overview for aviation application. As you all know that lithium batteries are mature technology with application from portable electronics to the space and for military operations. Lithium batteries converts chemical energy into electrical energy using a cathode material and anode material coated onto the current collector, a polymeric separator, and a liquid electrolyte. The lithium battery sector is a very promising field as it is capable of powering the next generation electronics to space and to the military applications. Lithium batteries show a blameless performance up to minus 10 degrees centigrade and beyond. Beyond this, the cell performance is unsatisfactory due to high charge transfer resistance in the liquid electrolyte at low temperatures. So we are working on several things on the electrolyte to develop low temperature the electrolytes which can perform at low temperature, as well as safer batteries which have a fire retardant electrolytes and so on. Next slide, please. Next slide. Yeah, application of lithium batteries for avionics. Lithium batteries are potential candidate for backup power supply, emergency location transmitters (ELTs), emergency power for control systems and auxiliary units, engine start and GPS devices. In fighter jet applications, they can find application for high energy density, resulting long mission time with less load, and emergency power and control systems with better BMS, less maintenance and long life. Next slide. Some of the limitation of batteries for these applications would be, these are the potential candidate for explosion and fire, degradation in low temperature due to electrolyte freezing, pressure built up in lithium battery due to reduced pressure, and low capacity and cycle life in high altitudes. As we know that the temperature for these application temperature can vary to the negative temperatures and so on. Electrolytes are the major issues. So these are the several disadvantages. And temperature fluctuation accompanied with vibration and damage to the cells and so on. Next slide. These are kind of strategy how to overcome these limitations and so on. Cell is to design batteries for avionics applications, and high rigid container and restraint for each cell, as well as pack, pressure release vent with innate safety devices, proper check and certification before installing into the aircraft, no compromise in short circuit and over potential, robot insulation and rigid structure, modification chemistry for less impact from extreme conditions, less shortening and resistance after vibration and shock, and so on. So next slide. Next slide, please. Yeah. In summary, India's requirement for batteries is huge, and no Indian company is making the cell as of now. And there is a big opportunity for lithium battery manufacturing. Scale up possibility to produce lithium batteries with improved energy density, power safety, and reduce the cost. It is possible that make in India batteries be cost competent than the imported cells from China, Korea, Japan, or elsewhere. Band gap engineering and tuning the degree of metal oxide covalence in cathode can be an alternative approach to mitigate the thermal runaway leading to safety issues. There is a threat of not getting the quality cells guaranteed availability if we depend on cell imports. With that, thank you very much. I would be happy to answer any clarifications and questions.
have been established at Secretary Chennai campus.
Yeah.
If there are any questions, that go ahead as a question.
Dr. Prakash, nice to know that you have done good work in this and that there is cell which produces 192 whatever per kg kind of a density. But the question is, I think if you produce all that cells a day, does it make any commercial impact on the country at all? Because Sony makes maybe 1 million cells an hour. So if you have to really make some impact on the country, then you have to really give it to the production to some manufacturer, commercially manufacturer. And otherwise, it just will remain another development and that go away. Actually,
Exactly.
what you should do is you should really concentrate more on the further development.
Yes.
And what we will have from you, something like what you see perceive to do in next 1 year or 2 years. Are we talking? Could you take up this capacity, the density, something like 400 watt-hour per kg in next some time? So there are two questions related. One is with respect to if you have this low capacity of production, you will never be cost competitive.
Yes.
Compared to the world. So how do you do that? Secondly, what is your R&D plan to bridge the gap? Today, world is already producing 400 watt-hour more or less at the commercial scale. So where are we? What is your perspective plan for that?
Yes. For the first thing, we have an industry partners who would use this facility even for the phase 1,000 cells. We have an industry partner who would use this facility and manufacture cells with our technology, and we will use it for various applications and so on. R&D, yes, we are continuously on phase with the global developments, and we are doing continuous improvement in terms of as you can see, we are very close. Similar chemistries, we are almost very close to the commercial benchmarks, and we have put up a continuous efforts on that. There are a lot of R&Ds we will be doing it, and there were even there are some of the significant things are there. We have created IPs and so on, so that we nurture Indian industries, so that they don't need to buy an IP for technology from other well-established people, and then they also don't give the latest technology. So these are the some of the vision SICRI is working, sir.
So I took the sentiments. I didn't get the numbers. Is there any industry coming up with a large production capability?
Yes, yes.
I didn't get that feel.
Yes, sir. So the 60 we have transferred technology to Tata Chemicals. So Tata Chemicals is putting up a gigawatt scale factory, and we have right now for our 100 megawatt facility also there will be an industry partner. For the phase 1 already we have completed the tender process. Godi Energy from Hyderabad based company has been selected to operate and maintenance and work with SICRI. They will be using these facilities to commercially manufacture.
Will I be able to buy CSIR technology cell available in Bangalore, let us say in city market sometime in future?
Yes, yes, sir.
Okay.
Yeah. I didn't understand what band gap engineering has to do with lithium ion batteries.
Yes. As I said, we are using certain elements in the NMC 532 chemistry. So wherein the bands, the 3D bands are too far away from oxygen 2p or cobalt nickel manganese bands. So therefore, you can see the DAC results. There is a significant improvement. So the most of the safety issues and thermal runaway are initiated due to this band overlapping with the oxygen 2p bands, oxygen 2p levels, and then the electrolyte reactivity and so on. So by using combination of several elements, substituents in the structure, we are able to get, and we are practically we are seeing from the DAC results.
Okay, if there are any other question? Yes, there is one last question. Yeah.
Thank you, sir. I don't know if this question relevant to the session, but definitely on the battery, yes. And because I think this is the session on the batteries part, so I thought I would ask the last. Regarding what about the battery? Once the battery life is over, does that not translate as a waste? In terms of battery-based management, looking at large numbers and the industry coming to a point where we're talking about variation. Are we looking at this also translating to some kind of a danger point in the future? That's just a question asking my.
Okay, the voice is not very clear, but what I understood is your question is on battery waste management. Am I correct? Yes. There are recycling approaches, recycling of lithium, used lithium batteries, etc. are on progress. We have a team working on exclusively on the recycling of lithium batteries to extract lithium as well as other metals from waste batteries.
Thank you.
Thank you.
Okay, thank you, Dr. Prakash. Let us thank the speaker for the presentation.
Thank you, sir. Thank you very much. And I thank all of you for opportunity to give me an opportunity to present our work.
So we come to the end of this rather long session, extended nearly 1.5 hours. We had 7 presentations which were completely different and touching various aspects of this lithium-ion battery, starting from the electric vehicle experience to the production of lithium-ion cells in the country. Thanks to all the participants and the presenters. Thank you.
Organizing committee thanks the session chairman Sri Shankaran and all the speakers of the session for educating our workshop participants on energy management, battery cells, packaging, and battery management system. Thank you very much, sir. Now we will break for a lunch and we will reassemble sharply at 2 p.m. So we are running behind our schedule. The lunch is organized at first floor of the campus.
Hello. Hello, Tejas.
Hello. Yes.
Yeah, Tejas, you are able to hear me?
Yes, I can hear you.
Yeah. Tejas, you have sent your presentation.
Yeah.
So what we will do is we will be presenting your slides. You
Okay.
can do the talking from your location.
Okay.
Is it okay?
Yeah,
Is it
that's
okay?
fine.
Yeah.
Navigation, you'll be able to do?
Yeah. Our person will do the navigation, and you just keep on telling next, next, or
Fine.
whatever it is. Okay.
Sure.
It's
Great,
not an
great.
issue. Now we have just half an hour delay is there in our
Yes,
session.
yes.
They have
Yeah.
gone for lunch. Once they
Yeah.
come back,
So, yeah, I've been following some of the presentation yesterday as well as
you
today.
can continue with your work, and whenever your slot comes,
Sure.
you can just join online, unmute yourself, and we will be presenting the slides, and you can do the speaking. Okay.
Okay. Great. Okay.
Similarly, Dada Sahib, good afternoon.
Yes,
Yeah,
sir.
same thing with you also. We will do the navigation of the slides. You do the speaking from your side.
Okay.
Okay.
Okay. And as per my information, there is only 10-minute time. I may delete some slides to explain. So I will pronounce slide number. Go to slide number 11 or 12 like that.
Doesn't matter. Okay.
Got it, sir. Thank you. Sir, expected time for.
One more thing, Dada Sahib, one more thing. In the panel discussions, you will be joining, right?
No. Siddharth sir will not join, and I will also not join.
Acha, you don't want to join, huh? Okay.
So, sir, there are eminent personalities, sir. I can present it. I will listen panel discussions. Sir.
Okay then, no problem. Okay, thank you. Huh? So we will join after lunch. Okay.
Good afternoon. Dear participants, welcome back. Dear participants, welcome back after lunch for the last technical session. To chair this last technical session, we have with us Dr. P.S. Goyal. I kindly request Dr. P.S. Goyal to come on to dais and chair this. And it's my proud privilege to introduce Dr. Goyal to this workshop participants. Dr. P.S. Goyal holds PhD from Bangalore University, started his illustrious career at ISRO. He was part of major ISRO programs. To name few, Aryabhatta project, Bhaskara 1 and 2, Rohini series satellite, Apple and Insight 2 series. He was the director of ISRO Satellite Center, ISAT, during 1997 to 2005. Later, he moved to Delhi as the Secretary, Department of Ocean Development. Under his dynamic leadership, the department was transformed into Ministry of Health Science by integrating ocean, atmosphere, geosciences, and technology. Dr. Goyal served in various prestigious posts. To name few: Chairman, RAC DRDO, Member, National Security Advisory Board, President, Indian National Academy of Engineering, DRDO Chair at RCI, Hyderabad, and many more. Dr. Goyal is decorated with many awards. To name few: Padma Shri 2001, Distinguished Scientist Award by DRDO, Distinguished Scientist Award by ISRO, Lifetime Achievement Award, INEE. With this brief introduction, I kindly request Dr. Goyal to moderate this session.
Good afternoon to all of you. Thank you for giving this opportunity to be part of this interesting and educative. This session, 6, fuel cell and management systems of the larger session, 7 presentations. My request to all the people, number one, that your normal classroom type of lectures which have been there appears to. Because we expect that all the people here are knowledgeable, they understand basic things. Kindly limit your presentations to the subject, because it's not just fuel cell and management systems, it's fuel cell and management system, the context of an aircraft, whether it's Hansa, whether it's RTA, whatever it is. So we would request your wisdom, your knowledge, your contributions which you have made in this field to be presented here, and how your knowledge or your wisdom can help in this national endeavor, which is very important for the country for the coming decades. So this is my first request. Second thing is, please pardon me if I really see that tutorial type of thing going, I may intervene and say, please cut this slide. So I'm just taking this apology in advance, because time is short. We have run short of time because of the longer sessions earlier. So please be to the point. The 15 minutes session which are there, may kindly reduce your presentation time to about 10 to 12 minutes, because we give a few minutes for discussions also. The last thing would be that we would really try to give some recommendations to the, let's say, the country or the people like Dr. Saraj, who is in the Niti Aayog. How do we take this forward? So I would like you, in your conclusion, if you have to say something, then look, if we have to rely this electrical aircraft, this is what we need to do. So we need to be focused in your presentation, but particularly concluding part. So with these suggestions, we will start our first talk, which is on fuel cell and management systems. We have essentially Professor Sonde from IIT Delhi and Professor Atul from IIT Gandhinagar. So these two gentlemen will be making presentation. The time allotted is about 30 minutes, but I would really request you to limit both of you to 25 minutes, so that we have 5 minutes for discussions. Thank you. Please start.
Good afternoon, everybody. To Dr. Saraswat, Dr. Kota, Dr. Goyal, and Dr. Suresh, and Dr. Janav, and everyone here. So I'll, all of you, many of you know Professor Sunday, who is right now at IIT Delhi. He was at IIT Thermax before, working on fuel cell IIP for Indian Navy, and also on the NMC program, HTPEM, and methanol powered HTPEM, and so on. And I was at IIT Gandhinagar, also in some ways involved with the Thermax project, especially with the reformer, etc., and doing other projects which hopefully will show in the course of this presentation. Without further, I'll just jump straight to it. Yeah, that's fine. So this is what, can everybody hear me? Okay. So this is what we worked with Dr. Kota and Dr. Pashilkar and Dr. Pankaj and his team. This is what we were given at the beginning. So this is the energy requirement and the thrust requirements at takeoff, flying, cruise, descent, and landing of the FC Hansa. That is the twin-seater Hansa. So there are certain power requirements of the avionics. Total power requirement at the propeller are required to be developed by the power pack is 78 kilowatt, 63, 39, and 3, while on these maneuvers are being handled. And so therefore, if you multiply the time, it becomes 400 watt hours, 17,000, 146,000, and 722. Total energy that is required for this four and something hours flight is about 164 kilowatt hour. And I would like to draw your attention to this particular part of the flight, which is the cruise. And if you divide 146 kilowatt hour divided by 39 or 40 kilowatt, you get basically a power requirement, energy requirement. If you have 40 kilowatt hour extra energy, you can go 1 hour more. So this is the conclusion from this table. So that 40 kilowatt hour is basically 142 megajoule. This is the, in terms of joule, the number of joules that you need to go 1 more extra hour. This is not the power. This is 1 extra. Then going by the heating value of hydrogen being 142, let's say 50% efficiency, we have 71 megajoule per each kg of hydrogen. Then the additional hydrogen that is required is 2 kg for every 1 hour of extra flight. And considering that, let's say we have pressurized hydrogen and it's 5 weight percent, then we have additional weight of the hydrogen container for 1 hour of additional flight is about 40 kg. With 200 watt hour per kg, if we go with current values, 200 watt hour per kg, and from the morning's presentation, 200 watt hour is possible, but when you package it, etc., there were challenges that we saw. Even with that number, you are at 200 kg. So that's just for comparison. This 40 kg in terms of weight increase for every 1 hour weight increase can be overcome. This is not the absolute limit. This can be overcome by doing other things. And Professor Sonde might talk about a couple of other things that we have thought about. So what we have done in terms of sizing this fuel cell system is we have chosen a fuel cell that delivers 60 kilowatt gross power. And roughly the parasitic requirements is between 5 and 10 kilowatt. So net power delivered by the fuel cell is around 50 to 55 kilowatt. And we have chosen a 4.5 kilowatt hour battery to hybridize this fuel cell. And with all the budget of the weight and the volume, we were able to carry about 2.9 kgs of hydrogen with a 42 kilogram cylinder, that is type 4. And so with this configuration, we were able to get to 123 kg of the entire power pack weight, excluding the electric. So this is the final weight of this. And we were able to get cruise time of 1.23 hours. Now, there are a lot of improvements possible over and above this. This is where we are today. There's a lot of improvements that can be done. We can get to higher times, and we'll talk about a few of those. As I said, for higher cruise and flight times, we have to do a lot of optimization, system engineering. Today, for example, we chose a compressor that was that is readily available, whereas and it straddles the flow rates that we have. So if we want to optimize or custom make the compressor, then we were able to reduce the weight fall. So this is just one example of what we can do. And weight increases. Yesterday there was that 750 kilograms is not the absolute limit, and it can be relaxed a little bit. That also can be considered. And for longer haul flights, then it becomes more and more attractive to have hydrogen-powered fuel cell systems. So this is the volume. We were initially given about 0.62 meter cube, and we understood that that was the cuboidal volume. That was not the volume that is inside the cowling. And so we sort of understood how to make that cowling, and then we said available volume is 0.56, and the weight restriction was 157, including the electric motors. Excluding that was 132 kg. So this was the constraints that we went with. And inside volume is around 0.35 meter cube. So it's not 0.62 meter cube. It's only about 50% of that is inside this cowling. And we have enough space. We will show you the CAD layout later. We have enough space to put the propeller and the electric motors after putting the fuel cell system. So this is, we constructed the CAD model out of this, and then so this was the total LBH, and out of that, the cowling volume, as I said, was about 376 liters that was available to us. Now, this is a very diverse field. I'll just spend half a minute on this. I would like to draw your attention to the characteristics of a fuel cell. So this is voltage on the y-axis and current density on the x-axis. This is very similar to the PI curve that was shown for battery before, but the characteristics are very different, and the implications are a lot more profound in case of fuel cells. So as you start drawing current, open circuit, zero current, as you start drawing current, the voltage drops, and ultimately it drops to zero. And this is current density, not exactly current, multiplied by the area to get the total current. And the power, that is basically V multiplied by J multiplied by the area, will give you the power. So that is power density here under vector. So in fuel cells, the voltage is directly proportional to the efficiency. So the higher the voltage, the higher the efficiency. And the current is directly proportional to the hydrogen consumption. If you draw more current or current density, then your consumption of hydrogen will be higher. So I want, for example, a certain power, I want it as high a voltage and as lower current. So, for example, if I'm at B, I would like to move to A. And that means reducing power. It does seem like I'm reducing power, but if I have a larger fuel cell, then I can operate at A and still get the same power because the area is multiplied with the power. So these are some of the implications of this VI curve, and Professor Sunday will talk a little more detail and show you one example of how profound this is. And so the key to fuel cell system engineering as well as management and operation is to save on parasitic power, because we have a disproportionate advantage by saving parasitic power. It's not just if I save 10% power, I gain 10% efficiency. I gain much more. So and oversize the fuel cell stack, because as we have seen, the fuel cell stack is one of the least bulky components and weighty components of the system. So we can oversize it, thereby gaining efficiency and therefore dropping the hydrogen requirement for a particular cruise duration. So with this and this schematic, this is gross power, parasitic power, that is the compressors, the motors, and the other things that draw power away from the net power that is delivered to the propeller. Now, some of the requirements which are probably due to people working on batteries is that having a fuel cell there alone is not enough. We need to provide humidification to the anode flow, that is the fuel, hydrogen, and also the cathode. And amount of humidification can vary from cell to cell, from membrane to membrane. But overall, humidification is necessary, and this we need to be thought about and built into the system design itself. And obviously, it adds to the weight and volume. And cathode air supply is typically forced into the cathode, and that is at about 2 to 2.5 bar absolute. and that requires a fan or a blower. Depending on the input pressure, it might also require a compressor. And the stack, because the efficiency is not 100%, the rest of it is heat. We need to manage that heat, otherwise it will overheat and the membranes will stop working and so on. And number of other components like compressor, the power electronics also need cooling. And so thermal management is very key in this whole engine. And parasitic power, as I said in the last slide, is also key. And as long as we can operate at part load, less than nominal capacity, then we are excellent. So this is the PMID that we came up with. It contains 3 or 4 innovations in addition to the normal PNID where you have just hydrogen, oxygen supplied with each other and so on. We have economized on the number of heat exchangers. We have optimized some water loops, and we have done a couple of other things to reduce the weight and the volume and the number of items in this whole system. And we have identified the operating conditions for each of these components and systems. But this is not, just to give you one example, this is not a fixed operating point. When it comes to part load, these operating points will change, and so we need to very carefully engineer the system. So ultimately, this fuel cell system is not the fuel cell connected to a hydrogen tank. It is the stack, the air compressor, the heat exchangers to manage the heat, the radiator, the humidifier, as I said, and an expansion tank for the water loops and so on, and anode recirculation. So typically, more hydrogen is supplied to the stack than what is used by the stack. So there is an unused hydrogen that comes out of the stack on the other side, and so we need to recirculate that back into the input, and that requires a pump. We are considering alternatives to that. We are seeing whether we can get away not having a pump, and of course it needs to be hybridized with a battery, smaller one. And just our recent discussions showed us that perhaps hybridizing with a supercapacitor may be a better idea as compared to a battery, but we are still exploring that out. And of course, the propeller and the balance of plant. There's a differential voltage DC that comes, and that need to be converted to a fixed voltage DC, and so that requires power electronics and so on. And of course, the hydrogen cylinder, which is the kind of the bulkiest component in this. With that, I hand over to Professor Sonde, who will.
Well, before Professor Sonde starts, I just want to make an observation that this is one of the most real-time optimization I have seen in my life at the systems level. Before yesterday, the stack was 40 kilowatt. Yesterday it was 50 kilowatt, and today it has become 60 kilowatt. I understand the reason, because you are sacrificing higher weight on the stack, but gaining more on hydrogen because it's 1:20 ratio. Yes. So I understand that. Yes. But this is something most dynamic exercise I can recall in engineering practices. Thank you. Dynamic.
Thank you. In fact,
I started correctly.
Yes, absolutely.
Yes, with purpose. We are doing it with purpose. Because we want to be really now, because we are moving towards the optima, going to a non-linear optimization. Thank you. If I just completed the presentation part, I don't have to add. I only go to the last part, what Dr. Goyal talked about, what we do from here. Because this particular thing is done, but I mean, everything is fuel cell, but there's a whole lot of system, and a lot of innovations are required with that. And that is what, thanks to Dr. Kota Arina and Dr. Goyal, for the last 6 months, I think Kota Arina must have been contacting us so often. We have been having discussions. So important because instead of hearing some people saying that this is a reverse flow of technology from a land-based thing to a air-based thing, because normally the high technology comes from the space and they go down to the earth. I would like to differ, because design of a fuel cell system and philosophy design point in FC for a propulsion is very different than the choice of a fuel cell for a land-based mobility. Now, I'm not going to the details like this, but operating point in a fuel cell is chosen to get a higher point during the short-term takeoff. The engineer's point is chosen at the lowest current density. That's why he's saying we are moving it. Because we're feeling that for every kg of fuel cell that we put, because today we can pump 4 kilowatts of power in 1 kg, but the amount of saving that we get by putting this 1 kilowatt, which would mean about 0.25 kg of a fuel cell, you can actually save about 2 kgs of weight, because that's not saving the hydrogen will give you a much larger benefit, as he says, disproportionate benefit by putting, and therefore the question is now, as he said, are we stopping at 60? No, we will not stop at 60. We may go a little more higher. Most important thing is the cost of the fuel cell, because we're not talking about cost of fuel cell. The fuel cell cost is, anyway, if I tell the number, maybe 1.5 lakhs a kilowatt. So when I say from a 50 kilowatt to a 60 kilowatt, that means additional 10 kilowatt would mean 15 lakhs of additional money that I have to spend, and hydrogen is going to be cheaper. Hydrogen may come down to, let's say, 200 rupees, 300 rupees. I know it's about 450 rupees, and therefore we have to, when you do the cost optimization, I may go back from 60 back to 55 or something. So this is, again, we may go 2 steps further and we may come back when the cost matrix will come into a discussion. I'm just trying to give you the dimension, because once we sit to a final thing, this will come up, as I'm saying, that whether we operate at point B or point A is extremely important to ensure that this thing, and I'm completely cognizant of the fact that levelized cost of propulsion energy is very important, and when degradation and end of life is concerned. Now, end of the life, again, I want to bring in that if you're operating at point B, the end of the life is much better than operating at point A. That means higher the current density, my degradation potential is much faster. Therefore, when I look at that, you're getting efficiency and you get a better life or a levelized cost, and therefore sizing the fuel cell, the initial cost may become 15 lakhs, but in terms of the overall levelized cost, it works out. So I'm again not getting the discussions. No, I'm done. Thank you. Now, this is another important revelation. What happens in case of a land-based mobility is that the fuel cell weight and the battery weight is almost equal to the 50% or even more than the weight of the rest of the truck or commercial vehicle or a car. Therefore, you have to be very careful that you reduce that particular thing, because it would, the cost of that particular thing will be more than, I mean, today we talk about a truck, the battery is going to be about 8 crores, whereas the cost of the truck may be 2 crores. Whereas in case of a fuel cell in a aircraft, you will see when we did this kind of a budgeting of every component which goes into that, you realize that the fuel cell forms only 10% of the weight of the entire system. 10% of the weight. And therefore, adding little more to the fuel cell, if I'm able to bring down the cost of the fuel cell to maybe less than 50,000 rupees a kilowatt, is a much better exercise. And our effort, what we have done now, is we are okay with 4 kilowatts of per kg. There are 7 kilowatts per kg fuel cells are available. But because we demanded 4 kilowatts per kg of the fuel cell, which is, I mean, if you compare a gas turbine, how much kilowatts you put in 1 kg? Yeah.
Maybe 5-6 times minimum.
5-6 times. So it will be 0.8 kilowatts per kg in case of gas turbine. So you are able to pump 4 kilowatts in a fuel cell, which shows it's about 6 times more. If you take the internal combustion range is about 8 to 9 times. So it shows that our efforts now, what Cathode was saying, is that how do you really reduce this particular thing? So as he's saying, for every kilowatt added to a fuel cell charge will enable a reduction of a net weight by more than 0.4 kg due to savings in hydrogen. That is one lever that we have got. And second lever is that we started with 156 kg and today we have come down to a level of 125 kg. And how we have done that, I will explain that and I will close this discussion. We have done many innovations. In fact, they are all work of intellectual property, but I'm taking this with a fond hope that this will remain in the house and we would like to do that. We have made a combined water system. We are doing a heat exchanger and humidifiers. Some modification. Hydrogen distributor pump, we may use an ejector. We may use expansion tank of different types. So that is what it is. So we have done this. But I just want to go to So here, I mean, I'm just saying here, we are not thinking that there is a cooling circuit and there is a humidification circuit, as you see here. So you can see this, right? It's like cooling. We are combining it. We are combining the humidification to the cooling aspect of it. That reduces the weight by about 15 kgs. So the way that we have been able to do is to bring out this particular modification. Yeah. So similarly, the thermal management system, we also made changes. We are ensuring that the degradation of fuel cell is minimized by reducing the shock loading to the fuel cells. That's one of the most important, because
very often we cannot take the current performance, we have to take the end of the life performance, and therefore by operating the right point of the fuel cell, we have reduced the shock loading of the fuel cell stack and therefore the rate of degradation. The control system will need AML-based control, so a lot of simulations are required to be done. So work while doing AIP, and I'm so glad that my guru, Dr. Saraswat, is here. I was just hoping that he will come back in 2011 when he was the essay. He said, so that please come, let us build this and into the proportion, which now we are so proud. That has been given first time in the country. Many of you may not be knowing now that it is open information. We know this. So this is, yeah, welcome to that. So this is the 320 kilowatt AIP, which it has a fuel cell, with the first fuel cell, let's say the TRL-9. All goes to this person here, and endurance mode versus compact mode. Exactly the same thing like Hansa we are designing. There are two. One operates as a combined. Endurance mode is about 212 kilowatts, and a compact mode is about 320 kilowatts. So this is the design. We are inspired of Hansa design. Whatever size that was Atul showed is on that particular thing, and very nice. I mean, I'm sorry, this is just a small promotion that I'm doing it to the work we have done. That this was showcased. India, there are only 4 countries which have developed this AIP on a fuel cell, and we are the ones who have developed this, when Nano has displayed and Navy has agreed to that. Similarly, he has built his 30 kilowatt design. These are the common again for DRDO, which I'll tell you later on how it will be utilized. This is my other contribution with your own sister laboratories, NCL, and Secretary, and we built this another item person. Now, right now, the fuel that we have provided is a low temperature fuel for Hansa. Probably for a period of time, we will migrate from a low temperature fuel cell to a high temperature fuel cell. The beauty, you don't need humidification, you don't need a purity of hydrogen, you can do a reformer, and that is something which again me and Dr. Saraswat share a common demand. Whenever you won't be responsible that you are not doing enough for the reformer, and I'm going to be talking about this in just as a concluding part. So, like the way that we have done a way forward, there's just 1 minute, sir, I'll complete the one. The goal is to develop. The way forward is that we need, let's say, 60 kilowatt. It may kind of converge maybe between 50 and 60 kilowatt system for our Hansa. We will like to first build a 10 kilowatt line-based system as a prototype, integrating all the concepts. All those 6 concepts that we have indicated, integrated. We will bring out all the central weaknesses in the entire system, including the degradation behavior. And I give an enormous amount of emphasis on degradation. If I learn one thing of AIP is that human cells are operating in series. The diagnostic features of a fuel cell is very different than the diagnostic feature that we employ in the battery. And that again goes to the entire polarization curve. If you have to look at it, it is a very different subject I'm not touching. And therefore, we want to test all these things at about 10 kilowatt scale so that we can build a 60 kilowatt scale. And here we can, when we started, when Dr. Saraswat called us, we started at 9 kilowatt, went to 120 kilowatt, 120 kilowatt by going 9 kilowatt to 14 kilowatts, a lot of changes in the catalyst and I think we did. Then and we built 320 kilowatt full system on a land missile. So this is the kind of a trajectory I'm inspired with what we should say. Fuel cell innovation for next version. I know chairman of this session says just focus on Hansa, but I want to tell you, sir, that we would like to look at this thermal methods to be used for the space condition requirement in RTA. So next Saras or RTA will require Hansa may not be required, and for that we can use the heat of the fuel cell. Right now we are just rejecting the heat into the cavity. We can use that to generate the space conditioning energy required. In case of the battery, for space conditioning, you have to put additional battery, as I said, 40 kg versus 200 kg. I think that whether battery or fuel cell, I think we have put a final nail to that. The battery fuel cell is 3 times going to be superior to battery, but it's going to be much better if you want additional energy. And in case of battery system, you need it. Hydrogen using fuel process, which can give a better hydrogen gravimetric density and reduce the weight by more than half. Today, for every kg of hydrogen, we carry about 16 kg of the dead weight, and that, if you are going to have an onboard reformer, my own, we have done a lot of analysis, can be brought up to 8 kg.
And you don't need a pure hydrogen, you are going to put a hydrogen. So there are enormous options to optimize further. I mean, hydrogen can give you almost for 1 kg of hydrogen, you just need about 6 kg of weight. So that's another level, but for the infrastructure and the cost of hydrogen is composite based, I must say. I think I'm standing in a place where carbon nanofibers and so much of the composite works, I think is going to be entirely will be based on MOC for high pressure and low pressure system. And beautiful what Arun said yesterday, productization of our thing. In fact, ARP, we took a lot of time to productize this thing. And his modification, I'm using this word, modification of that will be one of the important aspects. So these are the 5 beyond our Hansa that we would like to do. So next step is land-based product development, 10 kilowatts, demonstrate weight and volume per hierarchical sets, demonstrate design efficiency, reliability, supply chain customization, demonstrate control algorithm and software, demonstrate ability to meet standards and regulations. In parallel, development of a airworthy fuel cell system. Bye. Thank you. Thank you.
Well, thank you very much. Very nice presentation. Now the floor is open for questions and clarifications. Any questions? Yeah. Go ahead.
So 5-8% of the hydrogen, compressed hydrogen, is the total unit volume. If I have a if I have a 100 kg hydrogen tank, 5 kg is hydrogen, 95 kg is the tank. That, sir, it can go up for type 4.
20 kg, 60 kg is what I'm saying.
You can go up 7. You can go up to 7-8%, but that is type 3 cylinder, 350 bar. But that volume is it?
No. I'm talking about 4 cylinder, which is 700 bars pressure. What is the kind of
5 to 6-8%, not more.
No, I'll tell you, I've done a lot of work on that when we did Upper Bhaskara satellite itself. Actually, best cylinder efficiency for hydrogen is 1:5 only. You cannot have better than that. And that is best with composite, with the reinforcing, with the sealing and all that. Nothing better can be achieved. You are running pressurized gas. It doesn't matter what pressure, 350 same, 700 same. Volume will increase, but weight you will not gain. So that is the. No. We will
from 350 bar cylinder to 750 bar cylinder. Particularly type of cylinder where everything is polymeric and carbon. This significantly no. No. Yes. I'm going to for the land system. API for the land system.
We'll do that. We have gone by a couple of different manufacturers, and they each are not exceeding 6%.
It cannot change. We can discuss that. It is basically physics. It comes from physics. It will remain the same. Because of that, your cost thickness increases proportionally.
It is not actually proportional because type 3 cylinder uses metallic liners and
see you
fiber. There is a lot of difference.
You compare metal to metal or polymer to polymer.
Data is metal to metal. My data is metal to polymer.
No, it is not polymer to polymer to polymer. If you design a polymer for 350, then and if you design a polymer for 700, your weight will remain same, but volume will come down. Kindly look at it in the basic physics. Okay, will any other question? Yeah, there is a question. We are talking 700 bar only now.
No. That is one. Second one is it has to be type 4 cylinder, no metallic cylinder.
I personally believe your choice right from the beginning should be a high temperature fuel cell.
Very good, very good.
Because that is going to give you tremendous advantage in terms of de-electrification, this, that, and all that. All the parameters what we are doing will be out. Fourth one is air compressor what we are talking about. That we should look at how to manage the airflow.
Yes. Yes.
Whether we can have a control system for giving you the airflow.
No, we are talking Ramjet. What I was just talking about. Yes, sir, you can even get Ramjet. This is a very small nothing is required. Yeah. So mention that point. I forgot to mention this. And I know the conference will come. So there is yes,
Yeah, we discussed that yesterday.
okay.
Today, as far as 120 degree fuel cell is concerned,
160.
160 120 to 160 is available today.
Sir, only one thing is, only that more per kg, whatever is required to maintain titanium as a byproduct case and not like the right paper. Today, one certainly is giving what you have been always learning and what we developed under the Nmc. It's still about 0.8 kilowatt per kg. I'm telling you, that's because of the fact that at a high temperature, because of the compressor stand and the way that you are designed that stack, I'm not going into the details. Reaching at 4 kilowatts per kg is going to be still challenging. In fact, the first number that I gave it to me changed upload of the same, when it's going to be 0.8 kilowatt per kg, which is almost similar to what is present in the current combustion or a propulsion based system. So my only submission to you is that I am a strong champion for a PBR based and an FM membrane. All the complexity of humidification and the purification of hydrogen and everything goes away. I'm okay to get even the degradation performance. Maybe I can get about 10 microwatts per hour in case of AC converter as compared to power in the heavier cells. But my only question remains is that start and stop, because every start and stop,
one recommendation which we have made is to go for a low current test. But you are shifting the.
Yeah.
You are saying.
So the point
A. You should be at the point A.
Yeah.
Yes, it is the preferred point. Low current testing for the start. You will have serious problems on current when it is gone.
It has mentioned this.
So that part has to be taken care of, whether the start has to be either supported by a supercapacitor or something or.
Yeah, you know.
Moment is.
Yeah.
So, but that then you have to see the optimizing. Whether the additional battery for supercapacitor are no problem. It will not increase rates of the.
But supercapacitor will be only very short, only specified. Yeah. Starting point.
Yeah. No problem. But only point is that when I go here, point A, I would need my weight of the fuel cell to be maintained, and if not more, at least 2.5 kilowatts per kg. Just keep it in your mind, sir. I may not be able to get it from my HP pencil. So that is one point. No, wait. So then what happens? Right now, my budget for fuel cell is just about 12%. So I could get at 4 kilowatts. But if it becomes 2, then my budget fuel cell will become higher. And then I may again go back to a 40 kilowatt and a 60 kilowatt.
So that is for aircraft. Land-based systems, people are preferring to go for high current.
Yes, they are going to go for it. They are here.
Some of the latest ones that have come here.
Toyota, sir, they want the fuel cell to be replacing money. They won't make money.
480, 500, that's right.
The degradation potential is higher. The fuel cell is very tiny. You can put it in a passenger vehicle, but the only thing which is hybrid there is that your rate of degradation of fuel cell is so much because you are now at the mass of the level. You are not even in the this is the activation, this is the roaming, and the liquid spot when I say, and when you come here, the way that the electroactivity loss in the system is going to bring down the degradation. You will have to replace the fuel cell faster. And that is meaning a cost, unit cost will be very high.
That is seller's design.
I say this because I'm saying for our aircraft, we should not be inspired by what is being done in the battery systems. This, yes, I think very low. 48%. This is 60%. This is how much
0.8 will be around 65.
65 to 70. B2A. B2A, you will get about 80% higher efficiency. No, B is higher. A is higher efficiency. Efficiency, no. A is higher efficiency. I have NDF by Okay.
Yes,
Yeah.
You know what is different from the voltage?
Hold it. Yeah, like it says, your power will increase, efficiency will come down. And they are already here. Sorry, right. Now you listen to our subsequent presentation, they will operate here. And I'm going for answer, I'll operate here. Sir, Jadhav has some, you want to ask me? Okay, go ahead.
This one, the cathode compressor flow which you mentioned, for aircraft applications, will it be required from the flight angle? It's only for finished lighting.
No, it will be as long as the fuel cell needs to work, you need to continuously supply air.
But we can't draw air from the aircraft is flying.
We can. That was the discussion.
The back pressure. The pressure drop in the system.
Yeah.
The pressure drop in.
What is the rating of lower of the pressure which you mentioned?
So we need to do about 0.5 kgs per second. That is the flow rate that we do.
But the pressure?
Pressure is 2.5 bar delivery.
You won't get in it. Civil aircraft going on.
It's a compressor.
But it can aid us, and then we'll have a smaller blower or a smaller.
So the optimization of this one will be a challenge for aircraft.
Yes.
That's all I want.
Okay, let's thank Dr. Sonde and Professor Atul for the very nice presentation, very relevant presentation, because you are suffering from time. You'll have to intervene and say, stop it now. Thank you so much. Sorry, I hold it because we have to move forward. One. Next presentation is online. The presentation is by Professor Tejas Kshatriya, Head of the Powertrain and Alternate Fuel Cell Department of KPIT. It's on fuel cell and management systems. We have allotted around 15 minutes for this particular presentation. My request to you will be that kindly try to complete your presentation within about 10 minutes or so. Professor Ravi Pandit, he is a member of the core group of Automotive Research Program Committee of Government of India, initially for the, yeah.
Yes, I'm there.
Okay, I think that you proceed, Mr. Kshatriya, please go ahead.
Sure, thank you. So am I audible? Can you hear me clearly? Okay, great. So good afternoon, everyone, and thank you very much for this opportunity. Based on the meeting that we had sometime last month, we have been given this opportunity to present our capabilities and the work that we have done in the automotive domain. And I'm sure there have been a lot of innovation. We have been doing a lot of technology work, and we believe that a lot of things can be applied to aircraft domain. We are very new to aircraft domain. So this presentation mostly talks about our capabilities and the work that we have done in the electric powertrain. In yesterday's, like the session that were conducted yesterday and today, we have noted down certain of the specifications, some of the details and the challenges in the aircraft, especially the specifications of Hansa. And we believe that with optimizations, certainly we will be able to apply the technology that we have developed indigenously in India for aircraft application. Yeah, can you go to the next slide, please? Yeah, this is our office. We are looking at. Can you go to the next slide? So KPIT is a technology company. We work on cutting edge technologies in electric vehicle powertrain, energy storage. We are developing a tunable sodium ion battery chemistry. We have done some excellent on hydrogen generation. We have developed a ground up low temperature PEM fuel cell for automotive and stationary power generation. This project was undertaken under Nmc CSIR's Nmc initiative and was done jointly between CSIR, SICRI and CL and KPIT. We are not a manufacturing company. We partner with manufacturers for production. Next slide, please. Just a very 30-second view about KPIT. Will not spend much time. We are 100% focused on automotive technologies. 7,000 plus people. Have won several innovation awards. We have 50 plus patents in the field of electric vehicle, electric powertrain, battery, state of charge, state of health, fuel cell, and battery chemistry. Yeah. Can you go to the next slide, please? We are located in US, Europe, and Asia. These are our offices. Next slide, please. These are the customers that we work. We work with all the global customers. We do a lot of work in ADAS system, advanced driver assist system, autonomous vehicles, and powertrain for a lot of EV companies and tier ones. Yeah, go to the next slide, please. Hydrogen for transportation. This is the point of discussion. Yeah. Can you go to the next slide, please? I did not stress on why hydrogen is becoming like the future, the fuel of the future, right? It has the highest energy density, 3 times of fossil fuel. Carbon neutral if generated through renewable sources. Fuel cell, the efficiency is around 50%, and conventional efficiency, we have seen it's in the range of 30-35% for the IC engines. Therefore, in terms of efficiency, fuel cell seems to be much more efficient as compared to IC engines. Of course, the emission is the biggest advantage because the output of a fuel cell is electricity and pure water vapors. Right. So from the automotive context, the world is moving towards.
We understand all this. Please go ahead with respect to our activity of the branch bit. I mean,
okay. Okay, fine, sure. Can you go to the next slide, please? Right. So this is something which is relevant for an electric aircraft perspective. If you look at the critical components that are required in any powertrain, we have designed, developed, and built those components in-house in India. I'll have more details about the fuel cell in the subsequent slides. But from the powertrain perspective, and a fuel cell electric power perspective, you need to have a DC-DC converter which will basically match the fuel cell voltage to the DC bus voltage. So this is mostly a boost type DC-DC converter, high power, high current step-up converter. So this is something that we have developed in-house. The module size is around 50 kilowatts, 50 kilowatts, and multiple such models can be combined to achieve higher power ratings. The input of this can be in the range of 150 to say 450 volts, and the output could be in the range of 650 to 1000 volts. We have designed our own induction motor. Again, this is from an automotive perspective. These motors are highly efficient at low speed and very high torque kind of application. We have designed, developed our own motor controller to drive these motors. This motor and the controller, the power ranges that we have are ranging from 60 kilowatt to 250 kilowatts of power, operating at 650 volts. It can be as low as 500 volts to maybe 800 volts. That would be the range. We have done a lot of work on the battery pack. We have been running our electric buses in the country since 2016 under various operating conditions, and done a lot of interesting work on the thermal management of the batteries, which is extremely important to make sure that the batteries are operated safely and we are able to get the required life from the cells. Now, this is again a liquid cooling system. We have developed the plates are mounted inside the battery pack, and the coolant is passed into these plates. It's a chiller-based system. We are maintaining the battery pack temperature under 32 to 35 degrees under all operating conditions, ambient conditions. So that is helping us achieve the cycle life of lithium iron phosphate and NMC battery pack in excess of 3,000 cycles at 1C charge and 1C discharge rate. The sixth is a summation gearbox. Now, this summation gearbox is again can be used to couple 2 or more motors, wherein the motors are controlled in torque mode, and we are able to get we are able to combine the torque and give it to the propeller shaft, the output of this gearbox. Again, this is very much relevant from heavy duty vehicle perspective. Number 7 is the BMS. BMS is one of the critical items to manage the battery pack cells. This BMS basically has a balancing capacity of 1 ampere. It has passive balancing. It can balance at 1 amperes of current. This is master slave configurable. It has 24 channel as voltage inputs and 10 channels temperature inputs. It has isolated CAN. This can be cascaded to achieve total bus voltage of up to 1,000 volts. So that was about the BMS. Vehicle ECUs, we have developed an electronic platform, a generic ECU platform. This platform has 30 to 40 analog inputs and around 8 to 10 digital inputs. It has onboard telematics. It has 3 isolated CAN ports. And this platform can be used to as a vehicle controller. It can be used as a multiplexer unit. It can be used as a charge control unit. The same thing can be extended as a fuel cell control ECU. Similarly, the BMS that I just mentioned, the same the BMS we are extending to be used as a fuel cell monitoring system, wherein we are monitoring 5 cells in a group of 5. So at any point in time, we have a clear understanding of what the operating voltage of each group of cells within the stack. Now, if we are able to combine all these technologies together and build a powertrain, we have been able to achieve best-in-class efficiency, which is 15 to 20% lower in terms of energy consumptions. We believe that this is something very critical for an aircraft application because system efficiency has direct impact on the battery pack, on the hydrogen storage. About the percentage for hydrogen storage, which is just 5%. So that would be a significant saving in terms of volume and in terms of weight. Can you please go to the next slide? Just a diagram of how fuel cell system is packaged on a bus. Yeah. Next slide, please. This is the low temperature fuel cell that we have developed. This stack can be scaled from 30 kilowatt right up to 200 kilowatts. We have developed the entire fuel cell right from the metal bipolar plates. It uses metal bipolar plates. The precursors like the catalyst and the membrane obviously need to be imported right now. But beyond that, all the processing has been done here. The bipolar plate design has been done in such a way that we are able to use the commonly available stamping processes to make these bipolar plates. Again, fuel cell for an automotive perspective is targeted for long range vehicles. The current solution or the current fuel cell system that we have developed, the cost is around 60% of the currently available stacks in the market. That is a USP. So even for a small volume, there's a significant savings in terms of cost. We plan to get into commercial production in next 8 to 12 months. Next slide, please. Again, this is a typical layout of a fuel cell stack along with the balance of plant, which goes on to an automotive application. It comprises of the air filters, which can filter out the pollutants. It has a compressor to compress the air, then an intercooler to cool the air, and thereafter there's a humidifier through which it's a gas-to-gas humidifier through which the air goes to the fuel cell stack. Each stack has its own control unit which sits on top of the stack, and apart from the control unit, it has the cell monitoring unit, which basically monitors the cell voltages and temperatures across the stack in different zones and provides real-time information for the stack control unit to take the relevant action and communicate with the vehicle control unit. Yeah, next slide, please. This is a picture of the hydrogen storage tanks which we are currently using, and we will be discussing about this tank in the previous presentation. If you see this Type 3 cylinder, water volume of 318 liters, it weighs 145.7 kgs with 7.7 kgs of hydrogen. So if you calculate, like we just discussed in the last meeting, last discussion, the weight percentage is around 5%. So we use these cylinders on the bus. In October 2020, we built our first fuel cell in collaboration with NCL and CIRI, and which was demonstrated on an electric car. Subsequently, we have developed a larger stack, 30 kilowatt and multiples of 30 kilowatt, which we have now demonstrated on our fuel cell bus in the month of December 2021. Slide, please. We are working on a couple of technologies for hydrogen generation. This particular technology is based on microbial culture that we have developed, which can be used to convert biomass into hydrogen. 50 kgs of biomass can give us 1.2 kgs of hydrogen. We have done the pilot for this, and we would be getting into commercial scale production in next 8 to 10 months. Yeah. Next slide, please. This is another technology for hydrogen H2 generation, which is gasification of mass. In this case, the woody mass can be used, such as soya stalk, cotton stalk, bamboo, municipal solid waste, etc. Biomass is gasified, and the gas is further processed to generate hydrogen. Again, we have made a pilot plant for this, and we are expecting to like this in next 3 months of time.
Please come back to what you would like to do in the context of this. I mean, we know all these developments. Tell us what exactly you would like to do in the context of the aircraft or against electrical propulsion for aircraft.
Right. So we would like to get involved in basically creating a solution for hydrogen PMLT fuel cell for a propulsion like Hansa. We have captured some of the specifications, so we would like to run some simulation and come up with the right size for the stack and for the battery pack to give the required power and the range for the Hansa aircraft. I think between yesterday's and today's discussion, we have enough information about the Hansa aircraft, and we would be glad to do some simulation, some base work, and come up with a potential solution for hydrogen fuel cell system for Hansa.
Thank you, Mr. Kshatriya, for a very nice presentation. I would invite now any questions, just one or two, because we are running short of time. So, one thing I note here is from your presentation that you have got a lot of strength in terms of system engineering, in terms of fuel cell design, development. I'm not very sure. You said you are not producing, but then we have to really find a production partner. Otherwise, it's not complete. Also, you have said that you have made tanks for the hydrogen, which again also looks like the same ratio of 20 kg per kilogram of hydrogen, which looks very pleasant. So we will. I think what message we take from here is that you have these capabilities, and these capabilities can be utilized by Project Hansa or in future in terms of the electrical aircraft propulsion. Thank you very much.
Just a couple of points here.
Kilowatt fuel cell. What is the weight and volume?
See, we got a lot of data from you, but we did not get the numbers. All your presentation, when you say fuel cell, what is the weight, what is the efficiency, these numbers. So maybe fuel cell efficiency you can tell us right now, and also we will be very happy if you can give the quantitative numbers to, let's say, our friends at Daniel. Volume.
Sure. So in terms of electrical efficiency, we are in the range of 48 to 55% as of now. That is in terms of electrical efficiency. In terms of gravimetric density, we are in the range of 2.5 to 3 kilowatt per kg.
Okay.
In terms of volumetric density, we are in the range of 2 to 2.5 now. Yeah, but we will be happy to share more details with you along with the working that we will do for Hansa. One more point I just want to address here is that just for the fuel cell part, we are not a manufacturing company, but having a fuel cell manufacturing ecosystem in India is going to be difficult. So only for the fuel cell part, we are getting ourselves into manufacturing. So we would be able to design, develop, manufacture, and supply the entire fuel cell system along with balance of plant for a given application. On the hydrogen cylinder part, we are not making them, we are currently buying them. I just wanted to show you a picture of a type 2 cylinder and the capacity about that.
See, these information is very important. We need that kind of way.
Yeah.
Thank you very much, Mr. Satya.
Thank you. Thank you so much for the opportunity. Thank you.
Okay, we move now to the next presentation. Next presentation is also online. Presentation is on fuel cell and management systems. Again, same topic. And this discussion is from Mr. Srijit. Mr. Srijit is a technical specialist in new power engineering at Cummins in India.
It's online, online.
It's online.
Mr. Srijit,
Good afternoon, sir. Hope I'm audible there.
please go ahead. You're audible.
Good afternoon, all. Greetings from Cummins India team. I would like to start by extending my sincere gratitude to all the dignitaries and the entire organizing committee of the esteemed CSIR-NAL management for giving Cummins India an opportunity to be a part of this workshop. It's our privilege to share an overview about the new power product portfolio to all the participants of this workshop. We'll go on to the next slide, sir. This is the brief agenda that we would like to cover. As I mean, the chair has advised, we will not take much time on the overview of the company history, vision, and then we'll try to focus more on what we have on offer as part of the clean energy transition in India, as well as some of the applications that we have already done globally, which can be a potential reference.
See, you can cut things like company history and all that.
Sure, sir. Yeah, I'll just glance through this. So powering a more prosperous world is what, as a company, the mission statement is. We operate in almost 190 countries and have a legacy of almost 100 plus years in the industry. We are known as a diesel engine manufacturer in the industry, but I mean, we are venturing into the new power technology right now. These are the key business units that we have. We are majorly known as an engine and power system company, but right now we want to just highlight the fact that in addition to all these 4 existing business units, we have launched a new business unit termed as New Power, where we are also offering battery electrified powertrain solutions to the end customers. Yeah, we can move on, sir. We have started in 1919 and the company has a history of more than 100 years, as we told, especially in the diesel engine segment. We will not touch here. Yeah. So as a company, we have a vision for 2020 that is basically to drive a change for a healthy planet. So we believe that as a company, we want to make the communities better where we operate. We want to be a part of the climate change to address that. And we also want to make sure that the natural resources are used in a sustainable way. That is what is setting up the Planet 2050 vision for us. So India specifically, we see that based on our understanding on the agreement that we had in the Paris Agreement and various missions like the National Hydrogen Mission and the Solar missions, we are striving towards that. We foresee some challenges here, essentially on the investment side, the maturity of the technology which is available here. We need to look up to the government to make sure that the policy framework is consistent and the incentivization that we do for the new power technologies are consistently maintained and the resources are available. So we hope that by collaborating with the government, industry and the research agencies like the CSIR, we can address this and then move ahead. So we believe that, typically 3 aspects we need to focus to move towards carbon neutrality, where we need to develop an ecosystem with a multi-stakeholder perspective. We need to carve out an attractive transition path, and then we need to deploy the technologies for the best use cases first. We can move on, sir. Yeah, so typically what we have on offer, we basically offer new power solutions in 3 categories. First is the electrified power, where we offer battery packs as a product to the customers. where right now we have already proven our battery packs in the commercial vehicle applications like the trucks, buses, as well as, I mean, we also have the off-highway solutions for the construction equipments, terminal tractors, as well as material handling equipments. Those are the battery packs solutions. We also have the fuel cell solutions, which are typically, offered again for similar on-highway and industrial applications. We are not into the aerospace application as such from a company perspective, but at least we have done few demonstrators there, and then we'd like to work closely for any opportunities upcoming in that direction. So in addition to these two, we are also into a hydrogen generation industry. The key purpose of why we are in here is that we believe that if fuel cell has to be successful in the industry, there should be sufficient infrastructure available for the fuel to be available in that particular market segment. So it is very essential that we need to have green hydrogen available as part of the fuel. So that's why we are there as part of the electrolyzer business also. So just to give you a glimpse about how an electrified powertrain is going to look like, we have shown two concepts architectures here. On the left side, we can see the fuel cell based hybrid electrified powertrain architecture, where we have a fuel cell, we have a DC-DC converter, a battery, a traction inverter, traction motor, and an e-axle. In case of a fully electrified powertrain, we have a prime source as the battery, the traction inverter, motor, and the e-axle.
In your
Absolutely,
presentation,
sure.
kindly emphasize what is being done in India and what is being done abroad.
Okay, sure, yeah. So typically, I mean, to be very specific to your question, sir, the key demonstrators that we have done are all, like abroad, and then mainly in the US market as well as in the Europe market. Right now, we are in collaboration with few OEMs in India also, so that we can take it to the demonstrator levels, and then those are actually yet to hit the field. So whatever application references we would like to show would be more from a global perspective, sir. So here we would like to just highlight the entire, well-to-wheel analysis, architecture here, where in order to hydrogen to become a clean energy source, we have to make sure that the hydrogen which is generated at the source is completely green. Because there are right now also hydrogen is getting generated, but there are the hydrogen getting generated as part of an oil refining process or a petroleum refining process may not be considered as a green hydrogen, and then we may not get the full advantage of the greenhouse gas emission offsetting that we are targeting for. So it's highly essential that we harness the hydrogen from the renewable sources of energy like the windmill, solar, as well as the hydroelectric power. And it is here our electrolyzer product comes as a handy option, where this gives us the flexibility to store the renewable energy that is getting generated and then can be used as a potential fuel for mobility, for industry, to gas application, and a power to power application, and many other use cases also. We just wanted to give an overall perspective of how a well-to-wheel sort of an analysis is being worked out here from an overall architecture perspective of how a green hydrogen is. So typically coming specifically to what we have on offer, these are again fuel cell offerings for mobility application, to be very specific. We have in our portfolio the fuel cell products ranging from 8.5 kilowatt power output to, it can go as high as 90 kilowatt. These are standard units. We can also couple these fuel cell modules so that we can generate a bigger power output capacity. So just to give you a glance on what are the capabilities of the fuel cell power modules that are on offer here. Just we have shared the key specifications like the overall envelope size, how much is the volume of the product, what could be the overall weight of the fuel cell power module along with the balance of plant. Again, what are the key operating current voltage ranges as well as the peak efficiencies of these models. So we would like to move on and then just show some references of the actual use cases which have hit in the field with respect to these fuel cell engines that we just saw earlier. So starting off with the commercial vehicle application, where we are already in as an industry leader. We have already demonstrated its towards scale initiative. This is basically done in US in collaboration with Navistar Trucks. We have used the HT45 fuel cell stacks based fuel cell engines on these trucks. These are basically powered by 90 power modules are being proven on the. So this is one use case in commercial vehicle. Probably if you can go on to the next slide, sir. We have also attempted a fuel cell based train application, like basically rail. This is basically proven in Europe, where we have worked with Alstom. Alstom is a rail coach manufacturer. So Alstom have used Cummins fuel cell engine along with the hydrogen tanks to power up an existing or I mean a new Coradia Island is the actual name of the rail coach that has been manufactured. The train is already proven in multiple parts of Europe, including Germany. This train has hit a maximum speed of around 140 kilometers per hour and has been successfully running across multiple regions in Europe. And then with having a range of around 1,000 kilometers each hydrogen tank fueling. I mean, this is almost getting compared with an actual existing diesel based rail train. So that, I mean, this shows that wherever even electrified rails are not available, or on electric infrastructure not available, I mean, this can be a pretty good use case to convert the rail lines into green. So, we also have done obviously one more demonstrator project. This is typically the HY4 project. So it's an H2 fly project is what it is termed for. And we have done this project in collaboration with multiple universities as well as DLR Aerospace. So they have actually used a Cummins-based fuel cell in this particular application. It's already the test flight is done, and then almost 30 flights of 2 hours each has already been done. And then I mean it's a 4-seat airplane and has successfully completed the test trials. And it has, this current model has a 4 passenger capacity. So we would like to just highlight the fact that we already have at least have an experience on supplying fuel cell into an aerospace application. Just giving your bringing your attention to overall aspects where typically we are in commercial vehicle segment. So the trucks which uses the fuel cell, we have already done the demonstrators with Scania as well as with found refuse trucks. We have fully battery electric buses with Gillig as well as with the Bluebird, and then the last use case, which is mainly on the electrolyzer side of things. So I think these were the key solutions that we would like to share to the participants. In case of any questions, we are open to take that.
Thank you very much for very precise presentation of your capabilities. We just would like to hear one sentence from you. What is your focus within India in terms of what you can do for in the case of electrical propulsion for aircraft, like you have done for let's say Europe? What exactly you would like to do, or have you done anything particular in this context in India?
So I mean, I think probably in the last month or so, we already have connected with the key engineering team when we got an inquiry from NAL. So we have already understood the key requirements of an expected application. At least what we would like to do more is that basically we do not have an expertise in an aerospace application. We need to bank on NAL to be acting as that integrator and then having that expertise of aircraft application, because we believe it is the OEM who has the experience in that particular application. How we can add value is basically based on whatever use cases we have done. We have pretty much good experience on how to select a good fuel cell power module for an application based on the duty cycle that we need to target. So if we get to know more details about the actual, the application requirement, probably we can work with simulation team to come out with possible potential solution for that particular aircraft application. Then we can probably to work as a demonstrator.
Hello. Ashish, are you able to hear me? Are you able to hear me?
Yeah.
My question is,
Yeah.
with DLR, right? DLR and University of Stuttgart.
Yeah.
Are the fuel cells which are used there, is the same thing what you have shown as a Cummins fuel cells, or they are different fuel cells? Which is used in the DLR for over 30 different types of flying experience. Is it the same fuel cell, or which are the fuel cells used in that particular application?
Yeah, sir. I mean, these fuel cell are basically hydrogenics fuel cell. So, I mean, Cummins into the fuel cell technology is basically by acquiring the hydrogenics. So typically, it was a hydrogenics fuel cell that are being used in the HI-4 aircraft project, so which are being carried forward as Cummins also. I mean, in the existing product portfolio. So absolutely, whatever technology that is already being used is now being probably branded as Cummins, but it is ultimately the same core technology that is being on offer.
But your fuel cell showed 50 kilowatt weighing about 118 kilos, 50 kilowatt fuel cell. 45 kilos showing 218 kgs. So it's about 0.2 kilowatt per kg. And what is the space of hydrogenics fuel cell?
Sorry, sir, I think your voice was cracking. Can you please repeat if you don't mind?
If you're saying that you're also adopting hydrogenics fuel cell as a Cummins fuel cell,
right? Yeah.
What is the specific power per kg of your fuel cell? Because as per the data, it shows 45 kilowatts were weighing about 200 plus kg.
Okay.
Yeah, 0.4 or 0.47 kilowatts per kg.
Yeah, sir. I mean, typically, like, I mean, if I want to probably be more specific on, suppose if you want to offer a 45 kilowatt fuel cell based power module, which we term as HD45, that is the model name of that. So typically, that 45 kilowatt fuel cell will be, I mean, weighing around 95 kg of weight, sir. I mean, that is what we have on offer. This is a latest generation product that we have. The DLR project was initiated quite some time back.
My question is, was that used in the DLR flight? Do you have the specs of the DLR flight with you? The specs of the DLR flight, the 44C?
No, no, sir. We do not have the exact fuel cell model specification of the DLR.
Can you get it, because the Cummins is collaborated, right? You said with DLR.
Yes. Yeah. Sure.
Get those specs.
Sure, sir. We can take this offline, and then definitely we can.
Thank you.
Okay, thank you very much. We now move to the next presentation from Dr. Dada Saheb, H2E Power on fuel management, fuel cell and management systems. Topic remains same. Dr. Saheb has from IIT Bombay. He is a general manager applications. He's basically working on application development and heat waste heat management from solid oxide fuel cells. And Dr. Dada, go ahead, please.
Dr. Shagde, you can unmute and go ahead.
Yeah. So thanks for this opportunity. So the intention of this presentation will be, we will share S2's experience in solid oxide fuel cell and different projects we are handling. So directly for hydrogen fueled aircraft, so it will not be directly related. So thanks for opportunity. Just next slide. Yeah. So what H2E believes is that surplus renewable energy will be the key factor in the future, and generation of green hydrogen, that we believe that will be the future. Next slide. Next slide. Fourth slide. Yeah. So now, as a S2E, we have two more sister companies that is 100% owned by us. That is Empower, it is in Germany, and Hexis, that is in Switzerland. So S2 owns these both technologies, M-Power, we have planar stack, electrolyte supported. For Hexis, we have planar circular stack, open-ended. Yeah. Next slide, please. Next slide. So this is what our product is. That is a solid oxide fuel cell, which will produce 1.5 kilowatt electrical output, and it is it is also a CHP application. So it can generate hot water about 600 liter per day. That is in 24 hours. And it can generate 36 units per day. The stack, the parts are the desulfurizer, stack, and heat exchangers. That are the critical. So we have installed more than 500 1.5 kilowatt systems. This is, you can say, CPOX reformer we are using at this stage. Next. Next. Yeah. So this is one of typical installation. One of typical installation. So you can see the 1.5 kilowatt system can be fit like as a refrigerator at in parking also, or in terrace, or in between, and it will consume NG. Presently, it is working on NG, natural gas, and with CPOX reformer, our efficiency is about 45 to 48% depending on the natural gas methane percentage. And it will also generate about 1.6 kilowatt thermal rule. So overall efficiency, you can say we are getting about more than 90%. And this system is operated continuously for more than 40,000 hours. And we declare or certify the life of stack as a 40,000 hours, continuous hours. This stack operates at 800 degrees Celsius. Next. So this is the facility from cell to whatever stack assembly, and we can produce about 5,000 systems per year of this SOFC. Next. Also on the lab, this system is also in India. Also, we are also working on steam reforming demonstrator, and we have successfully operated the system 1.5 kilowatt system with steam reforming. And we can say that for 10,000 hours, we are consistently getting efficiency more than 55%. So that is 55% electrical efficiency. Of course, there will be CHP. So combined CHP and electrical, it will go more than 92%. Next. Now the presently we are comfortable with NG gas, but in future we want to also integrate pure hydrogen and also hydrogen blended natural gas. That is, the products like that are in process. We also want to run this SOFC system on liquid fuel, like as a diesel or methanol. So, but the development of reformer and association is in the process. You can see the stack technology is ours. We can say that is 100% owned by us. The beauty of stack technology is that if we use in reversible mode, the life do not impact. So same stack can be used in SOFC at 800 degrees Celsius, and we can generate hydrogen, pure hydrogen or green hydrogen, by using electricity and water. Here beauty is compared to PEM electrolyzer, AM electrolyzer, or alkaline electrolyzer, it will take about 2/3 of electricity. So you can say overall, considering the balance of plant and everything, you can say 1 kg of hydrogen will require 38 to 40 kWh. Or in case of PEM or alkaline, it is 55 to 65 kWh per kg of hydrogen. All this process works at 800 degrees Celsius or high temperature. And if you have waste heat or waste steam at 300, 400 degrees Celsius, then again the electricity consumption will go down. So with this stack, with solid oxide electrolyzer, and for continuous operation, this is one of the energy efficient way to generate hydrogen. Next. Yeah. So for SOFC also, if we can we reverse it by providing water or steam and electricity, so that can be demonstrated. It has been demonstrated, and the beauty is now we have made 5,000 units of such SOFC systems. Now we are looking for cost reduction, like as a gas measurement systems. How we can manufacture insulation or SMI assembly, desulfurized assembly in mass and effectively. So to reduce the cost, that will be the next target. Next. So this is the operations or factory. It shows the capacity from cell to systems. About 5,000 systems we can manufacture with present setup. Next. So next, go to slide number 21 directly. Yeah, so we have also installed such as 2 systems on commercially on one at NRML Ambernath, and it is successfully installed, and other is in process. We are giving this system to IIT Guwahati, and they want to integrate it with liquid fuel reformer. So now presently they will experiment with NG, and again they will integrate with liquid fuel reformer. We will get H2 plus CO, that is syngas. That syngas will be provided directly to the SOFC. Next, go to slide 24. Yeah, so we are also looking for different applications. Can biogas filtering or separating H2S and CO2 from biogas can directly we use for SOFC? So it will become like as a microgrid, 24 hours microgrid, including solar PV, wind, grid. So that is one of the project we are handling. Next. So this is the first project we have installed on 20th April. It has been inaugurated by OIL chairman. They have installed 100 kilowatt hydrogen generation plant. It will produce about 10. It is AM technology, and it will produce about 10 kg hydrogen per day, and it will operate about 8 hours. 8 hours per day. Yeah, the input will be from solar. Of course, they can run 24 hours and using electricity from grid. Next. We are also working on development of hydrogen fuel cell 3-wheeler. The difference here we are taking the electrical 3-wheeler, but here we are using solid state type storage for hydrogen cylinders, and there will be 3 cylinders of 300 gram. Each cylinder will store about 300 gram of hydrogen. So there will be 3 cylinders, and the pressure will be 50 bar. So we will get the convenience that we need not to have chargers or systems at 250 or 300 bar. That one type of 3-wheeler we are going to develop. Yeah, next. And we are also in battery technology. This is high temperature NaNiCl2 battery. It operates at 300 degrees Celsius. But the beauty is the life of this battery. It uses only NaCl is the major component. Nickel will be 150 gram per kWh. So the cost will be less, and its life will be more than 10 to 15 years. And there is no costly atom like as costly or polluted atom like as lead or lithium. So this is one of the area product we are working on. Next. Yeah, and using this, we are developing different applications for microgrid. Next. Next. I will just brief what journey we are doing next. So same way, what we believe that if diesel is not a dirty, if we can use diesel with minimal CO2 and minimal NOx, then from diesel can we replace the instead of diesel pump, we will have electrical charging stations. So if we got 40% efficiency and less NOx or negligible NOx, of course CO2 will be there. but per kilowatt CO2 will be very less. So in transition phase, we also believe that for electrical charging stations, diesel will be used to generate electricity for EV charging efficiently and with minimum pollution, or a clean way, we can say by clean way. Next. So next, go to next. Yeah, that would next. Go to next slide. I will, yeah, next. So there are many applications like refineries, for fuel cell, for electrical vehicle as a range extender, that we can look for SOFCs. We have also as our own 12 patents.
Please conclude just next 1 or 2 slides.
Okay. Next slide. Yeah, please. Next slide, please. Yeah. Before this, that will be last slide, 39. Yeah. So our main technology is SOFC stack, and that can be used as a SOEC. So now we are looking for some experiment up to done in the lab. We have generated hydrogen in SOEC route. So can we use electricity from the sugar factory or a surplus electricity available and CO2? Let us say from sugar factory, CO2 available is from fermentation process. If CO2 and electricity is available, then can we make high costly or a high grade SAF fuel? And yes, the economics said that it is possible, and through SOEC route, that will be the route. And I will stop here. There are many projects. So that is what as a S2E, our main product is SOFC, and on stack basis we are developing different applications. Yeah.
Dr. Dasa, could you like to summarize in 1 or 2 sentences in the context of electrical aircraft, which we are discussing for last 2 days, what specific contribution you would like to make?
Sir, for electrical car, we are using also for 3-wheeler PEN fuel cell, and we are also using for fuel cell solid state hydrogen. But as of now, sir, I just joined. How it is relevant to the present workshop goal, I literally don't know. I will stop here.
Okay, any other question? Yeah. Any other question for him? Okay, thank you very much, Dada Sahib.
Thank you, sir. Thank you, sir.
Yeah, we'll move to the next presentation that is also online. This is from Dr. Rajesh Kumar Upadhyay from IIT BHU. Professor Upadhyay talks to us on development of reformers for fuel cell systems. Professor Upadhyay is an area of expertise.
Good afternoon, everyone. I am Rajesh Kumar Upadhyay.
Go ahead, Professor Upadhyay.
From Department of Chemistry.
Go ahead.
So we all know that hydrogen is considered as a fuel for the future. However, it is still not able to make an impact in terms of the applications. Our Honorable Prime Minister has already launched a National Hydrogen Energy Mission, emphasizing that hydrogen should be used for the power generation. TERI has submitted a report emphasizing that hydrogen use will increase drastically in near future, particularly in the transportation sectors. However, the major bottleneck in using the hydrogen as a fuel is its storage and transportation. It poses both safety hazards as well as increases the cost of the overall system and make it uneconomical. Therefore, many people are trying to work on generating the hydrogen on site or on board. It means you are generating the hydrogen at the site of application itself. Now, there are several ways one can generate the hydrogen, but steam reforming of methane or methanol is being favored because of its cost effectiveness as well as they can be made compact. Now, as a group, we are focusing only on methanol because methanol operating conditions are little bit moderate. So it can be applicable or it can be used easily for onboard application or on-site application. But we have also started recently working on the methane, given the cost of the methane is very low compared to the methanol. Nevertheless, today we are focusing on mainly on the methanol reform. So what we are working on is that conventionally methanol reforming is not a new process, and I think already being used in since last 4 to 5 decades. In typical methanol reforming process, what is being done is that you take the methanol water mixture and feed it to a catalytic reformer, which is operated at 200 to 500 degrees centigrade temperature, depending on which catalyst we are using. And the output of this reformer consists of hydrogen, CO, CO2, water, and unreacted methanol, if any. Now, in PM fuel cell, we need a hydrogen which should be, the purity should be more than 99.999% or higher. And there the problem starts. So what we do, we have to convert this CO. We convert the CO to the hydrogen and CO2 by using the water gas shift reaction. So first, these gases are passed through the WGS reactor. Then the remaining traces of the CO2 is again passed through the procs to oxidize. The CO is oxidized to the CO2. And then they are passed through this series of PSA to separate all the gases, and the pure hydrogen is formed, which are packed in the cylinders. And these cylinders are transported at the site of the application and clubbed with the PM fuel cell to generate the power. Now, what we are trying to do is that we are trying to combine all these assemblies in a single unit, which we call it membrane reformer, in which generation and separation of hydrogen take place in a single unit. So what happens that in this typically membrane reformer, the catalyst is placed at the bottom and the membranes are hanged on the top of this catalyst. So methanol and steam mixture fed to this catalytic bed, they convert it to hydrogen, CO, CO2 and all. And these membranes, which are hydrogen selective membranes, selectively separates the hydrogen from this mixture gases. Now what it happens that once you are separating the hydrogen from the product stream, as per the Le-Chatelier's principle, the whole equilibrium is shifted towards the product side. So this gives you added advantage that you can have a higher conversion at the same operating conditions or same conversion at relatively moderate operating temperature and pressure conditions. And that gives a bigger advantage to make it compact as well as less energy intensive and suitable for onboard or on-site application. However, in this whole process, the membrane is very, very critical that it maintains the purity of the hydrogen. It should also give the high hydrogen selectivity. Now, these devices which we have demonstrated, and I will show you a prototype later on that, even a 10 kilowatt prototype, it can be fitted in a floor space of around 1.5 meters square. So they are very, very compact and can be used for onboard or on-site applications. Now, if you see the motivation why we are doing this work, so these are some of our results which we have published, is that this is the performance for methanol reforming in terms of the conventional reactors where you use the catalytic bed, and you can see that this is the conversion with the temperature, and these are the MR. We have tested different type of MR. I will come to that later. But any type of MR, if you see that at lower temperature operating conditions, obviously MR gives you a major advantage. It gives you a very high conversion compared to the traditional reactors, and that makes it suitable for on-site application. So that was the motivation of these studies which we have performed. And as I said that it is very critical to make a membrane which is very highly selective. Now, palladium is metal of the choice because palladium is prepare a dense membrane. It means there is no holes available, and it separates the hydrogen because of its catalytic activity. So it means if your hydrogen is being separated through this palladium membrane, the purity is guaranteed, and ideally you will get infinite selectivity. It means it will be 100% pure hydrogen. But the challenge is to make a thin membrane which is still dense. So how the palladium separates the hydrogen? So suppose this mixture gases comes to the contact with this palladium membrane. Let's assume this is the palladium membrane. So what happens when the hydrogen get adsorbed on this surface? Because of the catalytic activity of the palladium, it dissociately adsorbed on the surface. So hydrogen molecules actually break into the hydrogen atom, and this hydrogen atom then diffuses in this metal like a liquid, and at lower pressure side they again combine and make the hydrogen molecules, and which is dissolved from the system. And no other gases do that, and there is no pinholes or no holes available. So it means what? And this palladium, if you make dense, will guarantee you 100% purity. And if this is fine, how to check that? Then what will happen? It will follow the Sievert's law of diffusion, and you will say that N value will come to 0.5 because it is dissociative adsorption, which is the rate control step. So we have prepared the membranes in our lab, both on porous alumina and porous SS support. Porous alumina supports are used for stationary application, while for mobile applications, porous SS is being used because they are more resistant to the shock. But the challenge is that their surface morphology for porous alumina and porous SS is very different. So you can see that porous SS has a pore size of around 31 micron, while if you see here that the pore size is in the range of 0.1 to 0.5 to 0.6 micron. Nevertheless, the challenge in the porous alumina is also to connect it with the metallic fitting so that there is no leak generated at this fitting. So our group has developed all these facilities and expertise to do this. These are the pore size distribution, mean pore size distribution of the porous alumina and porous SS. So you can see these are the bigger pores, these are the smaller pores, so they pose the different challenges, but they also provide the different advantages. So we started preparing the membrane by using the electroless plating method, and there are different stages in doing so. We use the pure alumina tube, like this is the bare alumina tube. We activate it and then we keep on depositing the palladium by using the electroless plating method. And if you see that after the first cycle, this is the palladium deposition, but you can see several cracks which is being formed. Now these are quite big cracks. All the gases will pass through this. So we keep on depositing several cycles, and say after another cycles, what happened? This palladium starts growing on the top of this tube, and a beautiful cauliflower structure is being formed where there is no pinholes available. So this makes the whole membrane dense, and that is suitable for separating the hydrogen. However, the problem with this technique is that the thickness of the membrane you get is very, very high, 16.5 micron. So what will happen if the thickness is very high, the flux will be lower, and in that case you have to use lot of membrane to separate the hydrogen if you want a desired quantity of the hydrogen to be separated. So it will make your size very bulky. Therefore, what we have done, we have started using some advanced technique like PVD, physical vapor deposition, and chemical vapor deposition, and we have prepared the membrane through PVD and CVD also. But the problem here is that the loss of material is enormously high, and this is palladium, so it makes your membrane costly. That's why we developed a new approach, which is hybrid approach, where we have combined the PVD and ELP, CVD and ELP. Now we are also working on combining PVD and CVD to make the membrane. And we have come up with a new methodology of this to prepare a membrane. Now you can see these membranes are around 5.3 micron thickness. So we are able to reduce the thickness of the membrane by 3 times. Hence, the number of membrane tubes required will be reduced drastically. So this is just a representation that how these tubes look like. And if you see this, this is the porous tube. And once you pass the argon gas, ideally what happens that there should be, this is the porous tube, so the gas will start passing through as you keep on increasing the pressure. So this is no deposition has been taken place. Now this is the tube which we have made through electroless deposition. So here also, if you see now that in this tube, there is no gases which is coming out. If you keep on increasing the pressure, if you see this pressure and this pressure, no gases is coming out. It means what? This tube is completely dense and it will only pass hydrogen because of its catalytic activity. So this tube here up to 3 bar pressure, we have now made our recent tubes which are high pressure tubes. This is able to sustain up to 6 bar pressure. You keep on increasing the pressure and you will see that no argon, no gas will come out of this. This shows that the tube which we have prepared is completely dense. There is no pinholes formation on these tubes. And that's why it is able to survive this pressure, and at high pressure also no gases is hydrogen from it. Then we have done the hydrogen permeation testing, and we have tested it at different temperature and pressure, and you see that here for n equal to 0.5 for all the temperature and pressure condition, it fits the straight line. It means the Sievert's law is dominating. It means the surface dissociation is actually the rate controlling step, and this suggests that there is no pinholes develop even if you operate this membrane at high temperature and high pressure. So we have compared this membrane performance for PDAG and for porous alumina and porous SS, and we found that porous SS gives better permeation. The reason is that it has bigger pores, so it doesn't, this support doesn't restrict anything, and because of that at lower pressure also you get high permeance. So, and we have also optimized the activation energy for this, and we have bring the activation energy by reducing the thickness and the operating condition to a level which is the activation energy of the catalyst. It means these membranes are now suitable for the integration with the catalyst, and if you integrate, at least membrane will not be the rate. We have also optimized the way the membranes should be stacked inside. So how to design an optimal separator to achieve the higher recovery. We have tested several design, and I'm not going in detail of this in interest of the time. And we have performed several CFD simulation also. And based on this CFD simulations, we have done some experiments to validate it and found that if you do the stacking properly, these membranes by using some internals, you can achieve the recovery as high as 80% with 4 membranes. Now with the 6 membranes, we are able to get a recovery of 85 to 90%. So that is a very good recovery, and no one across the literature has reported such a high recovery by using these membranes. So this makes these membranes ready for integration purpose. We have also worked on the catalyst. I'm not going in talk in detail about the catalyst, but we have come up with the catalyst, which is a novel catalyst, and which can give high performance, high conversion without giving any CO selectivity up to 450 degrees centigrade. So this catalyst is, good part of this catalyst is that it reduces your CO. And if the CO formation is reduced, what happens that it enhances your separation efficiency. We have also tested this catalyst long time efficiency. Until 100 hours, this catalyst shows the same performance of around 70% conversion. We have also done the drift analysis to understand that why the CO formation is not taking place, and we have found that there is a carbon-carbon bond, the CH bond stretching is taking place, which is actually reducing the CO formation. Now, after that, we have integrated both catalyst and this membrane in the reactor, which is for 500 watt membrane reformer. First, we have tested it. So this was the reformer setup where the membranes was hanged here. The catalyst was the packed at the bottom. And you can see that for this 500 watt, the catalyst life was sustaining up to 100 hours in the membrane system also. The permeate flux was very high, that this is the molar flux which was increasing with the temperature, and you see this portion where it shows that the hydrogen, this conversion which was in the traditional reformer was around 70% in presence of the membrane, it goes up to 95%, and we are able to achieve a recovery of 80%. And all these components, catalysts, these membranes, and this whole design of this reformer is being developed indigenously in IIT BHU. So we have prepared all this component and all. Then what we have done, we have developed a bigger prototype, 1 kilowatt, which can actually run up to 5 kilowatt prototype. And we have connected the output directly with the fuel cell to generate the power. So you can see here that power is generated, and we have ramped the power slowly up to 900 watt to so that this reformer is able to sustain that 900 watt amp, this power for longer term. And the good part is that to generate the 5 kilowatt power, you just required around 50 to 60 ml of methanol per minute. So it requires a very small amount of the methanol to generate the 5 kilowatt power. So it is overall economical, handy, and very compact. Now this is the test setup, that's why it is big. Ideally, we can pack everything in a 165 liter fridge. So this is the prototype demonstration which we have done recently for the DST to show that, okay, this prototype is working, and we have come to the TRE to the PM fuel cell, which will be shown here right now. Yeah, this is the PM fuel cell we have clubbed, and all this system, computer, this UPS, this YouTube light, and the other power source, major power source, is being lightened up by this using the PM fuel cell, which is using the hydrogen supply generated through our reformer. And we are slowly ramping up so that fuel cell can generate that much power. It takes some time. So this is the way we have demonstrated our prototype. So you can see that we are able to generate a lot of power through this 1 kilowatt around power by using this reformer. There are a lot of places where we can use. If we talk about the addressable market, we can for providing us a generous funding to do this work. I would also like to acknowledge my group who is working tirelessly day and night to develop all this prototype. And at the end, I would again like to thank the organizers for giving me this opportunity. Welcoming any questions if you have, I will be happy to answer. Thank you.
Professor, you are available for
discussion? Yes, sir.
Okay, thank you very much. It's a good development, but we have to really see how best it can be used or available, utilized for the aircraft purposes. So is there any question regarding this?
This is the reformer. Multiple applications. We can see that on the because I've been looking for this reformer for quite some time, and Dr. Sonde is aware of this. What we should do, because you are showing that it is TRL7, both for aircraft application and for this, we should start making it as a compact version. And the kind of iterations which you are doing on the membrane, I think you should now reduce it to the least possible number so that we can now bring it to markets. TRL7 is good enough. We should now at least make a couple of prototypes and field it on a truck where we can use a fuel cell, and we can buy a fuel cell from any of the companies and use your reformer and make a system for commercial lorries, commercial transportation system. Same thing can be applied tomorrow when we do it for the aircraft application. Only weight and volume calculations will have to be done for packaging purpose. So I think we need to start working together on this. I see it as a good future for this job.
Thank you, sir. Thank you for your comment. Sir, am I audible? So thank you for your such a kind comment. And we have done some calculations. We are also trying to pack it. Regarding the membrane, we are now reducing the iteration. Now we are planning to make some bigger membranes, which can be used for the application purpose. And regarding Hansa also, I have done some calculations. Harikota sir was here with us a few days back. So we were discussing. So we can make a membrane reformer now. We are developing a membrane which will be around 1 micron thickness, and that may be developed in few months' time. After that, we may able to fit this 10 kilowatt, this capacity, which means around 1 kg hydrogen production per hour. We can fit it in weight of around 25 to 30 kg. And it will be also fitted in around a fridge of around 165 liters. So that is the target now we are working. And yes, we are also working that, okay, to make a prototype, put it on the lorries for EV charging and maybe for power backup application, as you suggested, sir.
No, I think the technology for manufacturing the membrane is the key in this, and you should find an industrial partner for that too, so that it can be developed, produced in numbers with the required quality and cost, and quantity and cost. So you should find an industrial partner. If you have difficulty, please come to us. We'll help you.
Sure, sir. I will come to you, sir.
Okay, thank you.
Thank you, sir.
Good one. We will come back to the. What, Sondeji? What is that? What is that you are saying? Sondeji. Yes, sir. Well, compare with your department.
Yeah. 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 No, it's good because what we had developed was we are stopping up to water gas shift reaction and going carbon monoxide up to 0.5% or HT FEMSAT. So we were getting about totally 88% efficiency. And the cost is because the palladium membrane is very expensive, Rajesh. To get those kind of membranes, we're trying to source them, and they're either in ceramic or in the stainless steel. They are hugely expensive. And the raffinate comes out of that particular membrane. It becomes difficult. What do you do with that raffinate, which contains maybe 30% hydrogen? The rest of it is all carbon dioxide. So you have to find some application for that particular raffinate after you get it from the membrane. Because in the fuel cell, you have one coming from the anode, one coming from the reformer, and one coming from the palladium. So it would need a very tight integration. But maybe often we can discuss Rajesh on this.
Yes, sir. So we have already thought about it. Regarding the raffinate, we are going to make a reformer which will be self-sustaining. So we are going to burn that to sustain get the energy for this reformer. So that we have already started working. Regarding the cost of membrane, we are now making a LOI which have only 70% palladium and 30% of the silver or copper. Now we are going to make it copper, silver, and palladium. So the palladium will come to 50%. So the cost is already reducing. And if you reduce the thickness to 1 micron, I think one cost of this one membrane will be around 5,000 rupees. So this will not be that much costly, which we are talking right now, that the cost. And even now, if we prepare this membrane, we are able to make this membrane of around 7,000 to 8,000 rupees. So we are significantly reduce the cost. We are also working to make the membrane thinner. But as Saraswat sir has suggested that I think this is the time we should also go for commercialization and keep on improving this in future.
Or after 15th of May, maybe myself and yourself, we should, and we can have welcome also to join us. Maybe in Delhi we can meet and then work out a real roadmap for how to make a commercial version of this at the earliest. Okay?
Sure, sir. Sure, sir. Sure, sir.
Anyone else would like to join in this meeting, will welcome. Okay, thank you very much. Thank you for giving us a good idea. Very good.
Thank you, sir. Thank you.
Go back to the physical mode. Next presentation is from Professor Rajesh from Siemens. He talks on urban air mobility, engineering and future. Probably Siemens has some plans for that. You'd like to hear that? He is a mechanical engineer with a long experience with Siemens.
Another 2 hours. 10, 15 minutes.
15 minutes. One more is there afterwards.
Yes. I'm audible? Yes, sir. Sure.
Sir, friends can be avoided.
Go ahead. Go ahead, sir. Good afternoon, everyone. I would like to thanks to NL to give us opportunity to join to this. So today we are talking about how we are helping the industry to design, to build and verify electrical vehicles or electrical e-aircraft. So in future, today what we are looking at is that it's not a traditional fuel system we should use, but we should implement something that can help us to improve the economy of the system, and it will help us to save the nature life. So what we have to implement, we have to remove the traditional fuel system and implement something called electronic system or electrical systems, which will help us to do the propulsion of the electric aircrafts. So for that matter, we have started something around development plan in 2012. Then we have developed a e-aircraft. Then actual sorties has started in the end of 2014. We have done some modifications into the electrical propulsion system. We have developed an electrical motor which can deliver efficient performance so that we can have almost point A to point B around 50 kilometers of flying within one charge, and we can pass the few passengers, or we can deliver some material efficiently with less time and in good manner. So during start of that project, there were questions: can aircraft e-propulsion system development is possible? But during that time, there was kind of joke, yeah, it may be possible, may not be possible.
Don't go back to that. Let's come back to what we want.
So today, with our customer Rolls-Royce and with our solution and with the help of Airbus and Boeing, we have started development of e-propulsion system for the aircraft. And today we are delivering best. So before that, what we have understood with traditional system, or if we are looking about the urban air e-mobility, where the future will talk about the city taxis equipped with the e-propulsion system, and it may go around some 10 to 20 kilometers or maybe up to 50 kilometers for delivery of the goods or carrying the passengers. So before that, what we understood, if we are talking about the vertical takeoff machines, what traditionally we are using, then cost of ownership is more in terms of maintenance. So 50% of the money goes to the maintenance. Some 30% of money goes to manage the crews, and rest another money will go to the fuel system and rest of the system. If we are talking about the electric propulsion, then definitely we are going to improve this system in terms of here. Of course, if we are replacing the traditional gas turbines and engines with the electric propulsion system, then definitely system will be quieter.
So we will have the compliance when we are talking about the noise generation.
We are converted already. You don't have to convert us.
Yeah. So thank you, sir. Yeah. Thank you, sir.
We are
So
already converted.
yeah. So for that matter, what we have to see, we have to see the main aspects of the system. We have to look at the distributed electrical propulsion system, where we have to ensure that system what we have developed, it's having less electrical compatibility issue, and it's having less electromagnetic interference when it is working. Then when we are talking about the power and energy density, then of course power pack should be efficient to deliver the effective power to the system, so that entire e-propulsion system along with HVAC, along with your avionics, along with your control systems and so on, it can run. So next we have to look around the thermal and energy management. As we are everyone aware about that, all electrical and electronic system failures are about 90% failures are due to the heat and thermal inefficiency. So we have to improve that. Then we are talking about the integrated physics of electrical, electronics and mechanical. Then we have to ensure that the integration should go well, so that the propulsion system go ahead with the expected or intent of that specific design system. And then when we are talking about the acceptance, so this is very important. So today, every day we are looking at the news that some electric bikes are getting fire and catching fire due to some inefficient thermal power, and that news are setting the trend into the people's mind that it may not be safe system what we can get into the future. So we have to look at that concern also. So we have to pass that message to our end consumers that system is reliable, can be used, can be implemented everywhere, and it is safe to use. And the last one is that end-to-end passenger experience. So when we are talking about the e-mobility, e-propulsion system, then everything last comes to the how the end consumer and passengers are having comfortable flight. So we have to look that aspect also. So for that matter, we have to do the verification and certification in early phase of development. Then question may arise that how. So here we have to implement faster and less cost drive processes, new design processes that can help us to design the entire system within less time, then which will help that system which help us to improve the product complexity, where we can work on to the complex products, and where we can talk about the integrity, though it is multi-physics systems and so on. Then when we are talking about the electrification, then of course it may introduce the stringent norms so that we can produce the safe system. So design and certification, that process we need to consider when we are talking about the implications of that product design. And then at last, supply chain and the collaboration, that is also important. When end users are using the system, they should not may face the problem of the serviceability and other aspects. So when we are talking about the key technologies, so here we will start working and we will start helping industry people to start with the conceptual design, then product engineering, verification and certification, production, and at last deploying and sustaining that system. So here we will provide you technical skill tools that will help you in early phase of development, and that can help you to achieve the intent of your product, which can fly safely with electrical propulsion system. And of course, when we are talking about the electrification, then digital twin aspect may come. So before building your prototype, you may start testing your products when they are in flight condition by using digital twin technology. And of course, data engineering analysis will help us to acquire the data once the physical prototype is available, and use that data to improve the efficiency of the product and fine tune some product performance issues. Then here data and process foundation and aircraft program management will help us to handle every aspect of design, build and verification when we are talking about the e-aircraft technology or e-propulsion system. So here we will help you with the accelerator portfolio. This portfolio is to design, realize and optimize the system across the all physics domains, including your electrical, electronics, mechanical, then collaboration of all those physics together. Here we will help you to simulate the system when your prototype is not available, and we will work or we can start working on to the digital prototypes so that you can find out the best manufacturing processes, best operational methods, and at last we can see how we can connect our product well with the Internet of Things and how the end consumers can have the communication with the manufacturer and how they can send back the data, in-flight data or some landing data to improve the product efficiency or to improve the performance of the product what they have developed. So when we are talking about the entire digital twin, then SimCenter portfolio comes here, which helps our industry experts to work into the mechanical system, fluid and thermal, electrical and electronics, and prepare the physical testing so that during when you are sending your products for the ground vibration test, so test engineers can have the idea where I can define the best possible locations to acquire the data or best possible locations for the accelerometers, whether I can go with unidirectional or bidirectional or triaxial accelerometers. That physical pre-test planning will help our physical testing team so that we can create the digital twin. We can correlate your simulation results with the ground vibration test, and we can ensure that simulation model is matching actual dynamic properties what your actual physical prototype is carrying. Then talking about the customer case reference, so here we had worked with Rolls-Royce. Currently, we are working with them, and along with Rolls-Royce and Airbus, we have developed a system. So here is the system. What we can talk about that. So here we developed.
Urban air mobility gives another possibility of transportation. It's not only the replacement of a traditional transportation with a green way of flying, but it's compensating the transportation we cannot achieve with the traditional means, helping people to move themselves in a way which was totally impossible in the past. What we have done in 9 months and 19 days is develop the power distribution system for an electrical vertical takeoff and landing. The City Airbus demonstrator is the heaviest drone ever flown. It's full electric, it's very heavy, it needs to demonstrate the capability.
So when we arrive at the early stage of development, when we are talking about the generation of the system, then it will start. Here is the example of hybrid system where we have worked with our customer Rolls-Royce. The hybrid system along with the hybrid system was having your electrical propulsion as well as the traditional gas turbine, and here we have developed a system. Along with that, we have checked the performance of the battery. The battery which was the power pack to drive the electrical propulsion system. And here you can see we have started the development from the cell level, chemistry, then cell level, and then the pack level, and the entire battery pack, how it can deliver the power, not only the propulsion system, but also other systems like your avionics control system and HVAC system and so on. So when we are talking about the other solutions, so here in one example, you can see this solution can help you. Also, it has helped our customers to find out the best possible location of the propulsion system and the sizes and so on, so that you can find that you can arrive the best product which can deliver expected for product performance, and you can meet the intent of that design when it is ready. So when we are talking about the mechanical system, so some electrical propulsion, electric vehicles, electric aircrafts may have the landing gear system, retractable landing gear system. So in that case, we can do their multi-body dynamics along with your air drag and the co-simulation between your CFD and multi-body dynamics to find out the effect of that. When it is retracted, what would be the drag effect and so on. When we are talking about the automatic rotor system, which can change the direction according to your location of the flight. And
you must conclude down another 1 minute.
Yeah, yes, sir. Thank you, sir. So here you can see this physics can be simulated as well by using multi-physics capability. Then this is very important, which is very unique here, that the safety of the passenger, safety of the crew is prime important. The safety of the passenger, safety of the crew is prime important when we are talking about the e-mobility, e-propulsion for the electrical or for the aircraft system. So by using cement solution, before prototype is available, we can create a digital twin, and in that, by using that digital twin, we can actually work onto the digital prototype, and we can find out if there is a issue or if there is a requirement to do the hard landing, then what would be the impact onto the crew and the passenger when that kind of situation may happen. So these kind of solutions are available, which already helped us, helped our customers, and here we will help you in that case. So it's not only about the safety, and when we are talking about the taxis, city taxis, then of course we have to look around the noise generated. So such kind of solutions will help us to improve the noise generated and emitted from the system. And at last, as everyone we are aware that electrical system failure is because of heat generation. Of study also we can do how much heat can be generated and how we can dissipate that heat to the outside so that system system can perform in well manner. So it's not about the electrical system, electronic system. It is also includes the electromagnetics, because when we are talking about e-propulsion, it may carry high voltage cables that may have the electromagnetic radiation, so that we have to make compliant, design compliant interference issue with the other components. So at last, once the physical prototype is available systems, so in flight, GVT and your occupational safety testing solutions are available, which can help you to optimize the system. So these are the customer references are available, which already got benefit of the Siemens solutions for e-propulsion system into the aircraft industry. So to conclude on this, integrated aircraft performance can be simulated in early phase of development where we don't have the actual physical prototype. So Siemens solutions will help you to build, test, and verify the entire performance of the system by using multi-physics solutions. So here we will help you with the model-based system engineering, then integrated program planning and execution, the intelligent manufacturing system, which can manufacture the product as early as possible, and we can get the products actually flying as early as possible. So that's it from my side. If you have any questions.
Thank you very much, Mr. Wale. You have done a great job in terms of sort of assist software in design, development, and all that. My only worry is if people use this, they will stop thinking. That's my biggest worry. We have done a lot of complex job designing satellites, rockets, and all that without such systems. Advantage is that we didn't lose the ability to think. Okay, any question to Mr. Wale? The last presentation of this Sil Kumar of NAL, he is talking about fuel cell based electrical propulsion system for aircraft applications. Senthil, just keep in mind that you have had a nice presentation from Professor Sonde and Professor Atul. So try to avoid repetition if you can complete in within 10 minutes. That's fine.
Yeah.
Okay.
Thank you very much. So in the interest of the time, I will restrict my talk. Good afternoon, everyone. And I will try to restrict my talk on our solid oxide fuel cell expertise at Surface Engineering Division of NAL. So these are we already covered. That is, these are the important aspects for a propulsion system. That is insufficient energy requirement, from the batteries. So we need the interest is now on the fuel cell power packs. So the fuel cells are being explored for many applications. That is aviation applications, auxiliary power unit, low altitude aircraft propulsion power, high altitude long endurance, airport applications, ground support equipment, unmanned aeroplanes. So this is the graph showing the fuel cell systems have a better efficiency than state-of-the-art battery systems. And there is already enough talk on fuel-based fuel cells and high temperature from fuel cells. So, and I will try to cover on the solid oxide fuel cells. As you are aware, the solid oxide fuel cells is high efficient fuel cells. It can operate at 800 degrees centigrade. And also, one uniqueness of the solid oxide fuel cells is that it can operate in a hybrid mode with a gas turbine engine. This is how the solid oxide fuel cell activity started in the NAL, way back by our former director, Dr. DR5, and it is being now led by Dr. Aruna and team. And this, in the cogeneration mode, this fuel cells can go up to 70% efficiency. And one unique thing is this is also fuel flexible. It doesn't require pure hydrogen. It can operate in ammonia and hydrocarbon as well. These are all the PEM-based fuel cell aircrafts, which is already demonstrated by various agencies. And this is one of the that is PEM-based fuel cell problems, which is all identified for, that is the cooling problem, which we have discussed elaborately. With the availability of the this kind of power pack, that is small PEM-based power pack, it is now possible to increase the endurance limit of UAV applications. So this is the one iron tiger, which can have a longer endurance by using this kind of fuel cell model. With this, we will also such an activities in our UAV program. So we are jointly proposing along with the NAL UAV team for ground testing and evaluation of such a fuel cell in the mini UAV. So this can improve the endurance limit of our switch from present 90 minutes to 180 minutes. And this can operate in a parallel hybrid mode with the batteries to take care of takeoff and climbing with power requirements. So as I told, the solid oxide fuel cell presently mostly seen in the stationary applications. Still, it have a wide range of applications, including airport support, and this can also augment typical airport requirements also. So our fuel cell activities are mainly on the cell based. That is, we are having expertise in developing the catalyst for the anode, cathode, and even we are developing indigenous electrolyte material by various synthesis techniques. And also we have enough expertise on fabrication these cells at NAL. We have developed anode supported and electrolyte supported cells. These cells we have also demonstrated in the short stack level. So these cells have a very impressive power density, that is 2 watts per centimeter square, which is par with the international standards. So, and it can provide a very good power pack of very good capacity. Also, we are developing the components for solid oxide fuel cells, such as interconnects, and we are also supporting the national labs like NMRs. We have supplied these kind of spinel coated interconnects for their SOC programs. And these spinel coatings can be also be utilized for the mesh. With this, we can also bring down the cost of the SOC stacks. And we are using the solution precursor based plasma spray technology to realize these kind of coatings. And these coatings are performing well with the platinum mesh. And as we told, these cells are also capable of handling hydrocarbon. We have specifically developed hydrocarbon compatible fuel cells. And these cells have specially developed a catalyst. This is an anode catalyst at NAL. And this can self-reform the hydrocarbon fuels so that the durability of the cells in the hydrocarbon can go up. And also this can open up the opportunity to use the other fuels like methane, which can bring down your fuel storage rate. And this also has an impressive power density of about 900 milliwatts per centimeter square at 800 degrees centigrade in the methane fuel. With this, we have also developed the electrolyte-based fabrication technology at the NAL, and we have also transferred this technology to Carborundum Universal. So we are also, with this, we are also supporting the MSMEs to enable the supply chain of SOC technology from India. Now, this company is anticipating big orders from international fuel cell fabricators like Coulomb. So, as I told, the fuel cell also can be find applications on board. These are some of the onboard applications that is based on fuel cells. However, on the larger aircraft, its weight has to be further improved. That is, from the at least the weight has to be reduced from the present weight to 2 to 3 times. And also, the specific power density, that is the present about 100 watts per kg, has to be improved to 500 watts per kg. So the NASA Glenn Research Center also came out with novel designs which can enable this kind of high performance fuel cells wherein we can achieve up to, that is solid oxide fuel cell, wherein we can achieve up to 2.5 kilowatt per kg, that is power density, gravimetric power density, and 7.5 kilowatt per liter volumetric power densities. So as I informed, our fuel cell can also handle multiple carbon fuel, including ammonia. So this can open up the opportunity to explore the ammonia using the ammonia-based fuel cells. And also the regenerative fuel cells, which is also based on similar technology, which can make, store, and consume hydrogen, could conceptually be used for energy storage system for a hybrid electric propulsion system. So with this, we also initiated reversible solid oxide fuel cells. This can handle multiple fuel functionalities and consisting of dual ion and electron conducting electrodes. Also, it can handle multiple fuels in SOC mode and utilize a hydrogen oxygen generator in the electrolyzer mode. So this project is recently sponsored by DST Advanced Hydrogen and Fuel Cell Program. And here the NAL is a nodal lab, and CSIR, we are also working with CSIR and TUI and other MSME like Dells Power in this program. So this is a kind of present global scenario, that is a fuel cell and package cell propulsion technologies mature for UAV or small aircraft. However, for large aircraft, that is concerned for major technology requirement. So these are the fuel cell programs which are developed by our sister labs indigenously in India. So with this, our power density of our cells are competitive. However, we need to design weight consistent for aircraft applications. I'm sure this will be realized. So the fuel cells are suitable for onboard and ground applications. It can be provide long endurance. So we can use it for UAV and small aircraft with the present technologies. And also the present power density has to be improved about 2 watt per kg. Here I'm saying watt hour per kg for a larger aircraft. And also there is enough potential for ammonia-based fuel cells. The dedicated programs are needed to develop flight-worthy fuel cells in the Thank you. Thank you.
Okay, thank you, Senthil Kumar, for very nice presentation. You have concluded yourself that you have to reduce the weight.
Correct.
And then only come back for the aircraft application. Yes. So as I think in the light of that, no further discussion is required. We break for tea, and I'm not concluding everything. No break. Okay. Sorry, I just assumed that we'll continue the discussion.
Yes, sir. We are presently actually working on a solid oxide fuel cell. Yeah. See, correct, sir. In NASA program, they have used bioelectrode support assembly. So presently we are using anode or electrolyte supported assembly. So that it is only the fabrication process. That is by free-scale casting they are achieving those kind of electrolyte. That is single cells. So it is possible to realize in that we can reduce the interconnect weight. That is, we can avoid metallic interconnect so that we can achieve such a weight.
In any you have a program like that?
We have to initiate.
This program is not that many. You have added about something to
Yeah.
Okay, so we prepare for the next session.
Dear participants, we are going to enter for technical session. We will start panel discussion.
Oh my God, yeah. See,
Entire thing you keep in center.
That's my God. I don't know. Camera ಹೆಂಗ್ ಸರ್ ಇದು ಒಂದು ಕೆಲಸ ಮಾಡೋಣ ಇದು
I'll only make one statement. I get the bike. संख्या भी कम हो गया नहीं वो अल्टरनेट है सर नहीं मैं रह रहे हैं जब तक बाइक हाथ में नहीं आएगा बोलेंगे नहीं बाइक नहीं आवाज बहुत अच्छी है बाइक तो So now the last session, NL session. I'm sorry that I couldn't be present in the morning, but some other commitment. I think you are very fruitful and very capture on subjects. My only one statement as far as electric division is concerned is what is the objective? I'm not talking about electric propulsion or what is the objective of this electric. Basically, like all we are talking about reducing greenhouse gas emissions. This is one of the major requirements for that. And of course, associated with this, if you get a better, cheaper performance, then it becomes a very useful solution. So, papers I have read, and the summary which I will consider on that is hydrogen is the only hydrogen electric propulsion system is the only best sustainable propulsion system for aviation. People have suggested many comparisons have been made with all battery electric, hybrid electric, series hybrid, thermal hybrid, all of them, including the biofuels, the kind of hybrid applications. And ultimately, when I saw on that chart, all greens are coming only in the hybrid propulsion, that is electric, in the electric, hydrogen electric. So, what I know which has happened since last year, I'm sure you must have concluded on the same lines. Now, if we have to reach that, there are two important points. Number one, if we have to get the right thing going on a commercial scale, number one is to get hydrogen at a reasonable price to the what we call as the green hydrogen. Because they're talking about sustainability, they're talking about net carbon zero, then we can't do gray hydrogen. We are going to do gray hydrogen. Then the point of sustainability, what we call as where to make kind of emissions. We have to look at where to make kind of emissions, and those emissions have to be into the air. So obviously it has to be green hydrogen. All of you know today the cost of green hydrogen annual today is not so different. So it becomes a major problem when you compare it with the actual content. So I'm saying that if you are using that, so you are having adding carbon to that concept, then even if I add what we call the green hydrogen cost and give you carbon credit for saving that much, even today it will not be that comparable. So that is one aspect. Second aspect is presentations which are we are seeing today on fuel cells. Is again the kind of costs which are involved with the fuel cells. There are some numbers with the quite numbers. So the cost of the fuel cell also becomes a major area. If all the aggregates with Dr. Sonde and Atul presented and I was very happy that they have actually looked at the cost part, what we call the live LCOE, then the leverage cost of operation and sustenance. So that, with respect to that, you will notice that the cost of motors, the cost of other aggregates which are there is significant, and that is also taken. And the last part I want to say is when we go for all electric or under electric system, and we look at these batteries, look at these motors, inverters, transformers, high voltage, the Nmc problem, which is related to the aircraft as far as the avionics is concerned, also has to be taken into account. So these are some of my observations. And but the most important thing is the choice
the kind of fuel cell which we are going to make, whether we are going to have to start with prime fuel cells and generate the prime fuel cells. Straight away should we start looking at solid oxide fuel cells because efficiency is 70% versus 50% as far as the prime fuel cell is concerned. So you do get advantage, plus also you get flexibility of fuel as far as the solid oxide fuel cells. So taking into account that, I think my suggestion would be both the options should be pursued, SOFC as well as prime fuel cell. But in the prime fuel cell, clearly the higher the high temperature fuel cell, so that we will be able to reach the ultimate objective even with that. I will stop here and we will go further. We allow request
Students of our. No, I thought you can make a few comments and then I will tell you what we want to do.
Thank you, Chancellor. We can go into science. We will do an experimentation on a two-seater aircraft. And we have an engine-seater aircraft which is already in development. And that can be taken. But 70-seater is what we consider is something we have to look for. Because that is the one we are developing now. Today we are developing with the gas turbine and all that. But the next generation we have to bring this kind. So we are due to that. That is the kind of route we are looking at. We are also looking at that when we showed the discussion in yesterday that if we can make a product with the one with the battery, another with the fuel cell, then we have to choose which is the best one to go at. Then we will be able to cater to 19-seater, 40-seater, 70 and 90-seater. This is what it looks to us. And mentioned fuel cell, which one to pursue. That is what we think. Whatever I've seen now, the last few months, look at the PME is being used, maybe because that is available. But the high temperature also could be looked at. But the only thing about SOFC, what I'm not very clear is, there is a problem of pollution problem is still there, the SOFC. So that is what we need to look at. Clear fuel. That is what we need to, I think. My understanding is next 3 years, we must find the two-seater.
Even water can be used.
No, two-seater. And we need to see another 5 years where we develop the technology of fuel cell and all that. But the intermediate technology we can do with other. Also, we will try battery. We will also try battery and fuel cell because today, as far as the small or below 10 C is concerned, battery seems to be fairly okay. And we will have the most important thing is on the ground, in the road, what you call power, like iron bird, we have to have power plant, where we have to do, and problems are Nmc, very problem, and internet issues we need to solve. So these experimental programs we need to do, and we need the support to see how to move forward. I'm extremely happy today because all the actors who are involved in that, right from ISRO, NL, friends from HL, from DRDO, from ADA, and friends from other organizations, startups, and at least 6 other academic institutions, they're all here. So, and that's what all the industry and startups are here. And we look at not just merely at the propulsion, we also look at what is required for what you call a support utility system, how to make them. Okay, end to end we look at it. We are at a stage where a lot of work needs to be done, but this is the direction we would like to move, and we need to see how to go about it. And we have the chairmen of all the committees. Maybe 1 or 2 minutes if they can make the comment, that we can. Last chairman, the first.
Yes, please. Yes. We have to go through some kind of a rendition for the. As a result, we have said that the answer can be that cost on which we can really do this experiment. On an experiment, certainly, battery can meet the requirement of very hard. But our aim is to move this experimental platform. That means we should also develop other
this one. Second point is, today, fuel cell technology is actually evolving. We cannot say with whatever we have seen that we have matured technology in the country. But we have technology, may not be matured to the level of the aircraft standard. We have to bring that. But there are two routes suggested. Number one is that we must develop a complete system of fuel cell, including the every aspect of that optimization of that, and that experimental platform we must build on ground with something like 10 kilowatt cable. How do we do that and all that? We must have an experimental platform. Next 2-3 years, we must experiment with that, optimize system, whether it's cold hydrogen or hot that part, we can get a little more detail, but we need a platform to integrate all these systems. That's the second part. Third, of course, comes with respect to the overall management. There are a lot of discussion modeling also. I'm sure this will come. My personal perception is that it's a much smaller of a problem because we have been managing our systems. And luckily, we have Shankaran, who is the director of US now. His whole life has been in management of the power system and with quite complex power systems in the spacecraft. And we managed for years. To my mind, why people are talking because they have not done that, but we have done. So I think these are the problems which are solvable. They are just they have been solved already. We have to accept them. So I think other things are we can look at it, but a platform for 10 kilowatt is something very.
Another important from here is all that is the electric drive and the power chain. Entire power chain, not for the long electric areas. Therefore, when we started, we thought we should be pulling water itself is not available in the country of very high power. But as we were not discussing the clarity as not in a particular yesterday, was available. The ground is available, but this is a very high power motor. So, what was 50-50, 0 is something like 1 megawatt, 6 numbers go that 1 megawatt, 1.5, they are available. But what has happened is we also brought in industries. Then we presented experimental ways how they can manufacture, realize, a design methodology, testing. All of them are available. So that way, I think we are in a very comfortable position. With the electric drive, motor,
We have to make them.
I think it's also good to sort of evaluate between the power system and the drive system from the beginning. They know each other quite well because always the compatibility. One important thing is these are all emerging technologies are coming, but there is no way to gather the data and manage it. Only thing that doesn't emerge that you must put it in answer. You can learn the lessons, whatever that is. Biggest thing, what kind of problems that one will see and how to get solution. Just cannot have experience rather than all this theoretical analysis, they are okay, but then to realize and understand something that undergo, maybe also learning lessons we are implemented through. And we should go for 19 seater or staggered what we have done like 60 seater, 70 seater. I think that way, I think this 2 days discussion has thrown enough light. Many of the questions that even in our mind we are able to. So that way we can certainly look forward. What is required in India, I want to tell you. But Dr. Saraswat, we keep on discussing, but we are not able to really go for that. Safety approval, you know very well that we started back in 2015 to get the clearance for the regional transport data. It is still going back and forth, back and forth, back and forth. Even today, we don't even have an approval to carry on even the development project before. A country of this size, I think that is where we need to concentrate. We need to really do just to support this activity. A country like ours should have for the lack of that, you know, all of us sitting here, the kind of aircraft, the number that is required. So that should happen. And of course, when we do, we have already last time, it is better that we jump into the aircraft than to start that. We go by anything further. This is right in fact that the part of fun. This is what this married with the RT approval. I think they are in a very good position. Thank you.
Shankaran, that is here.
Thank you, sir. Also, let me fully concur with what the chairman Saraswat mentioned. In my opinion, also, SOFC is the technology we want to go for this kind of efficient power generation. To start with, we need not wait for the development of the fuel cell technology or reach the required efficiency. I think we should do it, go ahead with the demonstration with the available battery technology, making some compromises on the mass element of that, because the main mass is coming in the batteries because of the safety and take care of the accidents point of view. So to demonstrate the technology, I think we can make some compromises there, and compromising the range and the speed, we can demonstrate the rest of the electric aircraft, including the powertrain, the control system. All those things can be demonstrated first, where we parallelly work on the SOFC kind of technology. I think that is the way forward. And the area of battery, the issue what we are seeing is the non-availability of raw materials locally. The moment we want to make a lithium ion battery, we need to import. More than 50% of the items are not available in our country. We need to import. And the cost of import, if we are buying, say per day a million cells, this kind of production capacity if we are buying, today's cost what is available in market, that rate we will be able to match it. But the type of cost reduction we need to make it economically feasible is another 2 orders of magnitude reduction is there. That is where the battery technology may help us to do a technology demonstration that may not be really viable as a long term for as the energy source. I think we should understand this as the requirement.
Speak on the utility system. Why we wait for the years for time to get into the water? I considering these are 2 programs to be immediately done on the utility system. Now the environmental control is a major system and a major power. I immediately we should launch, and the only thing which is holding us is the indigenous availability of high pressure ratio, high speed, centrifugal compressor motor. As of today, in the commercial world, only 787 high speed this type of environment. And we want to do it, we can take hydro or RTA as an example. And we should immediately launch this. Second is Indian makes electric resource shown yesterday on the conceptual stage by Lucknow again. I think we should encourage them and immediately start electrical training, at least taking Saras as an example. We all the data for Saras, on the load and everything. I'm not too sure about landing yesterday, but we have to see how to work it maybe subsequently. And more the environment process. Also, we can take Saras as an example. We have all the data, we have the heat movements, we have everything. And we can start working on it, electrically,
So one point I want to make, I think the changeover to electromechanical actuator is the fastest and easiest possible, because both space and DRDO have done enough size, huge, small, all kinds of things. And that's the space and function. Yeah, we have. So only we should start using it in either ANSA and Saras at the earliest. So that will automatically introduce the system. Then reverse landing gear, braking system.
The industry man, you please tell us what are the issues. That's why I'm here.
So probably, since it's already emerged that what is the way forward, probably saying that even the focus and frames can be cascaded. So rather than waiting for the next phase, these technologies are already there. So probably in the first instance, once you move on to the engine, you can cascade the motors and frames so that it's available more. So that can be one way forward because fuel cell energy source can keep happening independently. If this is already done and tested, all of the sources are available. You are not waiting to catch it. And the one more point is that being a Navy man, from the day I stepped off the ship, EMI hygiene was always given to us. So they have considerable experience and test setups, which can be probably brought into considering the EMI hygiene is one of the very critical when power electronics and the motors coming into the chip. So that is something which may be a ready-made data, which would probably just hasten certain processes.
I want to add a point. One important point we came out is we have another industry about making motors. But he is looking for somebody who can develop control. IST and this team, they can work together and say,
The controls have been done by multiple agencies. Department of Space has done.
that's what I'm telling.
For many motors. The DRDO has done for many motors. So motor control is not a problem at all. Only industry has to work with them.
That's what I'm suggesting. Because Suresh, there is the chancellor. They can work with the IST and
all of them. I don't see.
No, but we have to
not want to.
See, what happens is they are separate. When you bring them together, you get the thing.
When they are making long-term plans, they should have a electric train plan as soon as possible. Inside the platform stuff. Slightly improved in terms of
You have to ask. I that. I am picking it last for you.
So, sir, we will definitely start outside the testing platform. Few technologies parallelly we will launch because first we'll buy some technologies and start integrating. And parallelly, I was just thinking some integrated joint working group has to be formed because some are expertise in some place, some are expertise, as you said, batteries, this, that, and all. So I will sit down and form an integrated joint working group, and probably technologies will start from okay, like 100 kilowatt controller, this, that will start from, and we will start making electrical rig also first because everything has to be integrated before we fly the aircraft. So that also we will start doing. And then slowly we will go to aircraft and all that. We have to take it to certification. All these are all challenges are there in front of us, but they are doable challenges. So I'm not finding anything. So the approach is like this: like start technology building parallelly, start integrated rig, and then whatever technology is available, start integrating and get experience on this, and then go to the certification, and then start flying there. Last one.
I think the time has come after listening to all this. We have found out this bond method as a now parallel development of technology as Mr. Jadhav has said is the right approach. In my opinion, I think the ANSA as the main flying aircraft. A system study should be done as to what are the requirements of the subsystem, what size of motor, what size of fuel cell, what size of other gadgets which are needed. If that can be done, then we can start, we will call it a mission. And while it is not a mission like nation mission or anything, but there is an R&D mission which will be launched. Will enable as spearheading that. And then you can have all the agencies like industry partners who can develop the motors, the laboratories who can make actuators, those who can make. Then, as far as the battery versus fuel cell is concerned, I tend to agree. See, this battery route is a very lucrative route. It is a route which has got a major pitfall. So sometimes what happens if you go into, that's what has happened in automobile sector. They did not pay attention to the hybrid vehicles and they went to battery vehicles directly. And today, you know what is the situation. Penetration has not happened even 2%. So this is the problem. You should actually go for fuel cell development and choices. Now, I agree with you, in India, fuel cell technology is still not so mature. But as far as foreign availability of the fuel cell is concerned, it is significantly mature. I want to tell you. H2E is a major partner in I think in Denmark or someplace, or Sweden, I don't know. They can supply you up to 25 kilowatt fuel cells without any problem. You can talk to them and they are ready to even set up a factory here. So you talk to Siddharth and you can work on that. Ballard company is manufacturing PAN fuel cells not today, but for centuries, for not centuries, decades. And they have got in Pune an office, so you can talk to them. PAN fuel cells, which are, I think, low temperature, I think 80 degrees. Low temperature fuel cells are available in the country. So, not waiting for our own development to mature to the highest level. I think when you start going into the system level, you can buy these items. Motors, inverters, transformers, converters, all that can be mapped out to the industry and the earliest to your basis and identified. Then you should, I was only wondering whether it is possible to do an unmanned platform for this kind of an. Can you think of for testing some of the things before we actually? Is it possible? This is a thought I have taken in my mind. Whether it is feasible or not, I think the expert will have to look at it. I have not given my mind, but just a thought came, so I'm just dropping the line. But I think anyone should start a mission. The DRDO and space, all three companies is a part of that. They should provide not only the human resource and the skills, but I am requesting that each one should pitch in certain money which can be coming in terms of an integrated program of R&D technology development. What is wrong? Nothing wrong. Some 25 crores he gives, 25 crores, DRDO gives 50 crores, he gives 100 crores, it starts to come. And that by the time we show the visibility, we can then go to very, let's say, please give us so much. We had a zero. Right now, so I'm thinking some participative management, both financially as well as otherwise, in the terms of skills and technology, will be the answer for our electric aircraft. You agree? Yes, yes. Yeah. So I think three departments, DRDO, space, and CSIR. And you have CSIR-NAL level. So you can work on that. This is what my thinking is. Industry should be certainly brought in for all electric items. HAL anyway, Lucknow is very good in many of these items. I don't know why you have such a serious doubt about landing here.
No, I have no doubt.
See, of course, that also needs an actuator.
Actually, the last resort to land. No, they have a safety issue. There was a discussion we had, but there is a solution also. They were.
I think you should not give up on that. So you should not give up on that.
That's what one last point.
Yes, to use it.
Suggested it's good to bring these two organizations, three organizations together. Maybe you should ask for a small meeting with these two.
I'll do that.
And tell them it's not big money. It's only
one more thing is there. NAL's RC, which I is supposed to be part of that, and many of us sitting there, will now sanction a program for development of a solid oxide fuel cell in the country. And for that, there should be a major drive with the industry as well as with other agencies to do that. And next one major program will be reformer development. What
IITBHU
has done, we should put our effort. I think they have done a great job. We should take it to a clear of commercial. These two areas.
Fuel cell, we have to have that.
Okay, thank you very much. Thank you. Thank you. Sorry, I will read up all of Sir, I'll do that. I'll talk to someone.
Yeah, this is all urban plant.
ये इस तरफ से अपने प्रांगण में लगा नहीं बोला
नहीं बोला प्रांगण एक साथ
Some will work out, not go through each one of the things. Whatever comes up to come, so we'll push further.
because